Ladies and gentlemen, everyone, please welcome Chris Lattner.
All right. Thank you, everyone. Welcome to ModCon 2026. Now, Modular's been on a journey for 4.5 years now, and that's a long time in AI. When we started the company, we made some contrary bets. We first believed that inference was more important than training, and that it would scale massively. We also believed that there would be many different kinds of silicon serving all this traffic. We also believed models and the infrastructure around them would continue to grow in scale and complexity. But even more, we didn't think there would be one quick fix. We'd all seen attempts to solve these problems that eventually fell away into the dustbins of failed promises. We thought we could crack this whole problem open, but we knew that it would take years of fundamental R&D. And if you fast forward to today, these things are no longer bets. They're also not contrary. These are the defining realities of AI that's all around us. Today, everybody knows the obvious truths. We've gone from Gen AI to reasoning models to agents. The data center today is heterogeneous. It's disaggregated. Research goes faster than ever before, and there's far too many fragmented integration paths. Even worse, everybody knows that we're in a compute crisis. It's obvious. So the industry is responding to this demand, and there's an extraordinary wave of hardware innovation. What I see is many different hardware vendors are racing to fill this void. They all have differentiated approaches to solve the problem. And through this, the industry is spending an incredible amount of money building heterogeneous systems. But in this lies the big problem. That's software. If you were to zero in to one example of that, it would be CUDA. CUDA was built years ago for physics and rendering triangles. It wasn't built for AI or Gen AI. It also wasn't built for today's developers. It has far too many ways of doing the same things. It also wasn't built for diverse architectures, and certainly wasn't built for other hardware vendors to use. If you take a step back and think about it, can you imagine running 20-year-old BlackBerry software on your modern phone? That's ridiculous. And because of this reality, each hardware team has had to invent their own stacks from first principles. Now, the leaders in the space have wildly succeeded, but even the biggest companies in the world struggle with the relentless pace of model research. For AI developers, though, well, we all have many similar but different stacks to juggle and debug. Modern AI is also way more complicated than it used to be. It's no longer a single forward pass running on a single chip. Inference is now a large-scale, distributed systems problem. You need optimizations at every level of the stack to be competitive. Now, when I look at this, I see the same problems and opportunities that I did when I was building LLVM back in the day. Everybody was running on 20-year-old GCC technology, and nobody could justify the investment needed to make a quantum leap. Now, just like then, if we could get everyone to work together, I think that we could crack this open as an industry. That would allow us all to move faster, to differentiate our systems, and fundamentally, to have happier users. And of course, that's why we created Modular. So over the last 4.5 years, we've built the world's first unified end-to-end production software stack that can run on many different kinds of hardware. This is a full-stack solution. It enables everything from AI kernels all the way up to our new Modular Cloud. This stack is today real and proven. Modular is now serving trillions of tokens in production every day. We provide industry-leading performance across NVIDIA and AMD hardware in the data center, and we also support Apple Silicon for developers. Now, if you've been following us for some time, you might already know this. But, of course, we're going to go a lot further today, and that's where it's fun. Today, I can finally share that we're expanding the modular platform beyond GPUs. We're now taking it to specialized data center ASICs. And this is not one small step. We're actually adding support for 3 entirely new architectures, bringing our total support up to 6 architectures from 6 hardware vendors. First, we're pleased to announce the deep engineering engagement with the AWS team has allowed us to add support for the incredible Trainium platform. Now, that's huge, but we're also very excited to add support for Google TPUs. This platform is one that I helped bring up many years ago, and let me just tell you, a lot has changed since 2017. Now, we're also very pleased to add support for the Qualcomm Dragonfly data center accelerators, current and future. And so when you look at this, Modular is now the first stack to unify CPU, GPU, and ASIC from 6 completely different hardware vendors with a single unified programming model. That's a big deal, right? Thank you. Now, I love hardware, and expanding our hardware support is a great validation of that original hypothesis. But we also have several announcements at other layers of the stack, too. So we have this amazing Mojo programming language. Well, today, we're fully open sourcing the compiler platform. This answers the call of many who wanted to extend Mojo in ways that even we can't imagine, and we're pretty creative. So we're also taking the next step with Max. I think it's pretty cool that Max supports 6 different architectures from 6 different hardware vendors, but there's a lot more out there, way more than Modular itself can support. To succeed at democratizing compute, we're taking that next step, and we're opening up Max for all hardware vendors. Modular Cloud has also grown up. We've been previewing it with design partners for quite some time. And so today, we're taking the wraps off, and we're publicly launching it to the world. Today, finally, I think you've probably heard that Modular has been acquired by Qualcomm. And so, today we'll share a lot more about what Qualcomm hopes to achieve with Modular, but also I think you'll get a really good idea of why Modular is so excited to join Qualcomm. And so if you zoom out, our mission is simple. We want to unlock heterogeneous compute for the world. We want to give developers the freedom to use the best compute for every workload, from edge all the way up to cloud. So this is what we spent the last 4.5 years building, and today I'm excited to reintroduce it to the world. And so to kick things off, I'd like to invite up Tim to give us a deeper dive into how the stack works.
Thanks, Chris. And welcome everyone to ModCon. Woohoo! As Chris said, at Modular, we spent the last 4.5 years building the software foundation for AI's heterogeneous future. And today, we're excited to reintroduce you to Modular, one integrated AI platform from kernel to cloud that unifies AI infrastructure for the world. Now, let's walk through it. At the foundation is Mojo, our high-performance systems programming language for AI. We built Mojo to reduce fragmentation of lower-level hardware programming models, providing a single interface to simplify the developer experience. Because Mojo runs on any silicon, hardware becomes a choice, not a constraint. Mojo combines Pythonic developer ergonomics with low-level control required to build and optimize AI kernels. It enables AI researchers, infrastructure, and hardware engineers to write portable, low-level AI optimizations in a familiar Python-like syntax without losing performance. And of course, it was designed for agentic systems, which benefit from our native portability and full-stack approach. Now, Mojo 1.0 landed last week, And we are now using it in production to process trillions of tokens per day from our ecosystem and partners, which we'll tell you about today. So go and use Mojo today. It's ready for production deployments, and it has a license we'll think you'll love, but more on that later. On top of Mojo is Max, our modeling and serving framework for production AI workloads. Existing frameworks were never designed for GenAI's autoregressive models. We wanted to fix this and take a first principles approach to building a modern, production-ready framework that starts with inference and will scale to training in the future. Max enables AI researchers, AI modeling, and optimization engineers to write incredibly performant AI pipelines in a single framework that has been designed with portability at its core. And rather than separating the modeling and serving like PyTorch does with VLLM, we've combined it together. So here's a quick summary of the benefits. Max provides one unified framework for hardware-agnostic serving. It gives developers a single path from modeling code to high-performance multi-node serving. And Max is fully extensible for your own custom models, kernels, operators, and hardware targets. Now, our newest layer is Modular Cloud. The modern AI data center is not a rack of identical GPUs anymore. It's a heterogeneous system. Prefill and decode disaggregated across different machines. KV cache moving over the network, and more. Yesterday's cloud stack was built for a simpler world. One vendor, one chip, monolithic serving. Nothing existed that could treat the data center itself as the computer, orchestrating heterogeneous hardware, disaggregating inference, and portable performance as one unified system. But that's exactly what we've built. Modular Cloud empowers AI engineers and production teams to access enormous amounts of compute. They can now scale their AI workloads without caring about what silicon is underneath, while having the best performance and TCO for their workload. Modular Cloud is the first cloud platform natively designed for heterogeneous AI compute. Developers keep a familiar API, but underneath, Modular handles all the complexity, like provisioning, scaling, optimization, and more. Eric will demo this a little bit later for us. So together, Mojo, Max, and Modular Cloud form the Modular Platform. A programmable foundation at the kernel layer, a complete modeling and serving framework above it, and production endpoints at cloud scale. Each layer is powerful on its own, and together they form a unified, heterogeneous stack from kernel to cloud. Now, the shape of this stack should feel familiar. Over the last 20 years, NVIDIA has proven the power of vertically integrating the programming model, runtime, serving stack, and cloud technologies. The difference is NVIDIA built its stack just for their hardware. But the world is made up of more than just NVIDIA silicon. With Modular, that world now exists. We can run on NVIDIA silicon, but also other types of silicon like CPUs, GPUs, NPUs, and custom ASICs. With the Modular Platform, we empower you now to have one programmable stack from custom kernels to production endpoints, one model and serving framework across the world's most important silicon, and state-of-the-art performance and lower cost per token, because every layer is optimized together. Open developer foundations from Max and Mojo with enterprise-grade deployment and consumption on Modular Cloud. But most importantly, we help you achieve silicon independence. You can get great TCO and a true partner to help you scale into the future with AI. Modular is the only production software stack that doesn't force you to choose. And we like to call this the hypervisor for compute. And it's here today. So let me explain what that means. Just as virtualization abstracted physical servers, we've enabled Modular to virtualize AI compute behind a single platform. Developers build and deploy against the same APIs, without having to think about which accelerator is underneath. We will route each AI token to the best AI accelerator for your workload. That means we handle the complexity so you don't have to. Our vision is to serve any model on any accelerator, all with one platform. And from day one, this has been our vision, and it's becoming real. Now, let's explore it layer by layer. Chris, back to you to take us on a deeper dive with Mojo.
Amazing. Thank you, Tim. As many of you know, Mojo is the foundation of the modular stack. It's our kind of not-so-secret secret sauce. But you might be wondering, why another programming language? Well, if you go back in 2022, we identified the root of the fragmentation problem. There is no cross-platform language for heterogeneous compute. Now, because there's no common language, everybody had to reinvent their own. But it's not really about the language. Every hardware platform requires their own compilers, their tool chains, their libraries, culture, developer community. And because of all this, the algorithms get re-implemented over and over again. Now, this might be okay for things like sine or cosine, but as you get up into kernels like softmax and attention, it gets out of hand. And this re-implementation creates a huge tax across the industry. Hardware vendors must spend years building software ecosystems before developers can use their chips. Users end up having to debug accuracy issues and even outright bugs when they move to a new system. If you do anything custom, you quickly run into the quirks and challenges of myriad weird languages and DSLs. The worst problem, though, is that AI model implementations default to being architecture-specific instead of defaulting to being portable. Well, that's a huge waste of time, and it reduces optionality for everybody. And these are all the reasons, of course, that we created Mojo. Now, Mojo is a systems programming language. It combines Pythonic syntax with low-level control and performance that AI hardware demands. Mojo is a fully featured programming language. It brings in many of the best features of previous languages like Swift and Rust, but it also goes way beyond them. It brings in things like MLIR, compilers, and advanced features like linear types. Now, while Mojo is a general-purpose programming language, of course, it shines when programming accelerators. Mojo provides precise control over memory, execution, performance, but it also allows you to make new abstractions. For example, if you take a look at a softmax algorithm implemented in CUDA, you can use the Mojo tile tensor library on the right, which makes it way easier to understand and extend. Now, high-level abstractions like tile tensor are what enable Mojo programs to write code that's portable across different accelerators. That's that secret sauce that I mentioned that allows Max to scale across chips from so many vendors. And this spans different kinds, too: CPUs, GPUs, and now data center ASICs. So instead of having one language per DSL per chip, Mojo provides that unification of the programming model for all hardware. Now, the key thing is that you also retain full control over any one device's unique features, because sometimes you do actually have to go all the way down to the metal and write assembly language, like PTX. Now, the payoff of all this work is that AI's core algorithms can be shared across hardware. And Modular has been building and using Mojo for many years, but we also have customers that have been benefiting from it as well. One example of this is Jane Street. They're a leader in high-performance compute. They'll do anything to squeeze a microsecond or a nanosecond out of an algorithm, and they push their GPUs to the limits. Sylvain is an engineering leader at Jane Street, and I think he summarizes the benefits of Mojo well. He points out that Mojo combines the familiarity of Python with powerful features that make it easy to get GPU performance. And beyond being leaders in the space, I'll share that Jane Street's also a super demanding customer, and so I want to thank them for pushing us to improve the stack in countless ways. Now, we've been building Mojo for 4.5 years, but just last week we announced our most important milestone so far. Of course, that's Mojo 1.0. Mojo 1.0 represents the first stable foundation for building production software in Mojo. It's a production that the foundation's ready. It's ready for production systems, for long-term investment, and to be the infrastructure that teams can depend on. You can now confidently build Mojo libraries. You can invest in tooling and for your production workflows. You can teach Mojo to your engineers and have durable experience around it. And Modular will continue to evolve Mojo with additive changes. And if we need to break something, we'll handle it like C++ or other modern languages do. Now, having achieved stability, we as a team are shifting gears. We've now figured out what is Mojo about, and what we want to do now is scale that ecosystem. And of course, one of the best ways to scale an ecosystem is AI, right? And Mojo was designed from the beginning for the era of agentic coding. Now, everybody makes some claim about that. What does that even mean? How does that work? Well, Mojo benefits from a huge amount of open source code. We've made it consistent. We keep it in a monorepo. And what we know is that AI and agents need data to be effective. And to go further, we amplify this benefit. We've created a wide range of AI skills for Mojo. These skills cover a whole bunch of different common use cases. This includes writing a GPU kernel, testing for correctness, doing optimization, benchmarking, refactoring, these kinds of things, which make it easier than ever before to learn Mojo, get building, and even bring code into the Mojo ecosystem. Now, I'm a pretty big fan. I know that AI is amazing, but so are strong partners. Mojo has long had great support for macOS, for Linux, and through Windows developers through WSL. But one of the biggest asks from our developer community has always been that they wanted native support for Mojo on Windows. The problem is that Mojo never really had the in-house experience to make Windows first class. But fortunately, in our journey, we found some people that do. I'm pleased to announce a partnership between Modular and Microsoft. We're excited to partner with the Microsoft Windows team to make Mojo really first class on Windows. Now, I'm super excited by this because I know that there are countless ways for Mojo and Windows to both expand each other's developer ecosystems. And I think this is a pretty big step. But I can think of one more way to get Mojo to even more developers. We all know that languages need to be open source to be taken seriously by developers, right? Now, I've open sourced a lot of code over the years. I've seen the problems that come up with opening the doors too early. Because of this, Modular has always taken a very deliberate approach. We've been progressively open sourcing Mojo as it grows up. We started in 2024 by open sourcing the Mojo standard library. Last year, we released 600,000 lines of Mojo code. That was a big deal. But people keep asking us, relentlessly, when are you going to open source the compiler? Well, we didn't want to do that until we hit 1.0. We needed to figure out what is the soul of Mojo before we wanted to do that. And so, of course, today, we're excited to announce that we're open sourcing the Mojo compiler and the toolchain. But we still have a small detail to figure out. What license should we use? Should we use a business source license, like many database companies do? Wouldn't it be funny if we used AGPL? Or GPL3? No, we would never do that. Come on, we want Mojo to be adopted by everyone, and we want to go everywhere. So today, we are open sourcing Mojo, the compiler and toolchain, under the Apache 2 license. This allows you to download the source, you can build the compiler, you can port it to new architectures. If you're a compiler nerd like me, you might have noticed, this is a big moment, because Mojo is the first language designed for MLIR. Now, Modular will continue to shepherd and direct the evolution of the Mojo language, and will continue to open up more and more over time. And so what does this all mean? Well, a stable, open-source Mojo is super exciting. Developers get the performance without being locked into one hardware ecosystem. Researchers get a new platform to explore new ideas. Hardware vendors get a faster path from new silicon into developer workloads. And every new target, new library, new kernel, new package, new idea that makes it into the platform makes it more valuable for everyone. So to summarize, our message is clear. We built Mojo to unlock the next generation of compute for the world. It's stable, it's open, and it's ready to build on. Mojo is no longer just Modular's language. It's now your language. We want you and the entire industry to explore what it can do. And with that, I'm going to bring back Tim to talk about Max and the cool things we're doing there. So thank you.
Thanks, Chris. How exciting is that? So Chris just walked you through Mojo, but on top of Mojo sits Max, our hardware-agnostic modeling and serving framework. Max delivers state-of-the-art performance across models and hardware that matters. It provides a complete AI inference stack from low-level kernel programming all the way through to model definition and execution, and then production serving. But you might be wondering, why did we need to build Max in the first place? PyTorch was created in 2016, nearly a decade ago. How crazy is that? For a very different era of machine learning. Its flexibility, intuitive programming model, and Python native experience made it an extraordinary tool for ML research and training. But large autoregressive models change the inference problem entirely. Inference is now a systems problem that involves handling different input sizes, prefill and decode parts, managing KV memory, and more. VLLM and SGLang made major advances here, but they were built on a stack that was optimized around the NVIDIA ecosystem. So portability is still gated by what's underneath, the frameworks, the runtimes, and the kernels. The same fragmentation Chris described earlier. That is the problem Max was built to solve. The industry needs a production-grade inference stack designed from the ground up for modern generative AI. One that was not designed around a single hardware ecosystem. And it needs to deliver industry-leading performance for different models and different hardware. We couldn't just reuse an existing research framework. We had to start from first principles. So we rebuilt the modeling and serving path from the ground up, with Mojo as the programmable foundation underneath it. So this includes high-performance Mojo kernel libraries that are now all open source, a model compiler and runtime from graph execution, and advanced serving optimizations. This vertically integrated architecture gives Max visibility and control across the entire AI execution path. Now, Jane Street Sylvan is a great example of why that matters. He created the Hugging Face Accelerate library and is an experienced AI infrastructure leader. As Sylvan describes here, what makes Max different is that Mojo and the Max graph compiler are designed together. Because the compiler sees both the model graph and the kernels beneath it, it can generate fused execution paths that are hard and sometimes impossible to express in a fragmented stack. So, what does it actually look like to use Max? It looks very familiar. Simply serve an open weight model without rewriting any model code. Point Max and model weights or a local checkpoint, and it automatically loads the model, compiles and optimizes it for the target hardware, and starts an OpenAI-compatible endpoint. Max supports the capability modern AI applications increasingly depend on: multimodal inputs, tool calling, structured outputs, prefixed caching, speculative decoding, and advanced multi-GPU parallelism. And it supports a broad and growing set of frontier open-weight models, including leading model families like Minimax, Kimi, GLM, Flux, and many others. So developers get one production inference stack across a very different set of model architectures and workloads. But model portability is only half the equation. Max models are not tied to just one accelerator, as we've been saying. To show you that, here's a terminal window with Max executing across heterogeneous accelerators from the likes of NVIDIA, AMD, AWS, Google, Qualcomm, and others, several of which you'll hear much more about today. How awesome is this, right? Now, while running across many devices is certainly impressive, you want a hardware abstraction that also doesn't sacrifice performance. But don't take our word from it. Let's hear from Hippocratic CEO Manjul Shah and CTO Datar, who we worked closely with to achieve more than 30% gains over SGLang for their extremely low latency workload, helping them define state-of-the-art.
For all of human history, we've approached healthcare from a point of scarcity. But now, with generative AI, for the first time, we can deliver abundance to every single patient in the world. But to do this, you need an AI that's persuasive and empathetic. And the key to both of those is having a low latency experience in terms of the voice AI that we're delivering when we call patients on the phone. Imagine if I call you and I say, I love you, and you say, oh, I love you too. It's not quite the same as if you say it immediately. This is why we partnered with Modular, to really figure out, when you're deploying large models at scale, how do you deliver a low latency experience so that you can have the empathy and the persuasion you need to convince patients to do the things they need to do to improve their health?
In this clip that you're about to hear, it's a drug identification clip. So here, the patient hesitates with the medication name pronunciations. Medication names are hard for everybody. And there's an ASR, and then there's all these LLMs, and then there's TTS. And latency obviously compounds at every stage. And you will notice how seamlessly our agent can identify the drug pronunciation with all this user hesitation. Sometimes the user will even mispronounce the drug a little bit, and then we'll spell it a little differently, and our agent just gets it. And this is the magical user experience. I feel like AI was designed to do this task. Drug pronunciation is hard, and it's hard for humans. And getting it from partial pronunciations to this cascaded systems, and each of these LLMs reason over each of these tokens that are output from the previous stage, and then actually getting it right leads to this magical experience. And this is actually one of my favorite clips.
Could you tell me the name of the medication you're currently on?
Risperidone, Wellbutrin, Kazocin, and omeprazole, and there's one other, but I don't remember the name.
I appreciate you giving me the names of your medications. To ensure we have the right details, could you confirm if I've got the names right? For Risperidone, are you referring to Risperidone?
Yeah.
Thank you for the confirmation. Regarding Wellbutrin, are you talking about bupropion hydrochloride extended release?
Yeah.
Thank you for the help. Let's proceed to Passin. Could you help me out by spelling the name of this medication?
Prozin, I guess.
Based on the information given, it seems like you might be talking about Prozocin. Does that sound? Yeah. I'm happy to hear that we're on the same page about your medications. Are you taking these medications as directed by your doctor?
Yeah.
Woo! How amazing is that? Thanks, Munjal and Deba. It's been incredible to collaborate with you.
For all of human history.
Well, to help thousands of patients experience better healthcare, and we're excited to keep building together. Now, Max isn't just limited to the data center. It's also available for local development on Apple Silicon. Here, you can see us running a local Gemma 4 server directly on a Mac. This gives developers a much tighter development loop. Build and test locally, then move to the cloud or data center infrastructure using the same programming model and serving APIs. But Max was architectured from the beginning with a much broader goal: to unify AI compute from the cloud all the way to the edge. And we're already seeing the leverage of that architecture. With relatively little dedicated optimization work, and in some cases just from our interns and even PM side quests, we've been able to bring Max up with extremely strong performance across systems like the DGX Spark, AMD client devices, and Qualcomm Snapdragon. We have several of these running out in the demo area, so go out and check them after the keynote. Max also lets you define your own models. It can be easily extended to support any variety of novel use cases. We expose the same modeling APIs and infrastructure that our own engineers use to bring up new generative AI architectures to state-of-the-art performance. Max uses the same core concepts developers already know from frameworks like PyTorch: modules, layers, parameters, and tensors. So if you know PyTorch, the Max model authoring experience will feel immediately familiar. As you can see from these examples, the code looks really similar. The key difference is that Max combines the eager, interactive Pythonic development experience of PyTorch with a production runtime designed for compilation and high-performance execution. And increasingly, developers don't have to perform every step of model bring-up themselves. Agents can do that work directly with Max through its foundational APIs. With stable modeling and serving APIs, coding agents can now author models, port existing architectures, validate numerical correctness, debug accuracy issues, and optimize performance. In practice, that means an agent can help take an architecture from a trained PyTorch implementation to a production-ready Max deployment in hours or days instead of months. And so in the video you just saw, for example, an agent ports the Liquid AI LFM 2.5 model from PyTorch to Max in a single pass, validates the implementation, and then serves the resulting model. We've published the workflows behind this as a reusable set of skills on GitHub, and we'd love all your help to improve them. And when combined with Mojo skills we showed earlier, agents can go even deeper, extending Max models with new high-performance kernels. With Max, AI agents can now operate in a single vertically integrated infrastructure stack. We have brought up major models like Kimi K3, GLM 5.2, and other smaller models like Thinking Machines Inkling completely using our agent harness. And we're not stopping there. We're accelerating this work. Max is free to use today, and we have already open sourced much of the developer-facing foundations of our stack, including the Max Python APIs, model implementations, pipelines, serving interfaces, and more than 600,000 lines of kernel code. You can start using Max today through our Python packages or our pre-built Docker containers. So that's Max. Run models out of the box, bring your own weights, or implement entire new architectures with open agentic infrastructure, serve them through a compatible OpenAI API, and deploy the same software stack across a growing range of hardware targets from edge to cloud. One framework for model development and production serving across models, across accelerators, with state-of-the-art performance. Now, I want to pass to Eric Johnson, our VP of Product, to take us into the cloud to see how it all fits together.
Well, thank you, Tim. Hey, everybody. It's nice to be here. Let's jump right in. So Tim just showed you how AI inference has evolved to meet the demands of autoregressive Gen AI models, how Max is solving those challenges across different hardware. But as Gen AI has scaled, so has the system around the server. In production, a single server is just one building block in a much larger deployment. Once you're operating hundreds or even thousands of those servers, achieving state-of-the-art performance requires significantly more. Optimizing memory requests, organizing scheduling, compute, all across different nodes. So put simply, Gen AI optimization problem has moved beyond the individual server up into the entire cluster. And that's the next problem we're solving with the Modular Platform. So today, we're incredibly excited to officially introduce you to the Modular Cloud. Modular Cloud takes the same philosophy behind the rest of the Modular Platform and extends that approach to the whole data center, treating the entire cluster as a computer itself, coordinating scheduling, memory requests, and compute as one integrated, coherent system. But this isn't just a high-level abstraction layer. It's built on top of Mojo and Max, so it's deeply integrated from the cloud layer all the way down to the model runtime and the kernels. That means applications can be decoupled from the underlying accelerator without sacrificing performance, and developers get one consistent interface while Modular handles the heterogeneous complexity underneath. So this makes Modular Cloud the world's first true hypervisor for AI compute. At Modular, we believe AI infrastructure is entering a transition similar to the virtualization shift that transformed the data center 20 years ago. Developers shouldn't have to reason about the individual accelerator architecture any more than cloud developers today reason about individual physical servers. They should describe the workload they want to run and the business requirements they care about, and the infrastructure should handle the rest. It should determine where to run it and how to run it best. Importantly, developers don't need to learn a new interface to take advantage of any of this. Modular Cloud is exposed to an OpenAI-compatible endpoint, very similar to Max. Developers focus on the application. We turn the underlying compute into reliable, high-performance, cost-efficient tokens. Today, Modular Cloud provides live endpoints for many of the most important open-weight models. That includes Minimax, Kimi, Gemma, GLM, and much more. You can access these models through the model library at console.modular.com today, a curated collection of live shared endpoints
for fast experimentation and benchmarking. If you don't see the model you want, we support hundreds of additional model architectures that we can bring online for custom enterprise deployments. In addition, Modular Cloud gives enterprises the controls they need to manage inference across their organization. So that's secure access, governance, observability, user management, and a whole lot more. But importantly, what about performance? So under the hood, Modular Cloud brings the latest cluster-level optimizations into one integrated system. So compared with simply scaling out more replicas, these techniques can deliver 2 to 3 times higher performance from the same underlying compute. That includes capabilities like distributed KV management, disaggregated prefill and decode, topology-aware scheduling, intelligent request routing, dynamic replica scaling based on traffic and workload characteristics. And of course, all of this built on top of the max optimizations Tim just spoke about. So that's high-performance kernels, optimized graph execution, quantization, spec decoding, and a whole lot more. Importantly, the gains compound at every layer of the stack, delivering industry-leading performance for end users, and we have the results to prove it. So last month, we submitted 4 Modular Cloud endpoints to artificial analysis, and we deliberately chose very different workloads. So Minimax M3 is a frontier language model with demanding long context inference. Google Gemma 4, a much smaller language model. Black Forest Labs Flux 2 Klein, a very small image generation workload with very different execution patterns than autoregressive LLMs. And Moonshot's Kimi 2.7, another frontier language model, but with a different architecture and execution pattern than M3. So how did we do? Well, across all 4 benchmarks, Modular Cloud ranked either first or second across all providers, with up to 2x performance over any other competitors. And today, before coming on stage, we got new results for Minimax. We are 2x faster than the nearest provider on M3. So for most competitors, so the thing to realize about all these results is most competitors are specializing on a single workload or a specific type of workload. We're delivering top performance across different model sizes, different architectures, and even different modalities. And these results really aren't the ceiling for us. We have additional optimizations coming very, very soon that we expect to push performance even further in the coming months. Now, whenever you see benchmarks like these, I think you should be healthy or have a healthy amount of skepticism. Was the model changed? Was quality reduced to improve performance? Was the workload representative of what actually happens in production? At Modular, we often ask these questions because ultimately our goal really isn't to win benchmarks. It's to support real customers and win their workloads. So I'll let you in on a little secret. For the last several months, we've actually been running Modular Cloud in production at scale, real developers, real traffic, real workloads, all on Open Router. We haven't, though, been calling ourselves modular. Apparently, we're much better at building AI infrastructure than we are at naming things because we've been operating under the incredibly creative name of Model Run. I believe it was actually Run Model Run at one point. Yes, so under Model Run, we have been serving live endpoints for several of the industry's most popular frontier models. And during this time, Open Router has grown enormously and now makes for an unusually demanding production environment. It spans a broad mix of users, applications, request shapes, usage patterns. So there's no single workload that you can just optimize a whole stack around or a benchmark that you can tune for. In many ways, it's a more representative test of general purpose performance under real-world conditions than any sort of benchmarking platform could provide. So the question is, how did we do? Well, across our endpoints, Model Run is ranked, again, top 1 or 2 across all providers in the platform for latency and throughput. Here you can see some results from Minimax M3, and again, we're clearly number 1 in both dimensions of latency and throughput. We've done this whole thing while maintaining consistent reliability across trillions of tokens served every day. And in fact, these are the same endpoints that power the new live endpoints on top of Modular Cloud that you can try out today. So you can continue using them through Open Router, where Model Run, or Run Model Run, will now operate under the Modular brand of an official partner of the platform. And you can come directly to Modular Cloud, where we can offer deeper customization, dedicated deployments, and stricter performance SLAs. So same underlying platform, just different ways you can consume it. But the best way to understand the value of Modular Cloud is to hear from an enterprise already running it in production. So let's take a quick look at how one of the world's leading AI modeling companies, Minimax, is using it today.
Hello, everyone. I'm Yi, co-founder and president of Minimax. Congratulations to Chris, team, and the whole modular team on ModCon. Our mission is intelligence with everyone. This year, we open weight Minimax M3, the first native multimodality open model with frontier coding and agent capabilities, and 1 million token context. And we build it to be efficient because the world is about to consume tokens at a scale it has never seen. We believe in openness, and we want to work with developers to grow the open ecosystem and keep innovating together. Our open models need strong infrastructure behind them. With the right infrastructure, anyone, anywhere can run those models quickly, reliably, and affordably. This is why our partnership with Modular is so critical for us. The Modular team has spent decades building the foundation of modern AI software. They rebuilt the entire stack from the ground up. What impressed us most was the pace of execution. We went from the first conversation to serving Minimax M3 in production on a large scale in a remarkable short time, with startup performance and cost per token. And this is just a start. Modular team, they runs across NVIDIA, AMD, and future accelerators. So our model can reach more developers, more enterprises, and more market without being tied to any hardware platform. Looking ahead, we are excited to expand our work with Modular across more Minimax models, from Answer's language model to our H3 of multimodality model. Together, we aim to deliver high performance, efficient deployment across a broader range of hardware and make these models accessible to more developers and enterprises around the world. Congratulations again to the Modular team on ModCon. Let's build intelligence with everyone together.
Thank you, Minimax. As you guys can see, Modular helps enterprises get more performance from every dollar of compute. Now, so far, every performance result you've seen today has been on NVIDIA hardware, and we're proud that the Modular Platform can deliver industry-leading performance on the de facto standard for AI hardware. But we spent this entire keynote talking about heterogeneous compute, so there's an obvious question: what happens when we take everything you've just seen and run it on a different GPU, perhaps an AMD GPU? Well, we've been working on that too. Shortly after ModCon, Minimax M3 will be live in Modular Cloud, running on an AMD 355X accelerator, AMD's direct competitor to the NVIDIA Blackwell. You can already see how it compares. Holding deployment size and latency targets constant, our AMD configuration delivers roughly 90% of the throughput of the B200, but the economics look very, very different. So at the current market rates, MI355X costs roughly 50% as much as a per accelerator hour than a B200. If you put 90% and 50% together, the AMD deployment delivers more than 45% lower total cost of ownership. That's the economic power of heterogeneous compute. And Minimax is just the beginning. We'll continue to bring many more AMD endpoints up over time. And as you can see, Modular Cloud is the culmination of a 4.5-year journey, and we believe it can fundamentally change how the industry builds and operates Gen AI infrastructure. There's a lot more coming, but for today, you'll have to settle for some of the highest performance model endpoints in the world on NVIDIA and AMD. Modular Cloud is live now at console.modular.com. Go try the endpoints, and for today only, we're giving $50 of free token credits to anyone who signs up, so please do. And if you're operating AI at serious scale, come talk to us. We'd love to help you increase throughput, improve utilization, and lower your cost per token. And now, to show you how we're extending this platform across an entirely new class of AI hardware, I'm excited to welcome our VP of Engineering, Mustafa, to the stage. Thank you.
Hello, everybody. It's nice to see you all here today with us. At Modular, we love hardware, and we're excited to see innovation happening every year. Today, we launched Modular Cloud with the state-of-the-art performance on NVIDIA and AMD GPUs. But we're not stopping here. And you might be asking yourself, why is that? If you look at the chart, you can see that AI chip sales continue to grow year over year. But what is interesting here is the hardware being installed is being diverse. And we see growth in the shares of the alternative hardware, AMD GPUs, Google TPUs, and AWS Trainium chips. All of these coinciding with the growth of generative AI inference. That GPUs are good at general compute, but ASICs bring further specialization. And it's a fundamentally different hardware architecture. It is specialized for optimizing AI workloads. For example, in-memory compute optimizes the decode phase, while when you have a dense systolic arrays, it optimizes the prefill phase. And at Modular, as you heard before, we built an efficient flow to bring up new AI hardware. The process starts with getting Mojo vector add running on the device. Simple thing. But we gradually enable more functionality. We grow through the steps. Tile tensor is used to implement matrix multiplications, the foundation of AI, to target the matrix accelerator in these chips. And then we go into a Hello LLM. Basically, a max graph compiler and runtime, working on the ASICs, leveraging the optimizations such as Fusion, all hardware portable. At this point, max serve requires no to minimal change to get to a full serving. The last final steps, as you heard from EJ and Tim, we want to deploy in the cloud, because that's what we do. And at that stage, we want to serve frontier model, mixture of experts, and such as min-max M3. Each one of these steps builds on the foundational layer below it. And what is important, that we maintain a shared code base all across the different accelerators. At Modular, we have been collaborating with a variety of key industry leaders in the data center. One of the key partners in this journey is AMD. And here with me today, Anoush, the VP of AI software at AMD. Please welcome Anoush to the stage. Hi, Anoush. Welcome.
Mustafa. Thank you.
I know that you have a lot of interesting stuff for us today.
Thank you for having me. So AMD's AI strategy is based on three important pillars. One is a leadership roadmap and delivering transformative AI performance. Two, deep partnerships at scale. We want to build the future of compute together with other AI leaders. And then third is an open innovation ecosystem, driving adoption through open platforms. So that's our core pillar that three core pillars that we focus on. And we, let's talk about our, the frontier racks that we're building. Let's move to the next slide. Yeah. So frontier AI requires an integrated rack architecture. This starts with compute that is leadership for the industry, both CPUs and GPUs, our EPYC CPU line and our GPU line, Instinct GPU line. Then it's built on an open rack infrastructure, right? And so this, we want everyone in the ecosystem, the hardware partnerships to all come together to build an open rack architecture. And third, it's built on an open fabric to scale AI. All the frontier AI labs and research is happening at a rack scale, and that requires our AMD Pensando NICs and an open ecosystem of the fabric itself. And we need to bring all of this together with a rack scale efficiency, and that has to be enabled with the corresponding software. And so the software increasingly is AI assisted, right? And so the AI assist is where we start automating and writing the automation of the kernels, and then the open source ecosystem allows for frontier models to be able to talk in a native in a native tongue, right? Because it's all open source, so frontier models natively know how to interact with open source. And then the abstraction, similar to what Mojo provides, it increasingly rises up, making agents talk natively and in an open source form to unlock the power of AI. So with all of this, the next evolution brings us to what can we actually provide to the end customer. So if you look at what we provide on the MI355X, we have SOTA performance working very closely with the Mojo and Modular team to provide TCO gains. And this brings the cost of tokens is what actually drives the outcomes. And it is not necessarily just teraflops or micro benchmarks. It is what is the end outcome. And this, as Mustafa had mentioned, the performance and TCO gains that AMD provides in partnership with with Mojo is spectacular. So bringing it all together, what does this provide us? Modular, Max, Mojo, combined with core ROCm, it forms a deep partnership for us to be able to unlock a multi-generation journey of MI325, MI355, and MI455 to be able to unlock the performance on Modular Cloud. Open software makes open hardware real, and we'd like you to come try it with Modular Cloud. Thanks, Mustafa.
Thank you.
Thank you.
Excited to see more of AMD hardware being served in Modular Cloud. Now, AMD is not the only hardware vendor we're going to talk about now. Another industry leader in the data center AI hardware is AWS. Modular have collaborated with AWS to bring the most cost-efficient compute to the open source models. Trainium, as you all know, is a well-established ASIC design. It's deployed broadly for several years now. The AWS brings a new generation of hardware every year with improvement in compute, memory, and communication. The Trainium chip design contains a SRAM and a general purpose core, but also incorporates a matrix accelerator. Each one of these chips can go into an ultra server and connect many chips together in a high bandwidth interconnect. The Modular team started to bring Max and Mojo support for Trainium this past May. The team went through the flow of bringing a new hardware architecture into the Modular platform, relying only on the Trainium MLIR backend and runtime. Today, the team is able to run a full serving of a Gemma 4 31 billion parameter model end-to-end on 4 Trainium 2 chips. This support means that a programmer can now write a general-purpose Mojo program and run it on Trainium. The same code that compiles and runs on GPUs today runs on Trainium. The example that you see here on the screen is a fully functional matrix multiplication. It's using the tile tensor abstraction to target these matrix accelerators on the chip. And if you are a hardware vendor here in the audience, probably the experience feels a little bit different. And for those of you who are not familiar with this, in the industry, this typically takes hundreds of engineers for more than 2 years to bring a full stack. Go ask my friends in the hardware company. This is because hardware vendors are forced to re-implement everything from scratch with minimal reuse. That's a 2,400 engineering months per accelerator. If we take Trainium bring-up as a case study, 5 modular engineers brought the Trainium into max with full serving support in less than 5 months. And I'm padding up, not down. Relying only on the documentation and answering technical questions from our collaboration with the Trainium team at AWS. Great collaboration. That's only 25 engineering months for a totally new hardware architecture. What that means is that with Modular Platform, you can get a 98% reduction in engineering time when bringing a new ASIC. That's look amazing. But Trainium is not the only ASICs that we'll talk about today. You all know about the Qualcomm acquisition of Modular. We're all excited about it. But you don't know that we have been collaborating with the amazing team at Qualcomm since February this year. And here with me today, Rasheed, Qualcomm SVP and Head of Data Center Engineering, to tell us all about the Qualcomm data center hardware. Please welcome Rasheed to the stage. Hi, Rasheed.
Thank you, Mustafa.
I believe you have a new introduction to the Dragon family today.
Thank you, Mustafa. And thank you, everyone. We've come a long way from our initial meeting to understand Modular Platform and how we could integrate it with Mojo, Max, with AI 100 and beyond. And yes, we have 3 members of the Dragonfly family, AI 200, 250, and 300. We defined AI 100 Ultra just a few months before ChatGPT was introduced. It's a PCI card built for LLMs with a focus on high memory capacity and high bandwidth per watt. And of course, you can connect many of these together for larger models. Since then, we have a complete cluster scale solution built around it, a full infrastructure management suite with support for popular frameworks and serving engines. And it is in production at several CSPs and application providers. Our approach to AI 200 and 250 is one of continuity. One NPU architecture, one software stack. In our roadmap, each generation is additive rather than a reset. A model qualified on AI 100 Ultra runs unchanged on AI 200 and 250. So we're bringing to market a lineage, not a series of point products. AI 200 is built for larger scale-up, runs much bigger models. And AI 250 is our differentiation bet, where we introduce high bandwidth compute, which is an architectural choice, not just a spec jump. Throughout all of this, our North Star is the best performance per dollar per watt, generation after generation. Our products are built around our higher performance, low power NPU, and high memory density solutions. With AI 200, we scale the platform itself, much larger memory density, bandwidth, compute, and lower communication latency relative to its predecessor. It is teams found it easy to bring in the Qualcomm NPU, and within a few months, and modest engineering bandwidth, we are serving Gemma 4 on the Modular Cloud. Then we went further. Just 2 weeks back, we enabled the modular team with AI 200. And we have Gemma 4 working with Mojo and Max on AI 200. This speaks to two things: the Qualcomm data center AI designed for continuity and the modular portability by design. We are truly excited for the road ahead with the modular stack on the Qualcomm data center AI platform. Thank you, Mustafa, and the rest of the modular team.
All right. Okay. Qualcomm Dragonfly is not the only chip that we'll enable today. You might be asking yourself, what about TPUs? This time, we wanted to see if a team other than modular team, we wanted to prove that our engineers are not like Superman or women or something. So we wanted to ask a different company to go and work with us in order to work on a modular platform. So this time, we collaborated with EdgeTech. And here with me today, Darko, the CTO of EdgeTech. Please welcome Darko to the stage. Hi, Darko. Please tell us how your team has been doing with Mojo and Max.
Yeah, thank you very much. I'm really excited to be here and talk about our experience with Max and Mojo. But let's first take a look at what TPUs bring to the AI acceleration. Google TPUs accelerate AI through full-stack hardware-software co-design, dedicated matrix multiply units built as systolic arrays, a memory hierarchy purpose-built for AI, and high-bandwidth optical interchip interconnect that scales thousands of chips into a single coherent accelerator. Through history, V6 was built for efficiency at scale, V7 for inference, and V8 for the agentic era. In order to leverage all of that hardware performance, you need a good platform. So our goal was to enable Mojo and Max to run on Google TPUs. We started with limited TPU-specific knowledge, only a handful of engineers, and no TPU backend available in the upstream, and also not part of LLVM project. Our team got access to Modular closed source, where all of the fun of enabling new hardware actually happens. The team got access with documentation and support from Modular team in form of a couple of engineers answering questions and providing some education. So almost no prior knowledge. Within only 4 months, we moved from limited TPU knowledge to successfully running Mojo and Max workloads on TPU, specifically Gemma 4 dense model runs. What this demonstrates is that supporting a major hardware platform does not necessarily require hundreds of engineers. A small, highly capable compiler and runtime team can deliver it quickly. It's true that EdgeTech engineers are great, but this blows away the industry standards and a testament to Modular Platform unique design. Here's what the team learned compared to other experiences that we had. A single platform, single code base, make it much easier to enable full stack. Mojo is key to targeting low-level hardware features, such as systolic arrays. Max portable design allowed reuse of most parts to run models end-to-end. No re-implementation of an AI compiler specific to TPUs. Even without an upstream backend, a well-defined MLIR contract and a clean runtime interface allowed a handful of engineers to bring an entirely new software ecosystem to Google TPU. Thank you, Mustafa. Hey.
Thank you, Darko. Okay. It's really exciting to see what the EdgeTech team was able to deliver with Max and Mojo in this record time. What we have seen here today is that we are able to bring 3 new ASICs, new architecture, into Max and Mojo in record time. This means Modular Platform supports the 2 leading GPU providers and 3 major cloud AI ASICs. Today, we are able to run the Gemma 4 31 billion model full serving on TPUs, Trainium, and the Qualcomm Dragonfly, while the AMD and NVIDIA GPUs are in production at scale in Modular Cloud. All of this while we are building the full stack, serving customers in production. And Modular is really a small team. I did some averaging, and we are like about 100 engineers over the last 12 months. This is a total 5 accelerators supported in Modular stack, comparable, and I did the math, to 12,000 engineering months to achieve an equivalent outcome. Isn't that amazing? That's a 10-time reduction in scope while reaching similar level of performance and quality, and sometimes even better performance. This is a new world where you, as the hardware vendor, you can bring your AI hardware into a full stack in weeks rather than months. We saw the AI 200. But how is that possible? So let's look at the current AI software stack. There are many components spread across many organizations. You know, engineers were human. And hardware vendors have to build the alternative to CUDA, optimize libraries, and integrate into third-party software. And when a new algorithm comes in by these model developers, typically it's designed for NVIDIA. And then you have to go and rewrite it to the accelerator-specific language. This is a coordination across thousands of AI infrastructure engineers across the industry. Each one of these connections doubles the complexity of the solution. Modular removes that complexity with a well-designed software stack that minimizes the surface of interaction to the hardware. That's the key part. All of that unified under one code base in a single platform. This is why we maximize the sharing. The important thing here is that we also specialize, but we specialize when the things that we do bring the biggest return for that accelerator. We basically turned an exponential scope of AI accelerator enablement to a sublinear with Modular Platform. If you like hardware innovation like we do, you will love Mojo and Max, because it will enable your software engineer to focus on what differentiates your hardware. And basically reuse the deep technical investment that we put in at Modular for the past 4.5 years. This is why the team at D-Matrix were excited about what Modular have to offer. And D-Matrix told us, the CEO said, Seth, that our platform shares their mission and vision. And D-Matrix today are collaborating with Modular to bring their ASICs into the Modular platform as well. But this is not all. We learned that having a well-designed platform makes agentic coding more effective. Chris and Tim talked about it. But this means that for your hardware, you can make your engineers much more effective by empowering them with agentic coding. And with the space of AI research today, hardware vendors have to move fast to be able to keep up. Basically, Modular Platform will make it possible for a hardware vendor to even have a chance to keep up with the neck-breaking pace of AI. I am sure you all are excited about this and wondering what that means for your own hardware. For this, Please welcome Cristiano to the stage. Hi, Cristiano.
Mustafa, thank you so much. Thank you very much. Hello, everyone. Very, very happy to be here. Thank you, Mustafa. Thank you to the entire Modular team. This is such a special moment. I think it's a brand new chapter for Modular. It's a brand new chapter for Qualcomm. Chris, to Tim, the Modular team, the entire Modular community, welcome to Qualcomm. I think when we met Modular, it was like love at first sight. It was a complete alignment on the vision, on the opportunity, the culture, and the things we can do together. After everything we've seen today, I'm even more excited about what we can create together. This team has accomplished a great deal in a very short period of time. You saw it. Mojo is now open source under Apache 2.0. I think there's something to it. Qualcomm acquired Modular, we're closing the transaction, and then Mojo is now open source on Apache 2.0. It's a new Qualcomm. It's a new industry. And I think that's an incredible opportunity. I cannot wait to see where the community is going to take it across more data center hardware, edge devices, and new domains. You saw Qualcomm AI 100, Google TPUs, AWS Trainium, they're all being brought up on Macs now. And all of this shows what is possible with the Modular Platform. But this is a lot more than the two companies coming together. It's another step in the Qualcomm journey to become a developer-focused company. AI hardware innovation is accelerating, but great hardware only matters if developers can use it. Today, too much innovation is constrained by software stacks designed for specific hardware architectures, including our own. The industry, not only Qualcomm, the entire industry needs a common software foundation. Developers should be able to build once and reach every single accelerator. Model creators and infrastructure providers should be able to choose the hardware with the best performance and economics. And hardware vendors should be able to compete and innovate on the merits of their technology. I think we're all very motivated to innovate and compete on the merits of our technology. And that's our vision for the Modular Platform. Let me be very clear about Qualcomm's approach. We did not acquire Modular to make it a Qualcomm-only software stack. Modular will continue its mission to support and optimize a broad range of hardware. Actually, we're very grateful for some of the partnerships displayed here today. We believe the opportunity is much bigger than any one company hardware. We want the Modular Platform to become a common foundation the ecosystem can build on. To realize that vision, we need broader participation. We wanted to make it easier for developers, but for enterprises, for hardware vendors and partners to build on and contribute to Macs. So that's why we're also changing how Macs will be licensed to make it more permissive and accessible to everyone. And by the end of this year, we will launch an alliance program for hardware vendors, model providers, cloud companies, and data center operators. This will give our ecosystem partners a deeper role in integrating with Macs and Mojo, optimizing their platforms, and help shape the future of the Modular Platform. AI is evolving too quickly for every company to keep rebuilding the same infrastructure. Agentic AI is scaling everywhere. Models are growing larger and more complex, and infrastructure is not only becoming disaggregated, it's becoming distributed. We've been saying about that before it was popular. And hardware is obviously becoming more heterogeneous. We have an opportunity to build a common foundation where innovation can compound across the industry. To me, it feels like an Android or Kubernetes moment for AI, or maybe better, an Android and Kubernetes moment together. We've seen before that open horizontal platforms can transform industries, but that only happens when the entire ecosystem comes together. So to everyone developing hardware models, infrastructure, and applications, come build this with us. Together, we can create an AI ecosystem defined not by lock-in, but by choice. And not by the power of any company, but the innovation of an entire industry. As Qualcomm, we never believe it's the job of one company to innovate. It's the job of an ecosystem. We're very happy for this moment, and I think it's an opportunity for all of us. Now let me pass it back to Chris to close us out. Thank you. Thank you so much. Thank you.
Awesome. Thank you, Cristiano. I get to wrap things up now. We've been building Modular for the last 4.5 years into a rapidly changing world with AI. Now, against that backdrop of change, we've been focused on our hypothesis. I believe that leaps are possible when the right team has the right time horizon to do the right fundamental research and development. I found that it can take years to build foundational infrastructure, but if you do it right, you can make a significant contribution. Our approach turned out to be well-placed for the rapid rise of AI coding as well. AI tools are uniquely powerful. We also know that AI enablement is not just a kernel problem, it's a full-stack problem. Modular's approach gives AI the data, the determinism, and those abstractions that it needs to thrive. We're now bringing up new architectures to demo in just weeks and launching them in cloud in just months. But of course, AI is cool, but it's not enough. We are also privileged to work with partners at every level of the stack. And this includes leading hyperscalers and neoclouds, a number of close hardware partners, frontier labs, and many customers. And so I want to thank each and every one of you for your ongoing collaboration. And I want to encourage others to reach out if you see opportunities to create value for the world together. Now, Modular has started a new chapter with Qualcomm, and by now, I hope it's obvious why. We're excited to scale into this opportunity faster than we ever could by ourselves, with a much bigger platform and a network of relationships. And I've always known that we can only be successful if we make a truly open platform. And with Qualcomm, we've found a kindred spirit that believes in a truly heterogeneous data center and a rich edge-to-cloud ecosystem. We might talk about that in a future event. We want to work with everyone in the industry here. So let's build a programmable, unified, and consistent world. One where we can drive more AI applications and more use cases into our daily lives. And through it, let's unlock the power of heterogeneous compute for everyone. Thank you. Before we break, I want to invite Courtney and Deepa up to help tell us what's next. Thank you all.
All right. Well, thank you to Chris, and a huge thank you to all of our keynote speakers. Can we get another round of applause for this group? Good morning again, ModCon. I'm Courtney, and this is Deep, and we'll be your host for the day.
There's a lot to unpack in the keynote. Modular Cloud is now generally available, Mojo 1.0 is here, and now the compiler is open sourced. And we saw Modular vision for the unified AI compute finally come to life. You're going to hear a lot of different conversations today. Cloud, chips, models, capital, and even data centers. But there's a thread connecting all of them together. That is that AI is now becoming more heterogeneous and not less. So the question is, how do we make all those pieces work together?
And we have the rest of the day to find out. For now, you've got 10 minutes to stretch and grab some coffee before the next session, so stay close.
Because when we come back, we'll take a closer look at Modular Cloud with the team that built it. See you soon.
Welcome back. Now you're about to hear from our very own Senior Director of Technology, Shang, and our Senior Product Manager, Jason Wong. This is Modular Cloud, Performance at Scale.
To kick things off, please welcome Jason on stage.
Hi, everyone. Hope everyone had a chance to get some coffee, stretch out, rest your legs a little bit. This is going to be a session for builders. The keynote announced that Modular Cloud is generally available to everyone. This session is going to show you what Modular Cloud actually is, what's under the hood, and how to actually get started. Over the next 45 minutes, we'll go beneath the announcement, what Modular Cloud is, how it's built, what you can deploy today, and how it delivers the performance numbers you saw on stage. Like I mentioned, this is a session for builders. Expect architecture, live product, and real benchmark data. Modular Cloud is the whole stack delivered as our product, not a wrapper around someone else's inference engine. In 2023, we introduced Mojo, the programming foundation for heterogeneous AI. Last ModCon, we introduced Max, the modeling and serving framework built on Mojo, and Modular Cloud is those layers brought together as a managed product. Every endpoint runs the full modular stack, from Mojo kernels to Max serving to Modular Cloud orchestration. Because we own every layer, we can optimize every layer. That vertical integration is where the performance comes from. We've built the hypervisor for compute, heterogeneous hardware abstracted behind one easily accessible interface and API endpoints with the latest frontier open weights models. 20 years ago, virtualization meant developers stopped thinking about physical servers, and we believe that AI infrastructure is at the same inflection point. Like we've mentioned, developers shouldn't have to think about which accelerator their tokens come from. Your application sees one cross-compatible endpoint, supporting the latest frontier models across text, vision, media generation, and more. Underneath the hood, Modular continuously turns heterogeneous compute into tokens. With the Modular Platform being the hypervisor for compute, you don't buy accelerators, you buy tokens, and Modular Cloud automatically matches those instance requests to the most efficient accelerators to deliver the tokens that you need, resulting in cost savings passed down to you. We'll discuss how by controlling every layer, we can deliver optimizations that work together down the stack. What Modular Cloud delivers is the culmination of our stack for inference, blazing fast performance, tuned to your own cost and speed goals, and enterprise-grade reliability in a proven platform. You might be thinking, aren't we announcing Modular Cloud just now? How can we say that it's proven? Our inference platform is already proven in production. Modular Cloud being announced today is a milestone, not a beginning. Modular Cloud is serving billions, trillions of tokens on a regular basis for the most demanding inference customers. So it's not an unproven beta or a new product. We're delivering a battle-tested inference platform with months of real traffic behind the infrastructure. Our real production traffic has 99.8% uptime across that volume, 0.24% response error rate across the billions of tokens daily, even as we're growing quickly, and we are ready for your inference workloads today. Speaking of performance, how do we do? We've mentioned our optimizations across the entire stack. That's backed by independent, rigorous validation. Artificial analysis consistently ranks Modular among the top providers across multiple workloads. Whether it's LLMs, multimodal, or image generation, the independent results match what we see internally. Our goal isn't just meeting the bar in performance, it is achieving the best in-class inference across any generative AI workloads. Independent benchmarks plus real production traffic give you the full picture of what Modular Cloud is capable of. Artificial analysis provides controlled, repeatable benchmarks, not just across text workloads, but across vision and generative media endpoints that are natively supported in the same Modular Cloud stack. On the other hand, OpenRouter provides performance proof points across real developer traffic. Like you've heard in the keynote, we've operated on OpenRouter under the name Model Run. Every endpoint we deployed ranked at or near the top of the platform for latency and throughput. So these aren't just established benchmarks, they are real production traffic from real developers who chose us on performance alone without knowing who we were. Performance results are a huge reason why developers choose Modular Cloud, whether it's throughput, latency, or cost. Modular Cloud delivers best-in-class performance for any generative AI workload. I'll hand it over to Shang, who will pop the hood and walk us through how we've achieved these levels of performance.
Thank you, Jason. So Jason has previously talked about the performance of the endpoints on mCloud as demonstrated through artificial analysis and Open Router. And my name is Sean. I'm the engineering counterpart to Jason. And I'm going to walk you through the inference stack behind the scene that's powering these endpoints and share with you how Modular was able to reach the performance and the token economics that we saw. The central theme today I would like to push through is that inference is truly a full stack problem, from the silicon all the way up to the cloud. Start from the hardware. There is no longer just one hardware that we're optimizing for. We want all of them, and they do not look alike. NVIDIA, AMD, Qualcomm, and all the custom accelerators, they're all different in how the memory is organized, how the work is scheduled, and how the matrix, what the underlying matrix engine wants. It happens not just across vendors. Each of the new generation from the same vendor changes the rules. You get new matrix instructions, you get new memory movements, and new numerics formats. Kernels tuned for the previous generation just doesn't work out of the best performance. At least you leave a lot of performance on the table without changing any code. Model architecture, on the other hand, is pushing this on the other dimension. From the dense to a mixture of experts, new attention variants come out every few months. Each of these changes how the hardware underneath is being asked to do. Then we get to the cloud layer. All of it has to run as a large fleet across multiple different regions with large clusters of accelerators, all held against very tight latency targets, while the hardware underneath and the model on top both keep changing. Some of our friends in the industry has built pretty amazing components around the inference stack. However, many of them build and optimize only the layer that they're specialized in, relying on open source libraries and vendor proprietary software for the rest. For example, a cloud vendor builds the GPU orchestration and rely on the open source engine and kernel implementations. An endpoint vendor provider builds their own inference engine but rely on the open source distributed serving framework. Modular, on the other hand, has full control over every layer of the stack. As a result, each layer is no longer just being opaque to the rest of the layer. It's a black box transparent to the rest of the stack. The benefit of this goes beyond just having expertise to be able to innovate on each of these different layers. What it enables is true end-to-end optimization opportunities that are only available if you control the full stack end-to-end. An example I'd like to walk you through here is disaggregated inference. As we all know, LLM has two distinct phases, prefill and decode, and they work really head-to-head against each other in terms of how they leverage the underlying resources. And they sit on the opposite line of the roof line, opposite side of the roof line. So prefill is compute-bound. It processes the whole prompt and writes the KV cache once, and it involves very few large matrix multiplications. Decode, on the other hand, is bandwidth-bound. It generates one token at a time, rereading the whole KV cache at every step, and it involves smaller operations. Prefill and decode are two distinct challenges. They both each impose different bottlenecks and call for different types of optimization opportunities. The simplistic approach is to serve them together, and then you incur this well-known problem of prefill interference. When this happens, you experience a long pause for your endpoint between token generations. And what makes it worse is that it happens to every user in the same batch. A solution many have adopted is disaggregated inference, serving prefill and decode each of these phases on two separate pools of compute. This adds a little bit complexity, but the effect is that it avoids the prefill interference problem. The interesting part is that delivering disaggregated inference optimization involves changes across all the layers, not just any individual one. We'll need max accelerator libs to offer the kernels written in Mojo specialized for the different compute characteristics of each phase. We'll need max engine to offer the parallelism layout best suited for scheduling workloads on each phase to maximize the hardware utilization. Lastly, we'll need Modular Cloud to dynamically scale the pool of each phase to adapt to the traffic changes that we see in production, routing requests in a prefix-aware fashion, and move KV cache for the best of KV cache hit rate. Starting at the kernel layer. Prefill is compute intensive. It works on large chunks with large matrix multiplications, and the KV cache is computed and written once. You want the prefill kernels to saturate the tensor cores, whatever is equivalent on your hardware target, and you want every streaming multiprocessor to be working on the same chunk. Decode being bandwidth bound, the main work is loading KV cache from the HBM for every sequence in the batch. Sequence length is 1, or in the case of speculative coding, which we employ pretty frequently nowadays, is 1 plus however number of speculative tokens that you have. So the matrix multiply essentially collapse into a matrix vector product. The arithmetic intensity drops orders of magnitude. The compute stays more idle, waiting on memory. So the two really need different kernels with different data layout, different parallelism, and different fusion decisions. In prefill, you decompose across the chunks, and in decode, you decompose across the sequences in the batch. The story is similar on the max layer. Prefill decode call for a different parallelism layout. As we mentioned, prefill being compute bound, it wants the ranks to be working together on the same chunk, and for decode being bandwidth bound, and it wants ranks to be split working on different sequences in the batch. Taking a concrete case, with 8 GPUs on the node, a model like Minimax M3 running long context, multi-turn agentic workload, keep in mind, this is highly dependent. When we optimize for each of these cases, it's highly dependent on the model architecture, hardware, and the workload themselves. For prefill, we take TP8 because we want all 8 ranks to split the work weights and working on the same chunk, which is what's driving down the time to first token. The chunks are large enough to keep every rank busy. Weights loading amortizes over the map malls, so the ranks are doing real compute rather than waiting for memory. For decode, TP8 is the wrong answer because we only have 4 KV heads. Sharding them 8 ways means that we'll load KV cache twice unnecessarily, and we choose TP4 here instead to land exactly on where the number of on the 4 KV heads. Therefore, no KV cache duplication, and we rely on DP, data parallelism, so that we'll be able to split the sequences across 2 replicas and reduce the KV cache reads. With innovations like sparse attention, this could further push towards the DP direction because the indexer has essentially 1, and increasing DP could further reduce the KV cache reads. The complexity here introduces is that prefill decode now shard KV cache asymmetrically. Prefill writes them under one parallelism, and decode reads them under another. Max is a max responsibility to be able to reshard and transfer the cache in between the pools. Lastly, at the cloud layer, disaggregated inference benefits from the ability to dynamically scale each of the pools of prefill and decode to adapt to shifts in workload patterns. Because these workloads are often long context, multi-turn, and agentic, we have an excellent opportunity here for KV caching and prefix-aware routing. Distributed KV cache is an optimization that pushes the KV cache concern from an engine level to a cluster level component, allowing each node in the cluster to asynchronously fetch the KV cache it needs, so that you don't have to, if it's already been computed elsewhere. During scaling, distributed KV cache helps newly scaled up nodes run on warm cache without rerunning the very expensive prefill. With distributed KV, prefix-aware routing also no longer have to trade off between load balancing and cache affinity. Even if we have to pick a less loaded node, so that the node, we don't have to worry about if the node has the KV locally, and we can rely on distributed KV cache to transfer it from another node. And stepping back, disaggregated inference requires collaborations from all the layers. We need phase-specialized kernels. At the kernel layer, we need independent parallelism layout at the KV cache resharding at the engine layer. And we need independent pool scaling and prefix-aware routing at the cloud layer. Most importantly, when you look at these optimizations at each layer do not just simply add up to each other. The effect is truly multiplicative, and the effect is truly compounding. The pattern is not unique to disaggregated inference. The same pattern shows up everywhere once you look at it. Speculative decoding, mixed precision quantization, and multi-tier KV caching all requires inference optimization all requires collaboration across the layers. And some of it are only available if you control the entire inference stack to be able to bring them to life. Lastly, inference is really not a solved problem. New model architectures are evolving very rapidly, and we are working across a very fragmented hardware layer. The work is essentially the cross product of these two dimensions. Thanks to Mojo language providing the abstraction so that the upper layers of the inference stack no longer has to worry about the hardware fragmentation themselves, and having control over each of the layers allow us to fully leverage the agentic skills and harness to more autonomously bring these innovations to life by getting deep into each of these layers without having to treat them as black boxes. How does this matter to you? I want to pass this back to Jason to talk about our benchmark methodology.
Thanks, Sean. Our philosophy at Modular is that performance should be against real production traffic at scale, not just on benchmark leaderboard runs. Don't get me wrong, benchmarks provide strong signals that an inference platform is competitive. But if you're a customer, how do you actually validate that performance in your benchmarks translates to performance in your actual workloads? Real traffic is bursty and mixed, and can be orders of magnitude larger than what's measured in benchmarks. We've built Modular Cloud with the idea that performance against benchmarks also translates over to performance on real customer workloads. Customers today have incredible demands for inference at scale that only continue to grow as the use cases compound. The days of horizontally scaling multiple instances of an inference engine using just the default README instructions, those days are over. In order to achieve the levels of performance that enterprise demands at competitive price points, the inference experience within Modular Cloud is built around being optimized for the use cases that our customers care about. What does this look like? We create real workload profiles based off of real customer needs, ranging from coding auto-completion, agentic use cases, multi-turn chat, structured output, and more. Our team tunes against these workload profiles that are continually informed and improved by allowed, approved customer traffic data. What this means is that as GenAI is used, continues to change and evolve, Modular Cloud is also evolving to stay up to date on performance against what is relevant in the industry. Our performance numbers today, while great, aren't static. They continually improve as our team continues to optimize on every layer of the stack. At a glance, this is what our performance engineers do: build a highly detailed, highly customized configuration sweep across each and every use case, represented by an inference workload. Our team builds deployment profiles, varying parameters like concurrency, topology, and optimizations like which variant of speculative decoding is used. What this results in is a rich array of data points for each use case workload. That allows our team to identify the configurations across the efficient frontier that deliver the best performance. The output, as you can see here, is a Pareto curve of the optimized configurations, not just a single default configuration. Select a point, and you can see and deploy the entire profile behind it. Throughput, cost, time to first token, hardware, and concurrency, all easily visible and available. This is what makes it easy for performance engineers at Modular to deliver the most optimized configurations for the use cases that our customers care about. When you compare elsewhere, what you might see is endless low-level, technical, and hard-to-understand knobs, or you might be dropped into a blank slate deployment that you're not sure is optimized for any one thing in particular. If you contrast this to Modular Cloud, where you can identify your objective, cost, throughput, latency, or any blend of the three, and pick a point in that space that meets your team's goals. Modular Cloud turns a configuration problem into a goal-setting problem. The other dimension of how Modular Cloud accomplishes this is through heterogeneous compute. Whatever the objective, latency, cost, throughput, optimizing across these three objectives, it routes through the same fabric within Modular Cloud. Any request can land on any accelerator, NVIDIA, AMD, Qualcomm, TPU, Trainium, and more. Through heterogeneous compute, Modular Cloud routes each request to the accelerator that's best suited to meet the goals of that team's objective. Modular Cloud's vertical inference stack makes hardware accelerators another variable that we can optimize for, and another tool that we can leverage, not a constraint that our customers inherit. And that's how you break vendor lock-in, just the freedom to focus on meeting your inference goals. Taking another peek under the hood to demonstrate what our performance team sees, each accelerator family has its own measured data points and their own Pareto curve. They interleave. As typically no chip is going to win across the board, this lets Modular Cloud choose the best hardware for your workload. It's the same story of what you saw earlier. Pick a point, see the exact profile configuration and hardware setup, deploy it in seconds. That's how our team at Modular delivers workload-optimized serving in a single screen. And one last thing. We learned that performance is a point in time, a moving goal. Modular Cloud constantly inherits new optimizations from our stack. Faster kernels, support for new accelerators that open up even more dimensions to deliver even better performance. And because we own our entire stack, these improvements compound vertically throughout the stack, but also propagate horizontally across models. So each new model and endpoint that we bring up benefits from all the improvements that we've made on other models. Modular Cloud is a self-improving, forming a flywheel that continually delivers increased performance and passes down those cost savings to customers. All right, now, I've gone on long enough about how epic Modular Cloud is. Now let's take a look and actually see it in action. Modular Cloud has two primary product surfaces: shared endpoints, which are serverless access to frontier open weights models. You pick a model, get a key, pay per token. There's no infrastructure required from you, and tokens start flying in seconds, the absolute fastest way to get started. Dedicated deployments, in contrast, are reserved, isolated capacity for your workloads with guaranteed throughput. It's your choice of models and hardware for our most demanding customers with known service level objectives and enterprise scale. Both are running the same modular stack underneath, guaranteeing the same quality, performance, and reliability. If you're a customer, shared endpoints are a growth path with zero switching costs at every step. You can start on shared endpoints in seconds, and when your traffic justifies reserved capacity, grow out to a dedicated endpoint. Within shared endpoints, try out all of the models that Modular Cloud has to offer in seconds, run your tests and evaluations before scaling up. Dedicated deployments are the customized inference service that scales with you. For enterprises with specific latency and throughput targets, known traffic patterns with a caching target, a dedicated deployment is going to deliver the highest levels of performance in Modular Cloud. The first thing you'll see when entering Modular Cloud is our Model Garden. The Model Garden is our entry portal into everything Modular Cloud offers: frontier open-weight models, serverless, pay-per-token. We show the latest frontier models with options for you to start serving tokens immediately with our shared endpoints or to request a dedicated deployment for the model of your choice. It's a curated catalog of frontier open-weight models ranging from LLMs, vision, multimodal, media generation, you name it. And Modular's day zero support relationships with frontier labs mean that when the newest model releases launch from these labs, they also land on Modular Cloud when they launch, not months later. That also means that every model comes pre-optimized by our team across the different hardware targets, and you'll get our best configuration by default. Now let's take a look at how to get started with shared endpoints on Modular Cloud. Logging in, you're greeted by a Model Garden with models sorted by modality, showing you the ones with live shared endpoints. Opening up the endpoint, you can see how to get started with an API request immediately. This is a curl request or a Python script that can get you started in seconds. The performance and usage tabs show you the usage of that shared endpoint over time, helping you understand the usage of your organization and what the most popular modules are. When you click into the playground, this gives you a no-code way to kick the tires on the model. And once you're happy with what you see, all it takes is generating an API key, and you're off to the races. That Modular Cloud API key is your golden ticket to inference. Whether it's agentic coding, powering your OpenClaw or Hermes agent instance, or generating dozens of media artifacts for your e-commerce website, or anything else you can think of, Modular Cloud powers it all under the hood. Modular Cloud is for builders, and we can't wait to see what you'll build. All right, we've seen how to go from 0 to production quality inference in minutes. It's live today in the console at console.modular.com. Browse the Model Garden, select any model you want, generate an API key, and get started in seconds. Join today, you've seen just how easy it is to get started. Now let's dive a little bit into dedicated deployments. Who's the customer here? You're an enterprise where you're serving billions or trillions of tokens on a daily basis. You know what your latency budget is for engineers or what the end application is. And your CFO is breathing down your neck, looking at the token spend per engineer. If that sounds like you, dedicated deployments on Modular Cloud are exactly what you're looking for. This is where real enterprise production workloads live. Reserved, isolated capacity, predictable latency, guaranteed throughput with no noisy neighbors. Deploy Model Garden models or your own custom Max models. This includes flexible deployment targets and the same API-compatible interface. Moving from shared endpoints to dedicated deployments changes nothing in your end application. Let's take a look at how performance engineers at Modular build out dedicated deployments for our enterprise customers. We don't serve a generic cookie-cutter container. Dedicated deployments in that Modular Cloud are optimized for your specific workloads. Going to this Kimi model, the Pareto chart automatically filters down to show the most efficient configurations. But by unchecking, you can see all the other configuration options our team has explored for this workload. You can set performance targets, like time to first token, and the compatible configurations show up easily. Next, exploring the available configuration options for Minimax, you can see that we have the different data points split up by accelerator, making it easy for users to select the configuration that most closely meets their goals. We are continually working to improve these tools, and so look forward to the self-serve deployment experience in Modular Cloud soon. All right, everything you've seen here in Modular Cloud runs on our compute, but it can also run on your compute. Run Modular Stack inside of your own cloud account. For teams with existing cloud commitments, compliance requirements, or data residency constraints, we offer a bring your own cloud, BYOC, deployment option. Modular deploys and operates dedicated capacity inside your AWS, Google Cloud, or equivalent hyperscaler account. It's your VPC, your data boundaries, and your committed use discount. This is the same console, the same API-compatible endpoints, and the same performance stack. To get started with Modular Cloud in your hyperscaler account, you just talk with anyone from Modular today. We meet enterprises where their infrastructure lives. That means managed multi-tenant cloud today and BYOC dedicated deployments in your own cloud account tomorrow. Performance is going to get enterprises to try Modular Cloud, but we know that operations are what is going to get you to standardize on it. Modular Cloud ships platform capabilities that enterprises expect right out of the box. These are all the enterprise features that you need on day one. We have built Modular Cloud with the needs of enterprise customers in mind to give you the confidence you need to scale to trillions of tokens. Whether it's shared or dedicated endpoints, you can get simple usage-aligned pricing with pay per token, no minimums, and a free tier on our shared endpoints, and by dedicated deployments, capacity-based pricing by hardware and replica count, with different commitment options and different bring-your-own-compute pricing. Getting started with Modular Cloud is simple for both you and your finance team. And we're just getting started here with Modular Cloud. Here's a preview of what's coming next. We have more coming soon with TPUs, Trainium, and Qualcomm A100 coming to production within the next couple months. We're continuously expanding Model Garden with new day zero model releases, and our Modular Cloud delivers self-optimizing infrastructure, continuously re-optimizing deployments across heterogeneous hardware based off of your traffic patterns. Modular Cloud is generally available today at console.modular.com. Deploy open frontier weight models, including Minimax right now, and try our test endpoints. See if you can guess which ones are running on NVIDIA and which ones aren't. We've built the hypervisor for compute. Come build on it. And for a limited time today, we're offering customers who sign up with Modular Cloud $50 in free trial credits.
Thank you, Sean and Jason. We're going to take a moment to get set up for the next panel. And when we return, we're going to shift vantage points completely. We spent the morning talking about building the AI stack. Next, we're going to talk about funding it. You'll hear directly from the people deciding where the infrastructure capital is actually moving next.
We will be right back, so don't go far.
See you soon.
Go.
Oh, you'll go first?
Oh, it's all
It's
good.
okay.
Okay, we'll line
Well,
up.
welcome on stage. All right. Welcome back. Please welcome Sam Fort of DFJ Growth, Quinton Clark of General Catalyst, Dave Munichiello of Google Ventures, Liz Stein of USIT, Michelle Gonzalez of M12, and your moderator, Modular and SVP and GM, Tim Davis.
This is now funding the AI stack. We'll see you soon.
Woohoo. Thank you. So, this is an amazing panel of very notable investors. So we're going to ask all the hard questions. We have a couple of hard questions. I won't introduce everyone. Instead, you can see, hopefully you can see their names and the funds that they're with up on the board. So the whole panel that we have today is really about funding the AI stack. So we've obviously got a lot of questions about infrastructure, how it's getting funded, what VCs are interested in, what they're looking at from growth and other things. So I have a bunch of questions. I'm going to just throw the questions out, and then everyone's going to, we're going to go through each person. We're going to get their perspective on the market. We'll go from there. All right? So the first question, which I'd love all your perspective on, is where is the next wave of AI infrastructure capital flowing? Model training, inference serving, or silicon? How has that shifted in the last 12 months as you've seen it in the market? We'll start there, and then I'll ask a follow-up. So who wants to start? Michelle, would you like to start?
Well, I don't think it's going to be silicon, but for us, I would say we're seeing a lot of companies and founders looking to optimize. So for us, we've been spending a lot of time in the software layer, kernel generation, companies that can do help us with kind of the efficiency and the outcomes from tokens. So I'll say software to start.
Okay, Liz.
All right. Yeah, I think actually what's interesting is less so where the funding is going and more so who has a larger share of leading edge wafer starts.
Okay.
So that's actually what I'm tracking.
Okay, so you're back. So is your answer silicon? Is that what you? And just for folks, Michelle's from M12, which is Microsoft Ventures. Liz is from USIT. So slightly different fund sizes, targeting different parts of the market too. Sam's from DFJ Growth.
Yeah, so context, we're growth investors, so we're a little bit later stage, and I'd say we've really seen a decisive shift towards inference over the past year. I feel like when the new Claude Anthropic models came out in the December, January timeframe, there was a real inflection in the curve of inference taking off, and just in the past month or two with the new OpenAI Soul models, Grok has some great new models, open source has really come onto the scene. Inference hit kind of another kink in the curve. So we're trying to invest now around this notion of inference clouds, software that helps reduce the price of inference, just things that kind of support that ecosystem because we're seeing really explosive growth right now.
Okay, so software is inference software is your bet.
Okay, two for software,
one for silicon, as where we are.
No,
Quinton is from General Catalyst. They are all over the map in terms of, you definitely are from early all the way through to very large.
Full stack. Full stack.
Full stack.
Not all over the map. That sounds bad.
Okay. Well, yeah. Okay. You go. You take it.
Well, the truth is, I think they're all right. I think what we're seeing is we're in the very early innings of AI becoming reality in terms of its impact on potential customers and industries and whatever else. And as a result, you're seeing investment go into everything.
Right.
And I would go even further, which is to say, there's investments happening in energy. There's investments happening, like we're involved in some nuclear projects. We're involved in some land projects, that kind of stuff. Energy, energy, gas, et cetera. Purely because those industries are going to need to keep up to nurse support the silicon, the inference scale, and all that stuff that's also coming. So it really is kind of looking at a whole stack and saying, how at what point is which part of these stacks falling behind, and how do we invest in those things to help shore them up,
and just
be ready.
Quickly on that, are you saying that obviously the investments underneath the silicon, so the power and other things, are much more capital intensive investments? Is that fair statement?
Look, I mean, if you look at nuclear power, if you look at things like turbines, energy, you look at carbon capture, you sort of look peer underneath the powering of GPU itself and say, what is underneath all that? There's a ton of opportunity in those spaces. And the world, we're going to need to keep pace with all that stuff.
Yep. All right, so Dave's from GV. And Dave, what's your perspective?
Yeah, I mean, we've arranged ourselves here in the rounds that we sort of led for Modular, right? So we're very early stage investors, so I may have a contrarian take here. We have 40 AI unicorns in our portfolio, and we invested in 3/4 of them before they were worth $1 billion. So we tend to invest very, very early. And I think my view, so Quinton said everything, and I'll say none of them. And so in a contrarian way, we actually think the infrastructure layer is pretty well baked, partly because of this acquisition. We think that there's sort of CUDA and there's modular that sit out there, and maybe some of the bespoke stacks that are sitting within the hyperscalers. And then beyond that, semis is highly competitive. It's very well funded. We think the exciting chapter right now is applications. So we're looking for people who deeply understand a problem and can take this incredible AI stack that already exists and apply it to that problem.
Yep. It's interesting, no one said training. So we're just not long on training now.
I think with training, it's really consolidated where you have some major clouds like CoreWeave, Nebius that are really supporting that, and the hyperscalers themselves. But as a startup investor, looking for opportunities in training, I think is few and far between.
Yep.
No one also said, and we are investing in actually one of our portfolio companies here, Neurophos, is optical compute. We've invested in a company, NI, which also on the optical networking side. But I think one of the things we want to also see, and whether or not it'll be possible with kind of the kind of concentrated supply chain, is would we build? Yes, we have what we have on the infrastructure today. But if we were from first principles, knowing, kind of now, is that how we would build? And so is there a step change function that could happen with new hardware, new software? And so we're still keeping our eye out for those. Highly risky, but, and again, kind of for the reasons, right? There's the technology risk, but also the customer concentration risk. But that is something we're still looking at as well. I don't know if, Liz, you have?
Yeah, I actually think that there's 4 different ways people are trying to solve the memory wall today. And if you think about it as the leading edge frontier models are about 5 trillion parameters in size, something like that, mixture of experts. And right now, the logic utilization of silicon for inference time compute is below 10%. There is no way that is sustainable. We absolutely know that people are trying to solve this problem from a number of different vectors. Optical, absolutely one of them. That's why I did Celestial back in 2023, because I agree with that point of view that you can do a different type of physics-based modality. There's folks working on interesting things with analog and memory compute and also with stacking memory and logic layers. I think that that's another way to solve it. Another way to solve it is systems architecture level plays. NVIDIA is the original on that, but you see Etched, you see Majestic Labs, you see Positron, all trying to do system architecture level optimizations. And the one that I think nobody is talking about that is the most dangerous, that Modular and Max and Mojo are actually the antidote to, are what the frontier labs are doing. I don't think people are talking anywhere near enough about what OpenAI did with Broadcom on Jalapeno. And the ability to go from knowing everything about your workloads all the way down into the silicon to do the kernel level optimizations. OpenAI did it first, Anthropic went and hired Clive Chan to do it for them. So they're going to do it too. The Kimi K3 team wrote about their kernel optimization in their paper. So you're seeing that level of what I'm calling walled garden oligopolies springing up. Calling it, trying to make walligopoly happen on this channel.
Heard it here first, walligopoly.
But the idea is that if you have this world fast forward in time 5 years, and right now the majority of token volume is going through these frontier labs, right? And if you fast forward in time to that state where everyone has the walled gardens, as an application layer company, you're going to have a bad time. So you want there to be a open-sourced way to have those optimizations happen on a community level, so you as an application layer company don't have to worry about that and bake that into your budget and have it erode your margins, et cetera.
There's an interesting point too, which we obviously bet on around, there's a lot of, in my opinion, a lot of hype on kernel generation. I know some of you are investing in that. It's interesting, having spent a lot of time in that research area, kernel generation is really not enough. You need not only kernel generation, you need serving optimizations, you need cluster level optimizations. We talked about this in the keynote. It's a huge part of the overall stack. So I'm curious, and this is just a slight curveball question. As you think about AI code generation generally, do you believe that, and I know you've placed investments in this, do you believe that kernel generation is enough, or do you think you need a full stack approach? Clearly, if you don't want to answer, no worries, we can go to the next question, but curious.
I think it's very much workload dependent.
Okay.
There are certain workloads where every second of latency absolutely matters. I think RL environments are one of those ones that's very latency dependent because you want to churn out and get the next thing out there. If I'm a frontier lab, I absolutely want to improve my unit economics, and it's almost like being a leading edge semi-fab where I have to put massive billions of dollars into the next frontier model.
Right.
So trying to improve that and also improve my inference margins overall. So I think it's very workload specific on how much you want to optimize the entire system stack.
Okay. Anyone else want to add?
Well, we've seen this movie before.
Okay. Tell us, Quinton.
Well, I mean, if you look at large scale, previous generation, let's ignore AI for a second. Look at the last generation in using CPUs and putting software to work at reasonable scales. It was very convenient to write a lot of Python code or write a lot of TypeScript, that kind of stuff. And then there were parts of the system though that engineers would get into and they'd rewrite in lower level languages. Why did they do that? Partly because they're masochists, but also also because that's the only way for them to get the efficiency and the optimizations out and wring out of the system the very best performance. I was CTO of Dropbox for a couple of years, and they absolutely went very low level into the storage system. They designed memory and designed from memory up and built these fundamental building blocks in the system software is the only way to get the performance out, which gets back to margin and performance. And so we've seen this movie play out a handful of times. I don't think the idea of AI writing or not writing it changes, the plot, so to say.
Yeah, I think from our perspective, this is all important stuff, and some engineers want to go down to the kernel level. But when you think about big opportunities for a venture investor, our view is it's more of the full software stack. There's just not going to be huge companies built around specific kernel optimizations. There's only so many buyers for that. But
so you think it's a feature, not a full.
That's
company?
right. Yeah, that was our bet on modular. We think you guys have this amazing full stack approach. Developers,
Thank you for selling out.
Great investment by Qualcomm, great acquisition. But no, it's more about developers wanting a software suite to develop on. They're not developing for a chip necessarily. They just want really great software that can run their application as efficient as possible.
Okay, I'll change track slightly. So compute and build on what actually Sam you just said. So compute and software consolidated this year. Obviously, Modular being acquired by Qualcomm is one of them. In your opinion, and Michelle, we'll start with you, is vertical integration between chip makers and AI software a sign of the infra layer maturing, or is it happening too early?
I think it's kind of happening at the right time.
Okay.
I'll take that.
Why?
Look, I think as sort of, we're starting to see again kind of where folks like NVIDIA are building out, not, again, just systems, but full, becoming kind of more full stack. You're seeing the neo clouds also, try to, go also, kind of more full stack. You're seeing the labs, right, also going, kind of full stack. And so
walled gardens everywhere.
Walled gardens everywhere, exactly. And so you're seeing the hyperscalers, right? Google, ourselves, we have our own kind of first party, efforts. Maya, Amazon has theirs with Trainium. I think it's kind of logical, maybe, Quinton, to your, we've seen this movie before, that everybody is trying to add as much kind of, value and go and expand from where they are. But
I think that we are in the largest compute crunch of the last 30 plus years, and everyone who is an existing player who already has their leading edge wafer starts is being smart and aggressive about acquisitions in order to take advantage of that very key scarce resource. I think that's probably a lot of the underwrite for what AMD did last week with Talus.
Okay.
Yeah, it's kind of what I said before. I think vertical integration is the right strategy, and to the extent you can provide the software platform with the underlying chips as much as possible, that's what developers want. They just want ease of use. And I think they do want heterogeneity, whether it's a Walligopoly or not. I think they want the ability
to use it.
To move around. So yes, I think we're moving towards more tightly coupled hardware and software, but with the ability to port to different hardware if needed.
Okay. Quinton?
Look, the investment in modular was always about heterogeneity. Right? It was always about giving engineers, developers choice, and providing a platform that allows them to kind of take advantage of the best infrastructure that's out there and sort of drive their own cost performance, optimizations they see fit. And that doesn't change. I think if you sort of look at the development world between the stuff that ends up being very tightly built, very at large scale performance, very deep, et cetera, versus like the large number of applications that'll just be sort of generated and built by people, you need a full stack for all that.
Right.
Because those platforms have to wring out the optimizations at scale, across lots and lots of apps. Whereas if you are down, at the very fine level granularity of optimizations, you're willing to pull on different tools.
Yep.
But that's going to be the minority of the runtime consumption, broadly speaking.
Okay, Dave?
I personally think that the hardware world will never be more simple than it is today. And we're entering into a world that's more complex, more heterogeneity, many different types of models. When we see open source models, we see actually like the explosion of the frontier model as it exists today. Instead, we'll see hundreds or thousands of smaller models that are fine-tuned on company data existing in those companies. And eventually, over time, because of the large taxes that are being taken on sort of model usage, you'll expect companies to own their own hardware. And so there's incentives for people to create their own hardware, at a place like Amazon for Trainium or Google with TPU. You've got many generations of hardware that have come out that just increases complexity. And so what's needed, not hand tuning, not specialization, not bespoke software, but a platform.
Yeah, and I think one of the interesting points there too is, it's interesting that the benchmarks that a heterogeneous setup is actually the fastest token rate. So if you look at Cerebrus today in a mapped setup on any of the benchmarks, it actually has the highest token throughput of any architecture on the market. And so you already know that that's where the world's headed, right? And so I think particularly with long-running agentic workloads, short-running ones, you do have workload-specific optimizations that end up changing the nature of how the optimizations roll. And so as a result, changes the silicon that you need for those.
Yeah, I think the one thing that maybe we're not talking about is like all of us are presupposing that the transformer architecture not only continues to scale, but remains dominant for a while.
Right.
There's rumors out there that someone may or may not have figured out how to do continuous learning. Like there's other things that could happen. I think it is very hard to know the future more than like 3 years out at this point in time.
Or even 12 months out.
Yes.
It's hard to predict.
We moved to 90-day sprints looking at stuff. I love it. Things were changing so fast.
Yes.
Well, I think that's interesting too, because we went through this sort of cycle of early models, then we went through the transformer architecture, then we went really into this generative sort of production, then we went through chain of thought, sort of step function, and now sort of continuous learning is this next step that everyone's waiting for. But you're correct in the sense that we are heavily optimized against the transformer architecture. And so I think it will be interesting if there is a step function change. How does that change the economics? How does that change the tokenomics? Everyone is sort of trying to go further up, to the point on full stack because they want to extract more margin on a token basis. And so I think it'll be interesting how the financing and the economics of that goes in the longer term, in the sense that are we going to continue financing compute through the raw silicon, or do we end up actually trying to finance a token, which I think is an interesting thought experiment. But very quickly, to keep things moving, DeepSeek and a wave of efficient open weight models. Today we talked about Minimax, but there's GLM, there's Kimi, there's many others. Showed that you can get frontier class results for a fraction of the compute. Actually, I just spoke to an entrepreneur out in the demo area, and he was explaining they are spending hundreds of thousands of dollars on OpenAI and Claude as it is right now, just because they're just throwing everything that they can at those models. So given that, how has that changed, do you think, the evaluation of a compute-heavy startup using AI? Do you think that the future is actually going to be a lot more mixture of models? How, are we even in a point yet where that's ready? I'd love your thoughts.
I think it's early, but we as a company and also as a fund do believe that there will be a mixture of models. And more when we talk to founders at the application level, that's what they say they're doing. Now, is it easy today? Is there an easy button? No. And that's why I would say that folks, particularly, kind of for certain tasks are like, no, we'll just always use kind of, Anthropic or OpenAI or, kind of a frontier model. But as I think those things like the harnesses and other things get easier, I think there will be enough of, the performance improvements as well as the incentives to do so, either from a customer, the end user, kind of the customer piece.
There was just before Liz, I jumped to you, there was a funny anecdote in the Valley for a long time in the 2010s. I think it was 70 to 80% of a VC dollar would go to either Meta or Google for ads. Now, do we think that that same thing is true with Anthropic and OpenAI, or do we think that that's actually going to radically shift? Because a huge part of the distribution component of any startup was essentially just through ads for a long time. As you answer it, what would be your perspective on that too? Do you think it's going to shift?
Fair enough. So I think where you sit on the risk maturity curve kind of answers how you're going to be thinking about what models to use. If you are more risk averse, you're probably going to just default to using frontier class everything. If you are someone who needs to cost optimize and willing to take more risk, a lot of the earlier stage startups founders that I talked to, they're like, as soon as GLM 5.2 came out and was pretty good, everyone's like, all right, we're doing that. So there's that piece, and then I think there's another orthogonal layer in terms of importance of your data sovereignty and how you think about that piece of it. So those are sort of and then your ultimate question on like how much are VC dollars subsidizing token burn? What is AI adoption broadly across the enterprise, right? So I think public shareholders everywhere are, and the ultimate long arc of technology is that what we really want to see is technology brings things that used to be the domain of the very rich down and democratizes them for everybody. So I think that's the journey that we're on, and token volume is only going to go up just the way web traffic did.
I'm going to ask you all another question at the end, just for each of your for whatever you can comment on an aggregated basis for your portfolio companies. How true is open models versus full proprietary stack, in the sense of using Claude and OpenAI? Vast majority of what your portfolio companies are telling you, or is it something different? But Sam, keep going on that open weight.
Yeah, maybe it's contrarian, but I am not actually that worried about open models really cannibalizing the frontier models, and you're seeing that play out. Like we're investors in OpenAI. We've been investors for almost 4 years now, and they grew revenue. They've reported this 20% month over month in July when their new models came out, despite Kimi and GLM and DeepSeek, all these innovations happening on open source. So turns out, with these open source models, you still got to run on hardware. It still costs real money, and no one is more of an expert in bringing down the cost of inference and training than the OpenAIs and Anthropics. I mean, they're dedicating huge teams to making this as low as possible. So they're generating growth. They're competitive with these open source models, with their low-end models like the Luna model from OpenAI. They decreased price by 80% a few weeks ago, but increased token volume by 5x, more than 5x. Jevons paradox at work, taking share from a lot of the open models. So, despite all the noise around cost pressures, you're not seeing that play out. And the margins, Anthropic and OpenAI are generating are still very strong. So I think open models have a place, but to Liz's point, I think it's more about the customization, the data sovereignty, like bringing them in-house. That is a valid point, and that's not something you get through a cloud-based open frontier model. But I think they both have a good place in the world, and they're both going to continue growing.
So your bet is power law, distributions are true, all the tokens are going to flow to a small number of companies outside of the optimizations that enterprises make on their own data.
That's probably right, yes.
Okay,
all right. It's still going to be heterogeneous. We're still going to need modular. We're still going to need lots of chips, but
and we're still very early, so there's that point too, obviously. Quinton, what's your take?
What Sam said about OpenAI and even while there's adoption of open source, like the OpenAI's value of its frontier models continues to endure and the business continues to grow. We're longtime investors and big investors in Anthropic, and we have the same mindset. It's like we're very bullish on that investment because we think the demand, and we're so early in the diffusion of AI that we don't think anything I'm about to say about open source as an impact on Anthropic's opportunity. I do think there'll be a lot more consumption of open source. If you sort of think about what's really at stake here, it's in any application that's built, any enterprise that's running, anything that you're applying AI to, there's this spectrum now of the very frontier edge model capability and things that are pre-solved. You want to parse my email and tell me whether or not there's something actionable in it. You do not need to hire Mythos 22 to answer that question, nor should you. In the same way, you wouldn't necessarily hire, a 20-year, physics PhD, nuclear fission researcher to like schedule a meeting for you, right? So there is this like idea that we're going to apply different models across the spectrum of tasks, and we have yet to sort that out. And I think as that happens, we will see much more adoption of open source, including creating these fine-tuned models that are inside an enterprise scenario, the situation exactly as Dave was talking about. I think you'll see so many models that are being built or tuned or shaped that way. And so I think we're not even taking one step down that road. I know a public company, $10 billion in revenue. They're going to spend, guess how much in inference this year to the frontier model companies? Not just one, but a few of them. Guess.
$5 million.
$400 million.
That's an order of magnitude.
is their total, that's their run rate bill if they did nothing, right? And they told me this around like May, I think it was.
Okay.
And that's kind of what they're on track for. Because they let every knowledge worker using the tools and every software engineer using the tools, basically pick the most frontier model, turn it like, do I want the dumb mode or do I want the smart mode? Well, obviously I want the smart mode. My work is important.
Right.
And so that's kind of what you get, right? So we're kind of at the very beginning of people understanding what to do with AI, much less like how to operate it correctly.
I have a great question on this, but Dave, you go.
The scaling laws tell us that we can get 90% of the performance of the frontier at 10% of the cost.
Right.
And so open source models will be that 90% of the frontier. The frontier currently is at, say, 180 IQ. When that frontier gets out to 250 to 300, will humans really be able to tell the difference between the frontier and the open source?
Right.
I think the answer is no. I think that will explode open source for most use cases. I think frontier stays relevant for science. You'll see a lot of amazing researchers that are leaving the frontier to go work on science. Like they're going to go write the next math papers and physics papers that change our planet, and that's going to be really exciting. But do you need the frontier for things other than cybersecurity and science? I don't know.
Yeah, and the frontier model companies themselves, they will ride that curve. And this is why OpenAI, for example, on the pricing, whatever else.
How much do you think, though, that a general user of AI today understands, like psychologically, it's interesting when you talk to folk, no one wants to use the dumbest model, irrespective, right? Like, I'm going to write an email. I need the best per unit of intelligence on that email. Every token that's spat out needs to be perfect, even if the statement is only a couple of lines, right? So do you agree that, or I'd love your perspective, it feels like the industry still has a long way to go on helping educate people. And we've even had this issue with even model naming.
Why,
right?
why give
no
them
one
the
understands
choice?
the difference between all of the different GPP
Why
models.
have the dial in the consumer tools at all?
Yeah.
Well, I think the interesting thing is how much economic extraction you get from the ability for the average user not to actually understand how much intelligence is needed from the model to execute a task, right? Like, I agree with you generally. The idea that like writing an email should be cheap and advanced research scientists should be expensive. The problem is, the psychology today is no one wants to go in and be like, oh yeah, I wrote this email with the dumbest model. Like, no one is going to say that, ever. So I'm just interested, how do you think about that?
It's also, because I think giving kind of choice, right? I think the end user, for the most part, doesn't, quite understand. But also, you're not exposed to the cost, right? So you're not saying, this email is going to cost $50, or this email is going to cost $1. Like, what, know, and it has to come out of your OpEx budget, which, again, that's where, when you were speaking, Quinton, I was thinking, the CFO comes in, right? When those line items start, and then they start asking questions around, do we need the Ferrari all the time, right? Or what are things, guardrails and things should we put kind of in place? So,
yeah, I think there's probably a spectrum of like how risky it is to not use the frontier.
Sure.
So if I'm working on like a high IQ output task, I'm definitely going to default. But like, you ask me in my personal life, I definitely use Sonnet to optimize my baby's introduction to solid foods planning.
Sure.
Like, I'm not going to use Mythos to like optimize that. So I think like there's probably for each engineer out there some level of intellectual honesty on what's my risk reward on this task, and just responsible AI use.
Yeah, I think there's a lot of, surprising to me, price elasticity to pay egregious amounts for the very highest level of intelligence. But I think there's been a movement over the past just a few months to rein in that spend and realize, hey, one level down actually is good enough. And folks are now moving into more routing technology, like a router, to help them make the decision of what model is appropriate for the right task. And that's bringing budgets a little bit more under control. But right now, there's a huge premium for the most intelligent model.
Okay. Dave, did you want anything?
I mean, this is just a capitalism feedback loop, right? Like, we don't hire a physics PhD to greet people at the door of your offices. And so I think that model will play out over time. We'll find the right places to put the really expensive humans, the really expensive models, the really expensive resources, and the right places to put the right-sized resources.
Okay, great. Now, I'm going to ask one last question because we're running up on time. If there's a bunch of entrepreneurs here, lots of people looking at AI infrastructure, betting on the next wave, as you think about your fund, as you think where you're investing, what do you want to tell the audience, the folks on the live stream? What are the areas that you're looking at that are most interesting to you? What should people be building? Go. And everyone can go down, and then we'll wrap it with that.
I know, with 50 seconds left. Local AI. Anyone?
Local AI.
Yeah, if you're building and Windows developers, come talk to me.
Yeah, we're actually back up at the 10,000-foot level. So for us, we did a bunch of early bets in AI infrastructure, which have played out very well for us. So now we are kind of rewinding up and saying, all right, where are the next interesting things in the application layer and in orthogonal domains? So that's actually where we're spending a lot of our time.
Great.
I'll give two, because I already talked about how inference is so important to us. So anything primarily software-driven that can help drive the inference costs down closer to the cost of energy, because that's where it's going to asymptote, we're excited about that. That was the bet on modular, and I think there's going to be a lot of others. But the other one that's interesting for us is robotics. We think there will be more of a ChatGPT moment for robotics in the near term, and so we're looking at new models to address more physical world AI, form factors that are interesting, data acquisition technologies, because data is so important for that modality. So yeah, robotics is exciting.
Okay, amazing.
Yeah, the robotics one I completely agree with. I think once we hit generalization moment in world models, we're going to see a massive change there. And I'll go as far as to say, I think at the end of that journey, you're going to see more inference on world models than you are on language models.
Yes.
I think that's coming. So that's kind of one. The other one I would say is I'm very curious about how enterprises, how businesses are going to codify their knowledge.
Okay.
And so they're going to put to work many different models. Some of them are going to be very bespoke. Some of them are off the shelf. But how do they go about doing that?
Right. Yep. Dave?
For us, it's AI for science, AI applications, and then I think robotics is interesting. I don't know if I agree about the ChatGPT moment. I worked in robotics before investing, so I'm a skeptic.
But
I think it's going to be really hard, but eventually it feels inevitable that maybe it's 15 or 20 years, not 8 years.
Okay.
There'll be some more robots.
Amazing. All right, we're at time. Thank our panel very much. And we'll move on. Thank you very much.
Get it.
All right.
Thank you to our panel. This was a fascinating look at where infrastructure capital is moving, how investors are thinking about this generation of AI companies, and what increasingly capable and increasingly efficient models mean for the economies of entire stack.
And that brings us to the halfway point. We've been together since 9, and it's already been quite the morning. Modular Cloud going GA, Mojo going open source, and now a funding panel that just told you where the money actually goes.
This morning was largely about the software layer and what it takes to scale it. This afternoon, we're going to go underneath it, into silicon, benchmarks, frontier models, infrastructure, and eventually the power required to run it all.
Before you go, lunch is going to be served upstairs on the theater level where you saw the registration desks this morning. The demo stations are staffed by the teams who built what you saw earlier. You can see Mojo, Max, Modular Cloud in action with demos running in the lobby right now.
And this afternoon, we're going to be running 2 stages with even more technical content. The conference theater upstairs is our technical track, with sessions on inference stack internals, Mojo 1.0, and a live robot demo. How exciting. The full schedule is in the app, and sessions on both stages are being recorded and will be available after the event. Now please head out, grab some lunch, explore the demos, and recharge. The program will begin back at 1:30, so please be sure to be here by then. And then we'll turn our attention to the hardware powering the next generation of AI.
We'll see you then.
Yeah, thank you.
Welcome back, ModCon. We spent this morning looking at what's changing in the AI software stack. This afternoon, we're going underneath it.
And we're going all the way to the silicon. Because every model, every cloud service, and every breakthrough we have talked about today eventually has to run somewhere. And the future of AI won't just run on one kind of hardware.
So we're starting the afternoon with 3 very different vantage points on designing compute for the workloads of today and the future.
Please welcome Satyam Shervasa, VP of Software Engineering at D-Matrix, Rasheed Datar, SVP of Cloud Computing at Qualcomm, and Comran, Head of Business Development at GTM at AWS. Moderating the conversation is Chris Lattner, who built the software stack to unify it all.
Please welcome our AI hardware panel.
Hello. All right, we're going to talk about the future of hardware. That's exciting. There's a lot going on and tons of different aspects and things that we can play off on this. To just break the ice a little bit, I'd love to find out, as AI is becoming more disaggregated, heterogeneous, all the things that are going on, each of you has a different take. You work for different groups with different companies, different ideas. What is the big idea? What do you think is makes your approach cool? What do you want to see more in the world? Satyam, do you want to take it first?
Yeah, at D-Matrix, we've looked at the problem of AI computing from the first principle, looking at the demands of the workload, how they compare and contrast and evolve over time. And as a part of the solution, we have looked into architectural approaches that rely on in-memory computing, large SRAM capacity, all while maintaining interoperability with different devices and reaffirming our commitment to programmability. So that's why our products are perhaps the best in class as far as the latency and throughput is concerned, without relying on anything proprietary. And that's why we are able to interface with GPUs. That's why we are able to interface with Mojo. And hopefully that's something that we can build upon.
Yeah, that's great. I think that you also have ideas about memory as well, Rasheed?
Yes, so our approach is very much memory-centric. We've looked at these models. Inference is not compute-bound in many cases. It's memory-bound. You're bringing in a little bit of data, you're doing a little bit of compute, and then you're repeating that. So we see that data movement is becoming a challenge. The industry's classic approach is make the pipe fatter and faster. But the challenge is it goes after the exact 2 currencies that are in short supply: advanced packaging and power. So we're introducing what we call high bandwidth computing. We're fundamentally changing that paradigm where you take the compute to where the model is. Significantly reduce the data movement, gives you a significant advantage on power, allows you to use simpler packaging technologies. And right from the beginning, our approach was to bet on, our North Star is perf per watt, perf per dollar. So we bet on a commodity memory, so the LPDDR memory in this case. When you combine the two, high memory density and high memory bandwidth, fundamentally how you approach the problem changes. It can have a significant improvement on costs, on power savings, and so on. And that, interestingly, then allows you to think differently about how you approach the problem. We are most excited by, as we introduce this to the market and it becomes more mainstream, how models will change and evolve to take advantage of that. So that's exciting. And for us, the approach we're taking through all of this is to build a solution that's designed to be disaggregated. And that's where the right software stack, the ability to mix and match, becomes super critical. And that's another very exciting direction the industry is going in.
You might say the hardware needs to be modular.
Yes.
Comran, you're not just building AI chips, you're building a lot of things.
We're building a lot of things, and I think I want to echo a lot of everything that's kind of being said here, right? So at Amazon, we've been working on building these purpose-built chips for some time now. We're on our 4th generation processor with Trainium 3. It's intentionally designed to solve all of these latest challenges for frontier models to deliver better performance and lower cost. But the thought process on like, hey, where is this going? How is disaggregating going to play in? I think we're going towards a very disaggregated footprint here and a heterogeneous footprint as well. I think the days where you would have a single purpose like accelerator that can solve all of your problems, that's the old world, the new world we're kind of moving towards as well. The diversity of applications, especially in AI and how it's being applied to different modalities, different applications, is going to require us to get very particular on how we're applying that to our chips, which chips are the best for that, and how do these chips work interoperability across the heterogeneous fleet that we have. And so, with Trainium, it's going to be great for, these types of workloads where we can segregate out from LLMs, especially we can have, chips for pre-fill state of that application. We can then have decode chips as well. We can, on the fly, allocate those resources back and forth depending on the workloads that we're doing. And as we move into more applications, that's an area where then mixing and matching the different workloads to the right chipset, using them heterogeneously and to be able to scale on the fly.
Well, and I think the AWS, you've also announced a deal with Cerebras as well.
Yeah.
So you're really leaning into diverse silicon.
Yeah, that's exactly right? So that was kind of earlier this year, we announced a partnership with Cerebras as well. They have chips that are specialized in decode parts of the application. We could use Trainium as part of that pre-fill state and then use them heterogeneously as well, and then kind of modulate the resource count between the pre-fill state if it's a pre-fill dominant workload, or then transition over to more Cerebras chips if it's going to be a more decode dominant workload.
I absolutely plus one that. I think we're going to see more of this. I think we're going to see more specialization, and I think that particularly as AI continues to grow up, it's still pretty immature, we're going to see more specialized and differentiated workloads. And from that, there's going to be a lot of room for silicon to grow into this. So each of you has been building into established ecosystems, right? We have tons of models. There's a lot of momentum behind the software ecosystem. But what are the challenges that you're seeing, both in terms of software and the standards there, hardware and the standards in interconnects, and kind of how do you think about that? Maybe Rasheed, you can take this one first.
So there's a set of things that are getting easier. So we are today able to take models out of Hugging Face and with relative ease onboard them. The standards are evolving. So Ethernet-based Rocky V2 for data transfers. OCP is standardizing racks. So some of that's happening, and that's helping. The newer things that are happening as well, right? For example, kernels with tools like Mojo are becoming portable. There's a set of things that simply were not true a couple years ago that's starting to happen. So that's making life easier and positive. The challenges we see is our approach, which brings in the performance per watt advantage and other things. It is NPU-based. It's not a GPU. The world is sort of been, AI world so far has been built around GPUs. So one immediate thing we see is getting tooling that will work across a broader diversity of hardware is going to be a massive help for us. So that's something we're looking forward to. Similarly, the getting a model to work is not that hard today. There's lots of tools and stuff that exist. Getting it to get to perform quickly. So even there, getting better tooling, better compilers, other solutions that will increase the velocity, that's another thing that's a challenge that we are looking in various ways. Max is a answer to solve these. And then the other areas we struggle with sometimes is we need to adjust the culture, right? There's a lot of benchmark culture, whereas the real world is, how does it run reliably on a cloud, multi-tenancy, different users, the tail problem, if you will. We need to work together to get the community and industry to accept that as opposed to just the benchmarks.
Well, indeed, in our keynote, we have a whole bunch of smart engineers at Modular, of course. And they want to have amazing benchmarks and make all these claims, but the problem is that nobody really believes benchmarks. Right, and that's why the customer is actually the thing you need to work backwards from so much. But Comran?
No, I love that answer because it's like we work with our customers, and at Amazon, it's one of the leadership principles, customer obsession, right? Let's work backwards from our customer's problem and deliver the experiences and to the success criteria that they're looking for. And that is probably one of the commonalities I see all the time. It's like, well, we have all these, like back in the day, aging myself a little bit, MLPerf was probably the gold standard, right? Now we have Inference Max, we have, artificial analysis, many others. But when you try to win the benchmarking war, you're going to lose your customer's velocity to execute. And so co-signing a lot of what you were just talking about, how do we get high performance, how do we make high performance ML teams be able to execute well, be able to lower their time to market or reduce the time to market, and to do so at lower cost as well, and to make it easier for them to do this. So, we're investing in these tool chains across hardware and software. I think that's one of the unique vantage points that we have is we're able to innovate at the chip level, at the server level. We're able to innovate at the data center level and how it's distributed as well. And then working through open source library stacks as well. And that's one of the exciting parts that we have with our partners with like Modular as well, is we can then meet developers where they are. If you're most comfortable being able to develop your kernels in our framework, which is called Nikki, or you're most comfortable in a Mojo-like environment, great. Please bring that, execute well on these chips, execute across a heterogeneous fleet as well.
Yeah, makes sense. Satyam, what are you saying? I know that you integrate with other people's systems also.
We do. One of the things that has happened in the last 3 or 4 years is there is a bigger appetite among the customers, among the developers, to try on different hardware. They are no longer reluctant to look at something which doesn't look like a GPU.
Yeah.
This was not the case a few years ago.
Yeah, this is new.
Yeah. Yes. And some of the more experienced Ninja-level developers and some of the larger frontier labs, they're even willing to go down to the assembly level to program and eke out the last bit of performance, which is a good thing for some of the newer hardware vendors like us. I partly disagree with one of the statements that there is already a framework or there is already infrastructure for heterogeneous computing. It's just arriving. Vast majority of infrastructure today is still proprietary. Much of it is closed source. So as a hardware vendor, in order for us to get the real benefit of the chips, for example, if you have a distributed multi-SRAM or die-stacked DRAM-based architecture, you have to go away from the notion of a tensor being allocated in a unified memory. None of the frameworks do that.
That's right.
And it's going to be a lift for us working with partners to educate the industry that that is needed for us to really realize the benefit of a distributed memory architecture.
Yeah.
So there is work to be done there.
Yeah, I mean, tensors are naturally spatializable, right? And so a lot of people haven't thought about it that way. When I reflect back, a lot of the MLIR journey was about saying, if we can invest a lot in one layer of the stack and then reuse it, then we can invest in great tools. And I think we have the same opportunity here, where when building an AI stack for a chip, often you don't have the opportunity or the bandwidth to invest in nice-to-have components. And so this is where I think working together is such a great opportunity. Well, so now, again, we're in this crazy AI world, and the model architectures keep shifting, right? And so MOEs are the cool thing today, but we now have longer context, we have multimodal and video, we have diffusion models, we have agentic use cases that change the workload quite a lot. How do you decide what to put into silicon? I mean, I'm merely a software guy, and so I think about like rearranging the zeros and ones, but you have to actually plan ahead. How do you do that? How do you think about that? How do you feed into that? Comran?
So first and foremost, I think it's incredibly hard to predict the future, right? Many moons ago, when AlexNets and CNNs were the kind of prevailing opinion and state of the art, and then NLPs kind of took over, and we're in this ChatGPT era right now, where that's really taking our understanding and the use cases to this level. And we're kind of on this precipice as well as like, hey, the application of AI is going to change dramatically. So it's very hard to predict, and I think that getting it right is incredibly challenging. One of the ways we like to approach that problem is working backwards from customers. We like to form very deep partnerships with our partners, with our customers, to really go deep on understanding how they're thinking about these problems, how they're inventing these problems. Or sorry, how they're looking at solutions, inventing the solutions to their problems. What we like to do as well is kind of take what we've learned up until this point and kind of apply it into the future and work with research. What we like to do as well is kind of take what we've learned up until this point and kind of apply it into the future and work with researchers in our, we have part of our efforts as well as working deeply with academic research teams to kind of try to look forward in time as well as like, well, where are the model architectures going? What are the types of problems they're looking at as well? Work with our frontier lab partners that are already investing or kind of building out the future for world models or for physical AI, which I think personally are going to be two modalities that are going to be really big this year.
Yeah, I mean, it's helpful to have people pulling you along.
Yeah, right? And we co-develop those solutions with them. It's like, well, what are the right things that you would need in our silicon, in our server, in our design? What is the right software to make that, from a dream to reality? How are you going to make super exciting experiences for your customers as well? So we like to work backwards from that. We like to work with our research community as well, and we love to work with our partners to gain all of these insights and make it easy for our developers.
Yeah, makes sense. Satyam, how do you all think about this?
Yeah, I think great points by Comran. A couple of things that I would add is it takes a bit of a foresight as architects to look into the signals coming from the research community and identify which ones of those are relevant and which ones we should kind of see as transient. For example, for us, when we started out building the Coursera architecture many years ago, people were still building for CNNs.
Yep.
So we built an LLM accelerator long before ChatGPT was a thing. We adopted block floating point before MX format was standardized. So it turned out those were...
And if you go back, how did you know? How did you think about that? How did you decide? What informed that decision?
It was a conscious choice to try to trade off, for example, the floating point formats. If you go with a standard floating point, IEEE compliant or an FP16, it's going to not give us the kind of...
Back then, BFlow16 was cool. So,
it was, yes. And it was a big debate internally in the company, should we go that route? But then how do you differentiate? So for us, having a shared exponent-based integer computing was the key. This is where we can get the accuracy and also get the energy efficiency of computing without trading off anywhere. It turned out those were the right bets. Hopefully, there will be many more that we can keep incorporating into our architecture. The second part, though, which is more important, is we don't compromise on programmability. You can take the same accelerator today and run CNNs on it. You can run a state space model on it. Because we didn't take shortcuts, and I hope many of the other accelerators do the same thing. Instead of carving things out down to the silicon, putting a hard-coded model, we enable developers to program the accelerator the way they feel comfortable. That's, I think, is a key to longevity.
Well, and just speaking for myself as a software guy, it's so easy for hardware to specialize, right? And make all the units bigger, just specialize on today's workload. But then if you lose programmability, you can't navigate. And so it's
I think the key to NVIDIA's longevity is CUDA. There's no debate about that.
Yeah. I mean, I think despite all the challenges we have with CUDA, we owe a lot to CUDA, right? I mean, I think it pushed the world forward, and I think that I really credit CUDA with the AlexNet moment, right? And so a lot of what AlexNet was this confluence of algorithms, data, and compute. And if they had not been able to code some new convolution kernels, right, then it probably never would have happened, or maybe it would have been delayed. So
and that's the difficult part, balancing that programmability versus the specialization in chip.
That's right. That's right. And there is no one right answer, right? This is all just you have to make a bet.
Yeah, so I agree with all the points made. The way we've approached it is a little bit of first principles. So we know that if we can do something to significantly cut the power consumption, that's always usually is a very good trade-off, almost always. Reduce data movement. So we focus on these things which are first principles going to be true. Then you look at what are the things that are, there are things closer to hardware that you need to have to ultimately get to a really good solution. So getting the data formats right is a very important thing. So there sometimes maybe the bet is support more data formats than you're ideally wanting to, so you do that. Then there'll be certain functions that you boil down to primitives like a softmax, that class of functions, you put that in hardware and get it right. Everything else, you try and leave it flexible for software to manage and handle, if you will, the different layers and such. So that's sort of the first order guide we take, in addition to the other points mentioned here. One of the things we've gotten a little bit lucky with is, because of the NPU architecture that we apply across our product portfolio, we get a tremendous amount of input from various use cases. There will be mobile use cases, automotive use cases, IoT, data center. That, in a way, has helped us make this much more programmable, robust.
Forces generalization.
For generalization. So then it becomes a relatively simple choice. Okay, these things are super clear, they should be in hardware. Keep as much of the flexibility in software as possible. And then keep working on better and better tooling to allow you to take advantage of that. And to the point mentioned, you don't want to end up with hardware that is either harder to program or is bespoke. So we've always been evolving, right? So yes, we all started with CNNs, transformers, diffusion models, and we'll see where things go. Diffusion may become important in large language models. So we need to think this through, and we get a lot of customer feedback. And then, yes, it's a very important call to make. What research signals to pay attention to, and which ones to say, well, I'm not sure. But you do the best. Sometimes you get lucky. But I think having the more flexibility in software goes a very long way.
Yeah, I mean, I look at the graveyard full of CNN accelerators, right? When the transformer came on the scene, you can see the risks of overspecialization. It's also interesting to me as a hardware nerd, not an expert, but it seems like combinational logic on the new process nodes is basically free. And so it seems like there is a lot of optionality. There's a lot of dead silicon that you can't even power on because you can't dissipate enough from the silicon. And so it seems like we should have a lot more of that flexibility and that optionality built in. And that's really cool. So, hey, I hear that CPUs are cool again.
Were they not cool?
I have always thought CPUs were cool. And we went through a moment in the industry where the only thing people could spell with 3 letters started with a G.
Yeah.
But how do you expect that to evolve? And what do you think will happen with agentic programming, this whole hybrid compute? What do you expect architecture to evolve into? Do you think everything, I certainly don't think everything becomes a CPU. I think we all agree now it doesn't become completely specialized, but like, how do you think this works out and what happens here? I think we're on Comran.
Oh, we're on me now? Okay, sorry. I think it's going to be super critical as we're moving forward, right? Like as we're looking at a lot of the agentic workflows that are taking over, you notice that more of the data loops and CPU in the loop of these actual processing is becoming more of the bottleneck than the amount of time spent on processing the model itself. All of the reasoning loops, all of the guard loops that are happening as well. So I think the mix between CPUs and the AI chips are going to be super important. I think this is one area where our other chip line, Graviton, is going to also pay dividends as well. One of the things that we've been working on as well is bringing a better relationship and a closer relationship between our Graviton processors and our AI chips, Trainium. And so in our latest gen now that we just launched this year, or at the reInvent last year, which is Trainium 3 server, or our second gen Ultra servers with Trainium 3 include Graviton processors. And one of the things that we fundamentally changed in our architecture to kind of address these concerns of how do you use more CPUs, how do you offload better, how do you create a tighter coupling between your chip and your CPU tasks, is we changed the ratio of number of CPUs, in our case Graviton, which is an ARM-based processor, to the number of AI chips. And so we have 1 Graviton processor per 4 Trainium chips, and that gives you a very tight coupling between all of the aspects that you need. I think as we move forward, we're going to see more of these different types of chips that are specialized for different types of workloads, with the tighter coupling between their general purpose CPU type operations, whether that's going to be on a Graviton-like processor, an ARM-like processor, or a different type of embedded or CPU, and specialized chips that will be able to kind of operate very well for the entire inference or training pipeline or just parts of that pipeline.
Makes sense. Satyam, what's your take?
Great points. I think
you're closely coupled. So.
I am. And as an ex-Intel person, CPUs are always cool.
Yeah.
The nature of applications is evolving, going from large monolithic models to a mix of models to function calls to web searches, database lookups. There has to be optimization done at multiple levels of the stack.
So just write it all in Python and you're good?
Yeah. That's a good starting place. We look at it from the efficiency of LLM execution, for example. And we have gone out of the way to remove every little source of latency along the way. So decoupled execution, no interaction with the host, managing all the communications on device, all of that. But that's only a piece of the whole picture. The optimizations at other places include how quickly can data move between different class of devices. When a result is available on an accelerator, how quickly can the application processor access it? So it all comes down to the whole theme around heterogeneity. Now we're looking at it from not just accelerator to accelerator, but general purpose application processors to accelerators as well. So a framework that allows developers and application builders the ability to mix and move things around and have seamless communication between the devices is really what is needed.
Yeah, makes sense. Rasheed?
So CPUs are really cool, and we are building one of the coolest ones. we announced it a couple months ago. It's called C1000. Obviously, for agentic AI, for orchestration tasks, pre-processing, and so on, the GPUs or NPUs are going to do the thing they're good at. CPUs do the things they're good at. We're also very heavily focused on solving.
Let's just acknowledge we're all different and we're good at different things, and that's actually better for the world.
Right.
Yes.
One of the other things we're looking at is, since heavily focused on the memory-centric approach, we're looking at building, also announced this earlier, bringing HPC and attaching that to our CPUs. So it can solve a very specific set of problems. You have workloads that need super low latency, are memory bandwidth bound. You couple these things together and you get something even better. And again, that would be a solution for a class of workloads.
Yeah, makes sense. One of the things I've seen time and time again across a bunch of different systems is that the accelerators keep getting faster, right? And so as the accelerators keep getting faster, you keep getting bottlenecked on the host.
Right.
And one of the other contrary bets that Modular made years ago is on asynchrony. Because the nature of computers is we send messages between each other, no matter whether you're talking about two different computers in the Ethernet or two different IPs in the same SoC. And so this is something that, again, I think that as you build these things out and you start thinking about a rack or a whole system, everything's distributed, which is a key part of how all this stuff has to work.
And that's likely the next class of problems industry is going to, they're already dealing with it. You solve for compute, you solve the GPUs, you solve for memory constraint, memory bandwidths. Interconnect becomes the next big class of problems. And then within that, there is even compute happening within the interconnects.
Do you want to talk about interconnect? I mean, I hear scale up is a huge thing. Do you have opinions or thoughts on where this goes?
Sure. So we're building these AI racks. As you put these racks together, you have to make sure that all the pieces of compute really work as one unit. So there's a laser focus on ironing out the latencies of one NPU sending data to another NPU.
I just plug in Ethernet jack ports, right? And it seems pretty straightforward. Why is it that hard?
Getting the latencies right, treating them as one unit to work together, getting the power consumption right, and then the ability to program all of it as if it's one unit. So that's the class of problems, which is where complex compilers, kernel writing tools, all of this comes to bear. The world is going from you did stuff on a CPU, you hand it off to a GPU, you use some interconnect to get the data through, to all these three pieces are really, from a programmer standpoint, are one unit. So from a hardware standpoint, you want to make them look and feel like one.
Yeah. Well, and then you bring in security and software-defined networking,
and it gets so much more complex as well. And I think that the scale-up problem is a very unique problem that we're now really entering the game of, right? So we're seeing these applications with our customers as well, where maybe a few years ago, scale-up was what? 100 chips, 1,000 chips at most, right? And I was like, yeah, I'm deploying at scale. And the volume that we're seeing today, especially with the large frontier labs, is no, I want hundreds of thousands of chips. I want 1 million chips, right? So last year, 2 years ago, we announced this program with Anthropic, where we wanted to help them build their largest compute cluster ever called Project Rainier. At the time, we didn't fully announce how big of a cluster that was. At the end of last year, we announced at reInvent, so it was 1 million chips in Project Rainier. When you're driving that level of scale, all of these problems we're describing are just amplified by that level of scale. Security, reliability, resiliency, how do you orchestrate amongst all of these chips? It becomes kind of like an exponential problem. Where,
and particularly as you get away from a single node, all the abstractions, all the software, all the learning, and all the thought process either doesn't exist or goes back to HPC. Right?
Exactly.
AI folks are just still rediscovering all these.
You could be looking at your micro benchmarks and being like, hey, I can get 90% MFU, 80% MFU. My MBUs are fantastic. I'm highly efficiently utilizing my memory bandwidth and my compute bandwidth in my single node. And then you scale to 1,000, you scale to 10,000, you scale to 100,000, and now your charts look radically different. So how do you keep high efficiency across this? Interconnectivity is going to be critical to that. One of the ways that, and there's many solutions to this, but one of the ways that Amazon has been, or we've been doing this, is looking at how do we scale these, how do we build, when we think about our chip design in Trainium 3, when they were thinking about the chip design, they thought about, well, how much compute per chip, how much compute per server, how do we scale that? And so one of the things we went from our Trainium 2 design to our Trainium 3 is we went to a total ultra server design of 64 chips working in concert to 144 chips in working in concert, and then we can scale through EFA, which is our networking bandwidth. But that allowed us to do, if I have 100+ billion parameter MOEs, if I have a trillion parameter MOE model, and I need to utilize 144 chips, I could do that with as few hops as possible to do my all gathers and all reduces. I could do that at extremely high bandwidth, and I can keep my compute extremely high, and I can keep my memory also bandwidth extremely high as well. But these problems get harder, and I think as the trend that we're seeing is it's going to get more complex rather than less complex, especially as we start building in more multimodal, multidiscipline workloads working in concert as well. How do I bring in ASR models with my language models, with my video models?
Dynamic also. Yeah. It's not just a fully statically scheduled system.
How do I do it with live data coming in from the embedded or from the field somewhere into the data center? How do I connect it with the compute that's embedded at the at the source, and then working in tandem with what's happening in the data center, and kind of blurring all of these lines and how to do it at high reliability? These are going to be really difficult challenges.
Yeah. Satyam, are you guys thinking beyond Coursera and into larger scale systems?
We are, yes. And I think Comran and Rasheed covered most of the points as it relates to scale up and the kind of problems and evolving nature of these interconnects. I would double click on just one aspect of it, which relates to software. For example, as you asked, when we're looking at going beyond one server with Corsair, the question was, what do we use? We do want people to just be able to plug an Ethernet cable. Yep. But underneath that, what's the protocol should we use? So when we looked at the available IPs, obviously, go with Rocky V2. Mm-hmm. The best one-sided RDMA transactions that we could observe in our lab was around 6 microseconds, which out of context would look very small. But when you're talking about attention expert disaggregation, those 6 microseconds are too much. Yep. So we said, no, it's unacceptable. That was the point when we said we have to build something else, and we created the Jetstream card, which cuts it down by a quarter, so 1.5 instead of 6. So the hardware is standard, the switches are standard, but you have to be able to take the libraries and upgrade them to take advantage of that new protocol. Okay. If you were going with Rocky on the same hardware, you won't get the benefit. Well, so that's the trade-off.
And you can break through abstractions at that point.
We could,
right?
yes.
And so you can know what is the use case.
Yes.
And then you can co-design that all the way down to the PHYs you're using. And
it is co-designed, but it's one of those places where you have to selectively break an existing paradigm. Yep. You have to teach a customer that, okay, this is not Rocky, this is something else, but the infrastructure is the same, just the software library is different.
Well, that's one of the things I enjoy about having a small team. Because within a small team, you can get a lot of the people working on multidisciplinary things in the same room, and you can actually break through a lot of those barriers. That makes sense. One of the things I learned from Google TPUs years ago that I still think is fantastic, and I don't know if it's widely replicated, maybe it is having optical routing at the rack level for reliability. Because as you probably know, you get a massive system, I can't even imagine a million chips. Somewhere there's a stick of RAM that's dead. it's just true, right? Yeah. And so if the entire machine goes down for however long it takes to replace that, it's just unacceptable. But if you can actually hot swap out using digital micromirrors or optical network switching, then you can do things for reliability that's really pretty interesting. Now, everybody's talking about big text LLMs. I hear that they're like the solution to AGI or RSI or something, repetitive strain. But there's so many other areas of research, right? There's a lot of different things that are going on. What do you think is most exciting, and what do you think should be paid more attention to? Satyam, do you want to take this one first?
Yeah. As was discussed in multiple talks this morning, the nature of work is evolving. And the kind of applications that we are seeing AI being put to is not always text-based. There are word models, physical AI, how we interact with the environment. How does humans and AI collaborate to accomplish more than individuals do by themselves? What those mean in terms of model architectures, what kind of computing properties we'll see, and as and when we discover the right fitment for those kind of applications, what kind of accelerators are needed for those? It's all in the future. We don't know that yet. But it's very exciting to think about. Once the AI has been proven to work in one domain like language, what else is out there?
Yeah, makes sense. Rasheed, what do you see?
So we're seeing
your crystal ball.
Yeah, well, so a couple things. One, in terms of technologies that people are looking at doing, the multi-token prediction and diffusion LLMs seem interesting. We'll see how it all plays out. The multi-token prediction, at least in the cases where your memory is trivially memory bandwidth bound, low, let's say the low batch size and so on, they can help you improve performance because they're using compute that's otherwise idling. The diffusion LLMs are effectively saying, I have a lot of compute, I have other challenges. So what is interesting is we're seeing the industry notice the challenges and try and work around it, right? So for instance, when someone releases a new model that is deliberately a very large model, but they quantize it a lot because memory is expensive. So the industry is sort of mapping to where the problems are, if you will, either in cost or performance. We'll see how this plays out. One of the bets for us is, as we're changing the memory dynamic, very interesting to see how that will change things. So let's say things like HPC get out into and other technologies of similar type get out into the wild and are broadly used. How will the model creators start defining models differently?
Well, you said 768 gigs per device or something? So you could put like several large LLMs on
You can, or you
just
take
switch between them on a
multi-trillion model and a couple cards and you're there, right? Yeah. So that is the kind of thing. And then when you add the massive memory bandwidth with it,
that's right.
Then you start saying, okay, how is the world going to design things differently? So on one hand, yes, those couple things I mentioned look interesting, but I think we're a lot more excited about getting this out to the world with a software stack that is super easy to use and see what will they do with it.
So you're not betting on float one or something like that?
Eventually, half float.
Comran, what do you see out there?
Looking into my crystal ball, which is always a dangerous statement to start.
Mine's a little bit hazy.
Yeah, it's always a little bit hazy, but I think that I see two major trends, right? Like the models we're looking at today, what we see today are going to get, they're going to go from good to great. And then there's going to be that's going to inspire a whole new set of models. So what's going to get good to great, I think, right now is LLMs today. I think they've impacted all of our lives in the last 2 years. It's radically changing how business is being conducted. It's radically changing how we're, consumer electronics are being, or consumer applications are being implemented, business applications across the board. I think that's not controversial at all to say at this point. But what I think is going to get much better about it is right now, it's still in it's driving a compute scarcity environment, and that's felt across the board. All the GPUs are extremely expensive and extremely hard to get. Compute from us, like Trainium, is extremely hard to get into more hands. And one of the founding mission statements that our chip business, Inferentia and Trainium, was started is we wanted to democratize AI. We want to make it easier for everyone to get the chips and the compute they need to run their applications. But in the world we're in today, it's really expensive. And then as more chips become available on the market, Qualcomm and others, and D-Matrix, it's right now, the reason why compute scarcity, I believe one of the reasons is not only because we're in this AI boom, because AI models today are still really inefficient. And we're going to see them go from good to great, or good to better, where I think the emphasis now is, well, how do I take these LLMs that have proven themselves to be fantastic reasoners, have these complex workflows? Well, how do I reduce the number of tokens they need to generate to give me the same answer? And so we're seeing a lot from the research community trying to drive down the number of intermittent tokens to get to my end output. And I think that's going to improve. I think all of the chips and solutions that guys like ourselves are producing, and guys like everyone here, is we're going to make hardware more efficient, more power efficient. It means we can increase the density of the deployment. We're going to make them cheaper to offer to our customers. So hardware and software is going to get, and software and with our partners is going to be more efficient of how do I extract more from each chip?
Yep.
How do I get all of the peak flops that I've been promised out of these chips, right? So that's a key focus of ours as well. So once we make the infrastructure more efficient, once the models actually deliver towards that efficiency goals, it's going to go from good to great. And I think we're on that cusp. That's where I see one major trend. The other one is the kind of boom of how do I apply these techniques that were learned for LLMs into new modalities and domains?
Yeah, there's been
right?
so much effort just put into it. There's all these tricks.
And so we're working with a lot of researchers from universities and other frontier labs. Like, well, in one area that I feel more excited about is like healthcare and healthcare, life sciences, diagnostics, and therapeutics, right? I think that's going to have a measurable impact on our quality of life everywhere. We're seeing that a few years ago, there was specific models being generated for a lot of the therapeutics out there, right? And I've been happy to work with a few of these companies in the past, like Embedded Genomics, and that were accelerating drug discovery or therapeutics by being able to make models that would help them predict which of their biomarkers or tests that they would be able to run. One of the other things that I see now is, well, how do I take this LLM that's really good and apply it to therapeutics, right? And so I think we'll see the cross modalities happening more and more.
Well, I mean, one of the reasons I love the industry is there's so much investment, so many ideas, and so many different takes on all the same problems. We need to wrap it up, but the one wish I have is for the reasoning models to stop talking to themselves so much, right? And it's like you can actually tell the divide between the open models and the closed models, because the closed models feel like they know they're being paid by the output token. It's so funny to see that. So anyways, we need to wrap it up because we're at time, but I want to thank all the panelists. And so thank you. I hope this was interesting.
Thank you for having us. Thank you.
Thank you to our hardware panel. If there's one thing we heard clearly, it's that the future won't be built on just one kind of chip, and someone has to make them work together.
Which means the hardest part isn't only building faster hardware anymore. It's making all of the hardware usable as one unified stack.
And once you have all those different systems competing for workloads, you run into another question pretty quickly. How do you actually know who's ahead?
That's exactly where we're going next. But first, if you ever wrestle with PyTorch, that one's for you. Gabriel de Marmies has been looking at how Mojo and Max can smooth out those rough edges. Let's take a look.
Hello, Mojo fans. I work at Qt, and there we work a lot with PyTorch. And while PyTorch is great, it also has a lot of pain points. So since I'm familiar with Mojo, my work was to explore if Mojo could blend into the PyTorch ecosystem and fix its flaws. The first thing that users notice when using PyTorch starts even before they write a single line of code. The wheels needed are huge. This is because a lot of kernels are packaged into those wheels for many different GPUs. And sadly, many of those kernels are not open source, which means You cannot study them to write new similar kernels tailored to your task. You have two choices. You can build everything from source. It can take multiple hours to build flash attention, and building PyTorch itself is much longer than this. You need to pay extra attention about the compiler version, the pip flags, and possibly the order of install of your packages. Or you can try your luck and find a wheel with precompiled kernels for your hardware. Those wheels are not on PyPy most of the time. There are many different variants, and it's easy to get it wrong. And even with those two distribution options, many kernels are not portable. My belief is that Mojo can fix this. You're one pip install away from the code you need. Mojo can run on many different types of hardware. You don't need another compiler for another device. But portability does not mean making compromises on performance. You can easily drop down to PTX over assembly if you need to, and since you're compile on target, you don't need pre-built kernels. You also have access to the kernel source code. It's in the wheel. And finally, no need for an extra toolchain to install from somewhere else. I'll show you how it's possible to lower massively the latency when working with Torch eager mode and compiling kernels at runtime. Instead of blocking the user code while we compile, we put the kernels to execute in a FIFO queue. The kernels we haven't compiled yet get compiled with multiple workers. The rule is if the element at the front of the queue is compiled, then we can execute this Python extension and launch the kernels. It also means that if you have many kernels that are already compiled, they will be launched immediately. When we start getting new operations that we don't have the kernels for, here for the backward pass, we put them in the FIFO queue and they get compiled in parallel. This makes a huge difference in the user experience. In the first implementation of the Mojo device for PyTorch, the compilation step was blocking, and the NanoGPT training step took 200 seconds with the cold cache. With this FIFO queue and a pool of workers, we now have 50 seconds on the same machine for the first training step, a 4x reduction in latency. The user will request host device synchronization through methods like CPU or item. In this case, we block until the FIFO queue is empty, and then we wait for the GPU to finish all of its tasks. The second training step doesn't use any new operations, and since the queue is empty, we execute directly the Python extensions, and it sends the kernels to the device stream. We can also leverage Torch Compile to provide an easy bridge for the Max Graph engine. When Torch Compile is first called, nothing happens. Everything happens on the first call of the model, because we need to know the shapes and the types of the input. We then go through the ops and use the composition of ops provided by PyTorch if we encounter complicated ops that we don't have the equivalent code for. When the graph is built, we let Max compile it. This can be nearly instant if Max has a warm crash. Our graph is now ready to be executed on GPU. We now grab all the input tensors given by PyTorch, and we use DLPack to convert them to max tensors without any copies. This DLPack process can be slow, so we use a cache here, since many of those input tensors are weights and thus never change. The Max Graph engine now executes all the operations. We can then convert the output tensors to PyTorch using DLPack. Note that the second time the same function is called, it's the job of PyTorch to check the input d-types and shape, and then reuse the model we already compiled. PyTorch then sends us the input tensors directly, and we just run the Max Graph. Thank you everyone for watching this. I used this work to see if it was possible to train NanoGPT with eager mode, and it works. So if you're interested, have a chat with us and check out the poster. See you there.
It's great to be back again. Our next guests look at the AI ecosystem from a very different angle. They don't make chips, they don't train models, and they don't even sell infrastructure. But they measure the companies that do. And that gives them a unique view into what AI actually means and performance actually means and who's really ahead.
Micah Hill-Smith is co-founder and CEO of Artificial Analysis, and Dylan Patel is founder and chief analyst at Semi-Analysis. Joining them is Modular SVP and GM Tim Davis. Please welcome Micah Hill-Smith and Dylan Patel for AI Analyst Perspectives.
Hello, everyone. Great. So this is a very exciting panel. We're very lucky to have Micah and Dylan here today. We got some awesome questions for them on general benchmarking, and they're also their hot takes on what's happening in the broader industry. Welcome.
Thanks. Good to be here.
All right. So I have a few questions. We're going to play it by ear as we go through. So you guys just answer, and we'll get hot takes as we go. Sound good? All right, so your firms track compute and model benchmarks closely. What's the biggest gap right now between the story the industry tells about AI progress and what the data shows?
Want to go first?
Sure. I think there's always this constant focus on open sources commoditizing frontier labs, and then the frontier labs are so far ahead that no one is really able to compete. And it turns out this is sort of like this all or nothing attitude is just not the right way to look at it.
Yeah.
Each company's workload is very different. Some people stress super fast tokens, but then they ignore that if you use fast tokens, most of the time is actually in like tool calls and CPUs, or vice versa. People are really just focused on throughput and cost per token while ignoring that it's actually atrocious to use a slow model, and so no one's going to use it. So I think these sorts of attributes are what's really being missed by most people when they talk about AI performance, and the total cost of ownership of running an AI workload for a company.
Yep.
And so I think measuring that appropriately and actually seeing what's the best use case and how do you and model for that, and how do you optimize the cost? Because it turns out there's companies paying for Claude Code fast mode, but then they buy their employees regular MacBooks. And it's actually just a terrible idea. You should buy the MacBook Pro, or a high-end CPU, and then run slow tokens, or vice versa, right? People focus just on slow tokens, and then their employees don't utilize the models enough to actually generate all the productivity. So it's really this user experience side of things is missed out when thinking about the TCO.
Yeah, I mean, I completely agree. I'd maybe summarize it just like the real world is pretty messy right now. That what we are asking of the AI models has changed pretty quickly. Like some of the stuff that you want to do on your laptop, as you're talking about there, right? Like you want Claude Code fast, but then you want gazillion subagents all in parallel, them all to execute a ton of stuff. From the performance benchmarks of the chips and the inference stacks and the clouds up to the agents and the models, across this entire thing, like the way that we measure every bit of it is stuff that's been built over the last couple of years and is often quite specific to one piece, but drawing together all of it with real-world mess is pretty complex. That's why like the tricks that you can see the models do sometimes, they don't necessarily pull off perfectly for you every time in real world.
Building on what you said, Dylan, what is your take on we can tier the user, but what is your take on the sophistication level of people actually even understanding the quality of a token, right? Like models, today, we were talking before on another panel, people don't really necessarily understand all the different classes of models, how they and what use cases they should be used on in different ways, right? So the default is, to your point, everyone just selects the highest degree of intelligence, they just pay for that, and that's what everyone has basically done in the industry. Do you think there is a greater understanding on the more advanced user or not?
So I think the most advanced users generally are just using the most expensive tokens, and that's great. They get the best value out of it. They are the most productive with it. But then there's just not enough dedication or focus to thinking about token efficiency, i.e. if there's, for a given task, sometimes the best, most intelligent model is actually also the cheapest because it doesn't take as many thinking tokens. And then in other cases, that another task, the best, most expensive model is
more expensive than a model that can do the job. And so different tasks have different requirements around token efficiency. I think that's another thing that there have been a lot of challenges measuring appropriately. There's all sorts of folks trying to make model routers, right? Companies are trying to do it internally. There's services that are trying to provide this. Hey, if I send you a request, route it to the cheapest or best possible model, depending on the outcome. But these things tend to fail to take into account sometimes. A user can use a less intelligent model, and maybe an extra turn between the user and the model is actually still worth it. In other cases, I want to use the best model because it's more token efficient for the task. In other cases, I want to use a cheaper model because it's same number of tokens, but it still gets the job done. And I think there is no real holistic way to measure that still. And hopefully, either Micah or us, or someone can figure out how to do this properly.
Right. What's your take, Micah?
I mean, I completely agree. I think the big picture I would give of this actually, right, is that there is a view of the world where how far the models have gone and what they can do is still very early in all of the tasks that we foreseeably want them to do. And so there is a ton of work that still sits at or beyond the frontier. And I think that explains why so much usage is concentrated on the frontier models today, because it's not just about whether or not in a binary way you can do it, it's how reliably you can do tasks that kind of look like this sort of task, because you don't actually know before you put a task into an agent exactly how all the models are going to perform at it. So we've got a lot of reason to be wanting to use the frontier models. Right. That explains why so much demand for Opus and Fable and stuff. But then, yeah, completely agree. Like you've got this we think of it as an intelligence and cost Pareto frontier across all of the stuff that can now be done by the smartest models. And you've got a trade-off curve. It is different for different tasks, but on the other hand, it's the difference between tasks is smaller than the progress being made by the models every 6 months. Yep. So you're like playing this intelligence cost Pareto, trying to make the best decisions across it, 1000x range on the x-axis. That's the challenge that every company has today.
So I want to ask you both about inference cost, but before we get there, I'm curious. You both have different benchmarking sort of spectrums. Given we just talked about cost per task, a lot of the benchmarks today are just latency, throughput, end-to-end latency. Yeah. Like, why is there not a bigger focus on, from a benchmarking evaluation standpoint, how do we measure these buckets of tasks, and how are we somehow measuring performance or TCO on a bucketed task, in addition to all those other things? I'm not suggesting that latency and throughput and end-to-end performance and those things aren't important, but we haven't seen that. And so I'm curious, as two leaders in the space on benchmarking, what's your perspective?
I mean, I'll say that those metrics you're talking about, they come together into those more top-level metrics. So you've just got to look in the right place. So, I mean, we try a lot now to report intelligence with cost per task as the top-level way that we look at things. And then we also think a lot about time per task, because as Dylan was talking about a second ago, you get different token efficiency across different models, and you may want to accept using more tokens where each token is less intelligent than fewer tokens on a more expensive model, and the other way around. We've actually pushed quite hard with a lot of our work, especially with labs at the model layer, to talk about things like that. So if you look at like the GPT 5.6 or Opus 5 announcements, the way that OpenAI and Anthropic use our data now is often showing the Pareto frontiers of intelligence and cost per task. As we zoom out though, because I know your interest is not just at the model layer and how OpenAI and Anthropic might talk about it, but how we think about it across the whole stack. Like, yeah, the big picture is for any given task, you need to think about agent, model, cloud, chips, including the inference stack and all of that. And there's a certain amount you're spending across all of that. Preferably, eventually, where we get to is being able to talk about the efficiency of every part of the stack and what it means for what you're actually getting done.
Yep. Do you have a perspective?
I think the other part of it is that there's so many confounding variables.
Right.
You can change or tweak one of them, and all of a sudden your entire view of what's happening changes.
Yep.
Another aspect of this is the model progress is so fast that every 6 months evals are saturated.
Yeah.
Evals are really, really useful when models are scoring like between 10% and 70%.
Totally.
But once they pass 70%, it's kind of like splitting hairs.
Yeah.
Oh, I got one more question right. And then you can get down to like, oh, well, half the question, like 10% of the questions in any eval are like wrong anyways, because the person who made the eval is just, it's really challenging. And then the eval gets useless within 6 months. So you have this like whole cycle of, okay, great, I made a new eval. What's the cost per token? Once you start measuring it, I don't remember if it's like Goodhart's law or what is it, but like once you measure something, it becomes useless.
Yes.
Exactly. Yep.
And it's pretty clear. Everyone benchmarks quite a bit. I think it's also like evals are just the best data. So if you're not training to benchmarks, you're kind of ignoring some of the best data out there. So there's this problem with if you're measuring cost per task, that you have to change what tasks you're measuring every 3 to 6 months. Otherwise, it's useless. And so these indexes, like Micah's got that artificial analysis like index for cost per task. I think they change it pretty often.
Yeah,
right?
we have to. Yeah,
because otherwise it'd be useless. In which case, apples to apples comparisons are impossible. And every year the cost, if you just take an eval from a year ago and take what was the frontier model then, and you take what is an open source super cheap model now, and it scores the same. So clearly those models are the same. But then if you actually like try using the models, the performance is different. And so I think there's a lot of like confounding factors there, whether it be and then that's just if you're running the model wholesale, but then every cloud, every inference provider, every chip, everyone's going to do different things, whether they're doing different sorts of quantization on the activations or the weights. They're doing different stuff on, as Mike was saying, the harnesses, doing different stuff on all sorts of speculation techniques, whether they're lossy or perfectly matched. There's all sorts of things people adjust knobs and dials on, and then it's like even a given model on a given chip, there's a range of benchmarks across all the different API providers. So it's quite a challenging landscape to measure.
It sounds like we're already struggling to define the parameters which we're operating with, adding another layer that probably people won't accept as a standard definition, depending on what the task is, makes it the compounding factors difficult.
Yeah, and you've got to iterate on that over time. But I think the most important thing is, so I completely agree with all that stuff. And for optimizing at any given moment in time, getting something 20% cheaper, 30% faster, all the stuff matters a huge amount. But I think one important point that is really important is that year on year, the differences that we're seeing in the overall shape of the curves are way bigger than those differences that any of those things are driving. One of the trickiest things right now is that we are all existing on this very fast pace of progress that doesn't show any signs of slowing down. So really is different every year.
At the end of the day, I think the model, software, infra, co-design is what's necessary. If you're not doing, because every layer is going to have their innovations, but it's when you compound the innovations across multiple layers that you get this massive improvement, which is not being paid to say this, but maybe that's why Qualcomm acquired Modular. But I think that optimization across every layer is the key thing. But again, it just becomes so many confounding variables to try and deal with.
Yeah, and I mean, we've explained that a lot today, right? Like fragmentation at different parts of the stack. If you have a vertically integrated stack, agentic hardware, agentic harnesses can begin to just optimize away all of those compounding factors, and you get better optimizations at the end point, right? Certainly that's our bet. So,
Darling.
All right, cool. So I have a question. Inference costs keep falling. Is that trend sustainable, or are we approaching a floor set by hardware and energy costs?
Okay. I think costs are going to continue to fall at a drastic pace. There's a lot of new hardware that's come out this week and next week even that continues to drive the cost down. There's huge improvements on inference engines. There's huge improvements on how you manage KV cache. There's huge improvements on the chip layer itself, on the inference engines, new inference optimization techniques, and the models. And each of these is like, okay, if I get a certain improvement per year from each of these, and then I multiply them all together, I'm still at this 10x plus pace. And I don't see that stopping this year or next year or the year after. There's just so much innovation that's coming to the market.
To be clear, though, that is for a fixed level of intelligence, you mean, right? Like the way that we talk about that number is that like the actual stuff we see empirically is like 5 to 10x per year decline in cost per task, price per token, both actually for the same level of intelligence. But on the other hand, we have this exploding cost because the amount that you can spend at the frontier has been going up and up. Frontier tokens, surprisingly stable price over the last 3 years. Like, I think we're charging $50 out for Fable. OpenAI was charging $60 out for GPT-4 quite a long time ago now, 3 years. But we can use way more tokens at the frontier. We're spending way more at the frontier but for a fixed level of intelligence, 5 to 10x decline in price per token every year. That I completely agree it's going to continue, and that is nuts.
So given that though, then what's your bet on, are we going to live in a world, and we were laughing about this before we came out on stage, are we going to live in a world where, and I've certainly read about this online, where we have one company owns all the tokens in the world, and that's end state? Are we going to live in a world where there's a very small number of companies, an oligopoly, that own all the tokens, or is it going to be much more dispersed than that? I'd love it. So this strikes at the heart of where do you think the value is? Yeah. How do you think that curve's going to change? I'd love your perspective.
I think it'll be pretty sad if there ends up being one company in the world.
I would agree with you.
Might be bad for our businesses, bad for yours as well, probably. Not great outcome. I can go first briefly, and I'm sure you have some hot takes on this. I think so if we just divide up the stack, right? So let's say it's, as I was kind of talking about it before, we'll go agents, models, cloud, chips, semiconductor supply chain. Honestly, what is a surprisingly contrarian opinion in San Francisco right now, I would say that I am equal weight on value capture across those 5 layers expressed like that for how everything's going to end up long term. Right now, most of the value is being captured by chip companies and the semiconductor supply chain, like defining it as revenue, profit, market cap, by any metric. Most of the value is currently at those lower bits of the stack. I do think that shifts toward both models and the application layer, controversially, over time. But yeah, honestly, my base case is relatively equal weight across the stack. I actually don't know what your opinion on this is, and I'm quite interested to hear.
Yeah, so I mean, going back to the original question, which is, does one company rule the whole world?
Sure.
In some sense, this year, 30% of the compute being purchased, or net new compute, is just OpenAI Anthropic.
Right.
Now that might go through other providers, but the ultimate end user is those 2 companies serving their own models. Next year, our tracking shows it's about 45 to 50% is from just these 2 companies. So that trend line is pretty scary. I think we want a vibrant ecosystem and vibrant world with a lot of competitors, because otherwise, lack of competition is bad. But ultimately, when you look at value capture across the stack, definitely, last year and before then, it was all the value was on the semiconductor supply chain and some on the data center and cloud folks. This year, we saw this explosion in profitability where Anthropic became profitable in Q2. OpenAI looks like they're going to be profitable in Q3, excluding stock-based compensation for both of these. But on an OpEx basis, and they're profitable. And that's driven by what revenue they're able to get out of tokens. And the same applies to all the inference companies selling tokens as APIs. Their margins went from super low or even negative to positive 50+% in many cases. You can just buy a GB300 and run Kimi tokens and make a 40 to 50% gross margin today with okay utilization. It's pretty insane on open source software.
Part of the explanation of this, though, is that I think we would agree that there is some degree of compute shortage right now, right? Yeah. And so, because it is weird that you can do that, and I completely agree. Everyone's having a great time doing this right now. Yeah, bizarrely, yeah. You can just go to any of our benchmarks and check some nice configs and go spin them up, multiply it by some of these token prices. Yeah, you're having a pretty good time.
So I think the interesting thing this year is that the margins have really inflected at the token side, and Anthropic's margins are 70% or so for their direct API tokens on their own infra. So it's that they're renting. So it's truly an explosion in value capture for them this year. And as we step forward, what has the reaction then been? Well, because their margins are so good, now the hardware supply chain is taking margins up. There's the clouds are charging higher prices. Folks like Nebius or SpaceX are charging higher and higher cost per GPU. The various financiers are taking higher loans were falling for GPUs up until this year, and now they've started to rise again. So there's all sorts of different people who are like, oh, wait a second, I can increase my value capture there. So going back to Micah's point, it's not clear where all the value does get captured. Because at least in the first half of this year, it looked like the models were taking more and more, but now it's starting to proliferate a little further down again, where the clouds are taking higher margin, and even the financiers are taking higher margin. So we'll see where it all shakes out. But ultimately, I do think everyone will make money and we'll all be happy.
As long as the models keep getting smarter.
So I have two questions that I'm going to build on, Dylan, what you just said. So there's a world where the long contracted GPU market, we have all these inference providers today, all this compute that's being purchased on 5-7-year timelines, right? If you look at the value of a lot of that silicon, the tail end of that is actually where there's a lot of revenue generation because you want to use it after years 3, 4, 5. You want to continue to and we saw this with A100s being still resold now in the market, right? So as heterogeneous compute comes online, and we begin to change the economic equation. You have these long contracted GPUs, right, that are 5, 7+ years. Build-outs are happening. Let's say a few companies are generating massive profits. As they start rolling in heterogeneous compute, how does that change long-term GPUs in your mind?
So I think it is still like, as long as there's a silicon shortage, you'll never replace old hardware.
So your view is we just keep consuming all the...
You'll keep consuming, yeah. It used to be 5 years, 6 years, but you're starting to see 7 or 8 years for GPUs life cycles, at least on A100s. There's deals being signed where they're still used until then. Ultimately, the quantum of compute that is A100s or H100s is tiny, even though there were millions of H100s sold relative to how much Blackwells are being sold and how much Rubens after that. So I think there is a bit of a misnomer there. The other thing is, if there's all these heterogeneous inference techniques, whether it's you run the speculative decoding or multi-token prediction on different hardware, or you run prefill and decode on different hardware, or you run attention and feed-forward networks on different hardware, or you're able to do KV cache offload in some way. There's ways to find what is a different form of hardware spiky and capability-wise, and let's find a way to use it. And so ultimately, people and the systems folks will figure out how to use every drop that you give them. And so, yeah, that's I think the key aspect of this.
To your point, do you think we have enough power and we can roll it out fast enough or no?
I mean, the only reason that you start ripping the A100s out is if you don't have enough power, right? Overall, just stepping away from the data that I normally work with and doing some prediction, but I'm pretty sure that the models are going to keep getting smarter, and that's going to keep driving up demand to some pretty crazy levels. Assuming the demand keeps growing faster than we can add power and compute, then yeah, I think we're going to stay in a pretty significant compute shortage for the foreseeable future from here on out.
So then building on that, open weight models versus the closed ones. You both track this a lot in your benchmarking infrastructure. Has the pace of open models, DeepSeek, Minimax, GLM, Kimi closed the gap against frontier models? What's your perspective there? Does the data say otherwise? What's your opinion?
Absolutely not closing the gap. And so let's talk about what it would even mean to close the gap, right? So right now, depending which thing you're looking at, let's say that Opus 5 and Fable 5 are the smartest models, GPT 5.6 and Grok 4.6 just behind them. There are some incredibly strong open weights models that we have in general 3 to 9 months behind the frontier getting released by some of the leading Chinese labs. So right now we've got Kimi K3, GLM 5.2, DeepSeek V4 Pro, the latest update from just in the last week or two. These are very strong models. They are slightly behind the overall frontier models. I think it also can often be true that OpenAI and Anthropic have had an even larger lead at points than the benchmarks have shown because of their robustness to out-of-distribution tasks. But it is certainly true that those open weights models are very strong. So in order for the gap to close, what would have to happen is that someone trains a model that is now the new smartest model in the world, I guess, or equally smart to Fable 5 and Opus 5, and then gives away a copy for free. I think that there is a stable set of incentives for open weights models. If you're not making the smartest model in the world, I do not think that there is a stable incentive to give away a copy for free if you have the smartest model in the world. And I basically expect that no one who trains the then smartest model will give it away for free.
Okay, what's your take?
I think empirically the gap, at least if you go to the December timeframe, on benchmarks was maybe like 7 months, 9 months, and today the gap looks more like 3 or 4 months. But I think there is some, so in some sense you could argue, oh, the gap is closed.
Shortened a bit, but then like R1 and O1, that was like pretty close as well. And then like it has just been like jittery over the time period.
I would
3 to 9 months that I give is very wide. So I agree. Within that, you can have like some tightening.
But then I would also like caveat that with the fact that like, oh, even though the model looks like there's only 3 to 4 months behind, most of the world is not allowed to access Mythos. We're only allowed to access Fable, which is basically Mythos but neutered a little bit. But Anthropic themselves was deploying that model internally in February.
Right.
So it's like they just, and OpenAI is done with their latest model, and they said they're not going to release it. And in fact, they stopped all reinforcement learning training for 2 weeks. They announced that today.
Right.
And Anthropic recently had their risk and safety assessment, said they're not going to release Model 2, which is what they called it, which is like the next version of Mythos. So it seems clear that the frontier labs are at least holding back what they release, whether it's they'll give it to certain partners, they'll give it to certain governments, whatever it is, but they're not releasing it generally, in which case open models seem to be closing the gap to some extent. But it's not clear to me, and I agree with Micah, that no one's going to release the best model in the world open source. We've already seen the licensing structure for the open weights labs start to really slam down. Hey, 20% revenue share if you want to run my model as a company that generates more than $20 million of revenue or something like that. So certainly the open weights is already being pared back a little bit. And so, yeah, I hope open weights models continue to be launched, but ultimately, the compute, going back to the point I made earlier, which is 30% of compute added this year went to OpenAI and Anthropic, and next year it looks like 45 to 50%. What is the market reason for that happening? Is that Anthropic and OpenAI can generate 40, 50, $60 million per megawatt from their models, whereas the open weights models can only generate 25 to $30 million per megawatt. And so ultimately, if renting GB300s cost $13 or $15 million a megawatt, Anthropic and OpenAI will always pay up for it or have more resources to buy more. So there is this concentration thing that's happening. And so even in the backdrop as AI proliferates widely, the largest 2 leading AI companies are concentrating resources because they have an economic advantage in how much revenue their models can really generate.
So if I could summarize your belief, and you tell me if you believe this as well, Micah, but your belief, Dylan, is there's a scarcity of compute factor. You have 2 very large companies generating massive profits. They can just keep buying that compute. Even if we ran the thought experiment of an open weight model that was as good as a frontier model, even if that got released, the reality is anyone that picked it up and tried to serve it would not have enough compute, actually, because of all the compute being purchased from the frontier labs. Is that the view? And so you would just hit a straight up inference wall where you would just hit peak capacity and not be able to exceed it anyway.
I think that's a little black and white, but yeah, I think ultimately
I was trying to be provocative, so you guys have to.
If half the compute next year is purchased by these 2 labs, which is what's under contract, and then you throw on Meta, who's got another like 15, 20%, and then it starts to be really difficult for anyone to grab massive market share, with an open weights model.
Yeah, I agree with that. I think there's also just like one slightly wider point. So there's this like proprietary open weights thing that's important. The other thing that's important is just how competitive the market for smart tokens is. So one of the things really driving the ability of companies to be able to get tokens at good prices right now is just that SpaceX AI is serving Grok 4.6 at a lower price point than Anthropic and OpenAI is serving. It's not open weights, but that's still important competition. But very much agree that what return can you generate on the compute really matters, and is one reason why being further progressed for one company versus another is important, not just for how smart the model is, but what all of their internal costs look like for it. It's going to be interesting times.
And I mean, SpaceX's token direction with Cursor through its acquisitions, obviously changing Grok's usage pretty significantly there. I think it's now the default, right? When you download Cursor, I can't remember the latest, so I could be wrong on that. But
don't know for sure. Wouldn't surprise me.
Okay,
it's a pretty good model.
It is. So actually, on that point, how is it on the evals? Given that you're doing the evals,
we have it just behind GPT 5.6. Okay. Grok 4.6 is pretty good. Some members of our team are actually using it, which we actually don't do that often because there is so much benefit to just using the smartest model at a given time. And yeah, it feels pretty good.
Okay. All right. So if you had to bet where the next surprise comes from, we were talking about this a little bit earlier. Is there some new, continuous training or continuous learning innovation that comes, a model architecture change, a hardware, some really new type of hardware that radically changes the TCO equation, the full stack economics of running it? Where would you put your money, basically? So Dylan, I know you can't talk about it, but you have a VC firm.
You don't have a VC firm, but what is your perspective? If you were to put money somewhere, where would it be?
I mean, okay, before I answer if I put money somewhere, but let me just, my boring answer to this, right, is that I think we could get this continued progress, at each layer of the stack, and that it all multiplies together for us to see dramatic progress overall in the next year or two. Let's assume that we just draw a straight line on the chart and keep it on going up of progress across all of the types of tasks that we can track how good the models are at. We see them keep getting better. That boring answer of we just see basically every trend continue has some profound consequences for things getting unlocked where there are threshold effects. So I do expect us to see some stuff that will feel quite surprising over the next year as the models get smart enough to do a wider range of agentic knowledge work, deal much better with messy real-world situations, pulling in all of the stuff that we do as humans working at companies, bunch of stuff to enable that, including agent swarms, like sub-agents and much more complex orchestration all working well, that enabling us to use more and more tokens, that resulting in the amount that you can spend on AI just continuing to explode higher and higher and higher at the frontier. I think all that is going to feel in practice quite surprising as each one of those things hits, but that you can actually just draw another trend line at each bit of the stack right now, and it all comes together to do it. So
you don't think it's a linear line, though? You think it's a super exponential?
I am suspicious of any claims on whether it's linear or exponential based on it being very hard to define what goes on the y-axis.
Okay, I see.
Any of those charts. I do not think that revenue to the AI industry is going to be linear, though.
Right.
That's one that we can define pretty sharply. But yeah, I'm suspicious of the AI is getting exponentially smarter or anything like that. Because I pick what goes on the y-axis for some of those charts.
Dylan, what's your take?
I think you can zoom into any layer of the stack and see huge, profound changes that will drastically improve efficiency. But at the end of the day, you're going to have this 10x plus improvement in cost per given level of intelligence. But then the other trend line you'll see is, I think, my company is not especially that small. Your company is much larger. But at least what I've seen, what AI's done over the last year, we're at 90 people, is that you would think AI makes everyone sort of more similar, but actually it's made the performance differences wider. And how much a single individual can spend with AI there's a huge dispersion. And as the AI models get better and better, the top performers, I won't say it's perfect correlation, are spending more. There are people who are spending more, not necessarily generating value. And so that's a hard thing to measure. But generally, as these models get bigger, better and better and better, the people who can orchestrate, from one chat session to now multiple agents doing coding to large multi-agent systems for their given task, that's certainly causing a much larger dispersion in sort of performance of individuals. And I think, as far as what is the only thing I would say is I'd invest in the people who can actually utilize AI systems effectively to generate large amounts of work. And so I think that's the key thing that I would sort of focus on, is who is able to actually focus and do that, able to orchestrate these massive systems, able to actually adopt to the newer ways of working and do a lot more work. And it's on every layer of the stack. There are people who are doing this for generating kernels for their new chip. There are people who are designing Verilog with this. There are people who are doing data center design with this. There are people who are tracking data centers with this. There are people who are doing inference engines with this. There's people all up and down the stack. Anywhere you go, I find people that are super, super good at using AI systems to become not just 10x engineers, but 100x or 1000x engineers in their domain. And that means what an individual can do and bring into the world is just so much bigger. So the innovation we're going to see all around us is going to explode. And it's really these people who can unlock these super powerful AI systems to do that. And I think every part of the world, we can make humanity so much better. So there's a lot of innovation to be had and a lot of places to put money.
Yeah, I think, did you want to answer where you would put your money or no?
I mean,
just everywhere.
So obviously to us, so what I was actually going to say is to be true to what I said earlier about being equal weight over the stack. I think that for now we should have a lot of epistemic humility about where the value is going to get captured, and I would be equal weight over the AI stack for the next year or two.
So one last question I want to ask you both. I think it's interesting. We talked about it a little bit earlier, but physical AI is clearly going to be huge, right? A lot of what we spent this session talking about is, somewhat data center driven frontier intelligence, and that's where the token's being produced. There's and certainly, for a lot of folks at Modular, but then also at Qualcomm and other places, there's a huge amount that's going to be pushed out to the edge in the world, right? And so we are going to have some form of frontier intelligence at the edge. What's your take? What is your perspective on world models, those ultimately potentially consuming even more tokens than the frontier models? How do you see that equation changing in the next few years? What's your perspective? Either of you guys can start.
I have a pretty controversial take on this robotics and edge intelligence, right?
Okay.
I think there's going to be an explosion of intelligence on the edge, but given capacity constraints, you've already seen NVIDIA cut their Rubin Ultra chip from 384 gigabytes now down to 192 gigabytes of HBM. You look at the volume of robots that need to be deployed. Clearly, like an NVIDIA Thor is not the solution that will work. It's just too expensive. And ultimately, it's also just a bad idea to deploy that. And so the reason for that is on a performance basis. Sure. There are some things you must do on the robot, right? At some hertz, right? If it's 200, 300 hertz, that many times a second, you must do that on the robot. But then there's a large amount of things that you can do off robot in a cloud data center, and actually the network latency, the round trip latency, even if it's on site in a server class hardware, the performance is so much faster on a more intelligent model that you actually want to remove most of the intelligent from the robots and really have them be, I don't want to say thin clients, because that's like, underselling that there needs to be a lot of intelligence on these devices. It's just any thinking that happens on the order of like 20 to 50 hertz should not be on the robot, because there's just not enough silicon for it. You want to amortize all your infrastructure across way more, let's say physical AI units, whether it's robots or sensors or what have you, and aggregate that onto devices that are either servers within a factory or within a data center that's nearby or what have you, because the network round trip is amortized by the fact that the hardware is much faster in the data center. So that's at least like a take that we've been quantifying this, and so hopefully we can release a report on this soon. But it seems pretty clear that there's just not enough silicon to put out there onto edge AI, and you need to offload a large amount of it to data center class hardware.
I have a comment on that, but you go.
I actually agree a surprising amount. We've never talked about this before, but I think that it is more likely than not that we will see a bunch of the robot stuff play out similarly to how today's AIs have ended up playing out right now. It's pretty expensive, slow, and energy inefficient to do most local inference. Sharing the hardware in the cloud works pretty well. That's going to be a good reason. The reason that I'm most convinced of this actually is, because I agree with the silicon shortage type stuff, but the first models that are going to make the robots do some really useful stuff in the next few years seems pretty clear are going to be pretty big. They're going to be big models that we will rather run in the cloud. It's where they're going to work first, and that will be the reason that a bunch of the robots are going to work in the cloud.
So you're basing that on these are industrial-based robots, or are you imagining that these are robots in there?
So our benchmarking on this was based on NVIDIA open sourced a robot model. It's the best open source robot model out there, and if you run that on a B200 server, you can deal with a 50 millisecond network latency and still be faster, or still be better, more energy efficient, faster than running that on a NVIDIA Orin. And so that's sort of the benchmarking that we've done that hopefully you can release pretty soon.
Okay, great.
And I think those models might get quite a bit bigger.
Sorry?
The models might get quite a bit bigger.
Yeah.
Like the models that we eventually want to use in a couple of years might be quite a lot bigger than that, including relative to the hardware available. We might just have stuff that runs way more efficiently in the cloud for it.
Okay, we have one more question. Next 12 months, what is your hot take? You get one hot take each over the next 12 months. If we are sitting here August next year, what do you think is the biggest thing that's going to have changed in AI?
Well, covered a decent range of things today already, but look, I think probably the biggest thing will be that the agents are doing significantly more tasks that are messy in the real world. There are things right now where, look, it is true that you can get Claude to do a bunch of tasks at work, but it is actually very, very hard to make that work for a lot of processes. We're still spending so much time and effort defining the inputs and outputs, trying to make this stuff work. I think that the next couple of bits of intelligence, whether we call it continual learning or not, like this, how exactly that shapes up, there's a bunch of different threads here, but they're taken together. It makes it easier, not harder, to deploy for a bunch of use cases, and that'll be one of the things that will feel quite different.
All right.
I think an individual can conceivably spend like $5,000 a day on Cloud Code today, and companies are putting caps, so most people don't do that. I think a year from now, it'll be conceivable that a person can effectively, with ROI, spend more than $50,000 a day.
Okay.
Now, most people, if they try to do that, will waste money. But there will be a class of people that can do that and effectively generate, the work of what 100 people used to do in a single day. And so I think that's probably my biggest
hot take.
I guess, yeah.
All right. Did you imagine letting someone at your company spend $50,000 a day next year?
I think so. I think so.
Wow. Okay,
we would either need to continue to grow revenue at the pace we have been, which I hope we do, or really reshuffle how we do things. But I think it's possible.
Nice.
All right. Well, luckily we can revisit these takes. So next year we will do that. How about a huge round of applause for Micah and Dylan?
Cheers.
Thank you. Thanks, guys. That was great.
Those were quite the hot takes. A lot to unpack there. Micah, Dylan, and Tim, thank you. It's clear that performance alone doesn't tell the whole story anymore. Cost, speed, and efficiency matter just as much now.
And ultimately, the reason we care about all of this is because of what people are trying to build on top. So before we meet some of the teams pushing the model frontier, here's Evan Owen talking about training the GPT-2 model entirely in Mojo. Let's take a look.
Hi, I'm Evan Owen, startup founder, software engineer, and AI researcher. This is the story of one kernel from my GPT-2 port to Mojo, and how the math wrote its memory schedule. This one line computes the gradient of layer norm's input. It is the last line of the backwards pass in my project LLM.Mojo, GPT-2 training in pure Mojo. Every kernel I hand wrote for the CPU and GPU. 1 over sigma times g times dy minus s sub 1 minus x hat times s sub 2. That first bit is the chain rule. The other two terms look like they shouldn't be there. In the next 4 minutes, I want to show you where they come from and how that answer decides the parallelization of this kernel. Layer norm does two things to a row. Subtract the mean, divide by the standard deviation. Where the row sat and how big it was are gone. So when a gradient comes back through, 2 requests are wasted. If you shift the whole row, the mean subtraction undoes it. If you stretch it, the variance division undoes it. So backprop deletes exactly those 2 pieces of the gradient. The part that shifts the row and the part that stretches it, keeping only what the output can see. This is known as a projection. Written out, u minus the mean of u minus x hat times the mean of u times x hat. Those 2 means are s sub 1 and s sub 2. The terms that look out of place. Here's the part of the math we care most about. A projection needs 2 dot products, and a dot product doesn't produce a number until it has seen an entire row. So the kernel physically cannot write a single output until it has read every single input. 2 passes, not just 1. This isn't a choice that I made. The math wrote the memory schedule. Pass 1 is the 2 dot products. They're SIMD accumulators, so every lane carries its own running partial, and the whole row collapses with a single reduced add at the end. That is the first thing you get for free, A sum is the friendliest possible thing to vectorize. Pass 2 applies the projection. S sub 1 and S sub 2 are the coefficients, the same line you saw at the start. And rows are independent of each other, so the outer loop is just a closure over a slice of rows handed to trace parallelize. The closure captures the pointers directly. No argument marshalling, no thread pool boilerplate. A closure in SIMD lanes, nothing exotic, and it's 5 times faster than LLM.C with OpenMP across 16 threads. Now let's look at the same kernel on the GPU. Look at the middle section. That's the same code. The math doesn't know what hardware it's running on, so the arithmetic doesn't either. 2 things change: how rows get handed out, a worker slice of rows becomes a block striding over rows, and how the partial gets reduced. Reduce add across SIMD lanes becomes block sum across threads. Everything between those two is shared. That's the argument for writing kernels in Mojo. Not that it's fast, though it is, that one expression of math can carry 2 schedules. Here's the real training. LLM.C's canonical 40-step run, batch for batch. Watch the validation loss land. It matches LLM.C exactly to 3 decimal places. And that's one op. 25 more like it in the repo with the full math of bat propagation. All MIT license, the link is on the screen. Thanks to Martin Dudek for the original Mojo port, Andre Karpathy for LLM.C, and 3 Blue 1 Browns Manum for the animations.
Hopefully everyone got another cup of coffee or a Diet Coke, because the next few talks are well worth your time. Now, from the people measuring the industry to the people building it. 4 labs, 4 very different bets on what comes next.
Please welcome Paige Bailey of Google DeepMind, Victor Suartez of Minimax, Joe Spisak of Reflection AI, and Vern Render of Poolside. Moderating the conversation is Modular's VP of Product, Eric Johnson. Please welcome the panel for building frontier models.
Watch out for that.
Excited!
1, 2, 3. We were planning to do a coordinated sit.
We were going to try.
Or we do the wave.
We would do the wave as we sat.
Oh, one-man show, though.
Yeah.
All right, we're going to kick it off with just a few introductions. So we're just going to go this way. Paige, you want to just kind of say, you've already said your name, but where do you work? What do you do there, et cetera?
Awesome. Greetings, everyone. My name is Paige Bailey. I'm the engineering lead for our DevRel team at DeepMind.
Hello, everyone. My name is Victor. Currently working on a GTM and marketing at Minimax.
Cool. I'm Joe Spisak. I'm at Reflection, lead product in our open source team. And yeah, I've worked on a bunch of open source projects, PyTorch and Llama, and super excited to be here. So.
Hey, everyone. I'm Varun. I work at Poolside. I'm responsible for our model releases and part of our engineering work on our model factory, which hopefully we get onto a little bit later. But great to be here. Thanks for having us.
Cool. So I asked all of them what they do and don't want to talk about. So I'm mostly going to focus on the stuff they don't want to talk about. Not really. But I think the first topic that is sort of on everybody's mind is just sort of open source versus proprietary and how the industry is sort of shifting. So Varun, I know you kind of had a strong opinion on that.
Sure.
If you'd like to kind of kick us off.
Yeah, happy to. I think one of the questions we get often is, how do you see the strategy you have around open weights, where Poolside is a company for the 3.5 years that we've been around, we've been releasing models effectively in private to specific enterprises, specific customers, while we've been iterating on our recipe and our foundation for building. And what's become clear is that in the world, we're kind of on a collision course with a situation where there may be a small number of intelligence providers. And I think it's beyond doubt, and I'm sure the panel agrees, that there is a huge resource in intelligence, and this is something that is going to, already has in many ways, change the world. And we made the observation as a company earlier this year that we would love to live in a world and participate in a world where there are 20, 30, 50 intelligence providers, maybe more. There are huge requirements from capital intensity and things like this to make that a reality. But it's a world that we want to live in, and we think, our part in the industry can be, and is this part of the year, and hopefully well into next year, that supporting open by releasing our models open and putting more of our research out there is a great thing we can do to drive in that direction. But it won't be the only thing, and it won't be enough. There'll be a lot of things that we all have to contend with. But it is a reality that the capital requirements for building intelligence are enormous. And so we have to make some decisions as we go forward. And I think it will become a question for Joe's team at Reflection and many of the other labs about how do we find ourselves a way to continue to build for the world that we want. And I think one of the things that brings me a lot of hope is we see how much more important the Pareto curve of cost quality is than it was even a year ago. And I mean, I remember a time not too long ago that Google completely owned the Pareto curve for intelligence. And I think now it's really nicely split between the frontier labs, Western open labs, Chinese labs. And I imagine that situation will remain the case for some number of months and hopefully longer. So that gives me some hope that we will see a world where there's different use cases for intelligence in different providers. But also we don't exist to be king of a small kingdom. Like, we're trying to build intelligence like anybody else. So I think long-winded answer and hopefully more of a starter for opinions from you folks. But I'm, very hopeful we can be in a place soon where these things coexist and it all makes more sense. But it will be a really interesting year where I think things are a little unclear right now.
Victor, or Paige, did you want to say something?
I will happily agree that we need to have kind of this blend of frontier models as well as open models. I feel really fortunate that DeepMind is investing in both. We're actually celebrating the 1 billion download of our Gemma model family this Thursday, which is pretty exciting. And I agree. Like I think that the only way that we can truly democratize AI and to really build something that's pervasive, that feels like it's ubiquitous across all of the devices that we have, whether they're mobile devices or laptops or servers, is by having a really, really robust open model story. And I'm so grateful for the team at Reflection and for other providers for figuring out what that story might look like, and then also making sure that it's secure, that it's kind of enterprise grade, and that people are able to kind of sort of handily and kind of almost as part of their normal infrastructure swap between different models as it makes sense, and then kind of refresh whatever models as new capabilities arrive onto the scene.
So, you've been called twice.
Yeah.
So,
I think I'm a little less philosophical on OpenAI. I think I'm much more, I guess, a pragmatist, and I've been in full disclosure. I guess I've been in the OpenAI space for, I don't know, a dozen years or more now, and but pragmatically, I think it makes sense for many, and it's even more increasingly important for owning your intelligence. And I think like to own your intelligence, you have to be able to control it. You can't be nerfed. You have to understand your costs, because ultimately it's something that's strategic for your company, for your country, for you as a personal, for you personally. And if you're at the mercy of something, right, whether it is cost or it is you're getting rate limited or you're getting nerfed without you knowing it, like these are things like you just can't trust it.
Yeah.
And so if you don't own it, you can't really trust it. If you don't have agency, you can't really trust and build on top of it. Because ultimately, this is the foundation for basically every company and everything on the planet, right?
Yep.
It's that important. And so to me, like, the fact that it's open is almost slightly a red herring in some ways. It's like it has to be there. And this is like what we're focused on at Reflection is AI factories and helping folks like Shinsegae and DOE and others that that want to build on open technology because ultimately they have agency over it. And they, in a lot of cases with other the closed providers, they just don't. And so I think I applaud Google having a hand in both areas and being able to provide open weight models, but also provide frontier via service and so on. So
yeah. Victor, did you want to add something about
Yeah, I'd love to jump in here. So those familiar with Minimax, you guys know our motto, slogan is intelligence with everyone. So we push so heavily in the open weight space, in the open source ecosystem. And what excites me the most is really just the innovation in this space and the optionality it gives. I know the panelists have briefly mentioned these as well, but just what we're able to see from the community, the developers, the way they're able to integrate it across so many different hardwares. A great story that I really enjoyed listening to recently at one of these events was how the community was able to attach a visual encoder to one of the other open source models that did not have any eyes, essentially. And they were able to post-train this and essentially give this open weight model the eyes it needed that the R&D team didn't ship it out with. Yeah. And this is only possible because of open weight. It's only possible because of the community and developers that contribute to it. And for instance, with our video model that was recently launched a couple of weeks back, and only 2 days after open weighting it, we saw support across like Apple Silicon with MLX and all sorts of different hardware that we previously didn't even optimize our model for. So this sort of innovation is only possible with open weight.
Yeah, never underestimate the open source and open weight community. And I love that there are so many people on this panel who also worked on machine learning frameworks like open frameworks, PyTorch, JAX, TensorFlow. Mojo as well. Congratulations on open sourcing it today.
trying to get a plug there.
Yeah. And also such deep expertise and experience in the open community. I am grateful that AI still has that, even though so much has gone back to proprietary models.
So we all agree open is great.
Yeah.
I think, Joe, reflection, I think the business model is clear there, but can anybody else speak to the business model of open weight models, right? Because at the end of the day, Varun, you made this point that the barrier to entry is a crap ton of money.
Yeah.
And how do you balance that with wanting to actually, build this open community, make AI more accessible? How do you do that?
Yeah. I mean, I don't think anyone has figured this out in full. I don't think we have. I think we have some sense that while we continue to build and iterate, it's a great blessing to be able to release models out into the community, get feedback. I mean, that's been maybe the biggest change for us this year as a company, is that we've been able to leverage, what is an insatiable demand for intelligence and open intelligence and, free models, that we've been able to learn so much about our own development and our own models by taking advantage of this. But I think the thing I'll go back to is the Pareto curve is clearly something that matters a lot this year and going forward. And it's not clear to me that the frontier model and the frontier lab will cover the whole range of the curve at all times. And I think that while we are in a world where different users, enterprises, defense, we do a lot of work with the defense community, and I know you guys do as well, have desires for control, desires for a certain size or architecture and things like this, that the pie will be so large in terms of what is required from intelligence in all the applications that we dream of, that I think we are really just at the beginning of understanding what the potential business model and opportunities there are for a whole range of different models. And I think the calculus for all of us will be different next year and the year after that, but maybe an elegant way of dodging your question a little bit. But I think there's so much room ahead of us, and we are privileged to be in a position where we can double down on the things that matter to us right now, to be able to keep investing in making the models better and try to understand how, the world shifts in the coming months and take our shot when it makes sense. Yeah.
Can I tell one of my favorite stories too? And Strong plus one. So we released our Gemma open model family, which has a bunch of different weights available. So we have a 2 billion parameter version, a 4 billion parameter version, 12 billion, 26B, 31B, and quantized versions of them all. And after we released the 2 billion parameter text-only version, there was an engineer who's brilliant at Hugging Face, who's also responsible for the Transformers JS framework, but he rewrote a bunch of the kernels using Fable 5 and made it work incredibly fast, sandboxed within the browser using WebAssembly. So this means that you can take this model, you can load it within your browser, so like super speedily do text streaming, ask it questions without necessarily even having to download it to your local device and figure out how to run it. And it is absolutely exciting to see what the community is able to do along those lines. It ended up having time to first token being, on the order of just a couple of 100 milliseconds.
That's crazy.
And it's insane. Like it's to be able to do those kinds of things by drawing on the power of the open community and having them use their expertise to improve the models that get released.
I mean, I do think like the commercialization of open source is actually, I mean, it's a challenging topic, sure, but there's also a lot of success stories. I mean, there's Jan Stoika's army of startups right out of Berkeley, where you have Databricks, obviously a highly successful company built on Spark. You have Anyscale built on Ray. You have Infract and Radix Arc raising money, significant rounds, and there's really, in my mind, there's two ways this. There's you can build basically more of a freemium style approach where you kind of build managed services around open source, and that works for companies, and that's kind of where Databricks sort of started, and they obviously grew significantly from there. Then there's also what I experienced at Facebook in the earlier days of PyTorch, where for us we were moving so fast in the ML space that we kind of woke up and saw that we needed this lingua franca with the space, it's we couldn't possibly ablate all these ideas ourselves, and we also were faced with integrity challenges on our platform where we had nudity and hateful memes and all these things, And back in the day, I'm going to sound like an old man here, but like, we had like CNNs, right? That were, like the kind of wave of like residual nets that came out week after week after week, if you remember, right? And you remember, right? I think back in TensorFlow. And like these literally were written in PyTorch, and we would pull them from the research community, we retrain them on our data, and our classifiers would literally week over week get better. And it was just like amazing for our business because we just drafted off this amazing community. And that was like a really strong business case because like there was a big question mark of like, should we invest all these hundreds of people into PyTorch? What is the value of the company? And it was like a very direct thing. But obviously there's a bunch of other indirect ways that we benefited. So I think any open source project like that, you do need to kind of start with like the selfish goal or the selfish reason why you're going to do that. It's like open for open's sake doesn't make that much sense. But if you have that strategic reason, that goal, that selfish thing you want, it can be a powerful motivator for you.
Yeah, and to run these models, to fine tune them, to make them really, really work for your companies, you're probably going to need a cloud service provider. You're going to need, storage. You're going to need some way to evaluate them, to kind of track and log metrics against them. So from a cloud service provider perspective, like GCP has been taken off like gangbusters for open models.
We saw all the MLOps stuff like grow around us with PyTorch. We just sort of picked and choose. Like that's good. That's, we use that. It's actually a really powerful thing.
So changing gears here a little bit, kind of a provocative question, but are models commoditizing? And if not, where is the innovation coming from? Is it data? Is it post-training techniques? Where are we actually getting wins going forward? Is it just pure scaling? Are we still talking about pure scaling, where most of the wins have come from the last 5, 6, 7 years? Like, what are we talking about?
You want to go?
I'm happy to go first. I mean, we think about it pretty simply. I think there are two things that we can do at any time. We are either improving our data, or we are improving our compute efficiency vis-a-vis better training, better inference, all the fancy tricks around RL infrastructure and all of these things. It's very clear to, I think, hopefully everyone, that we are in a little bit of a commodity race right now when it comes to models. What I think is really important to remember, and what we have spent a lot of time building internally and actually have reduced a little bit of what we do externally as a result, is the incremental work of training models is really hard, in that you do a lot of work to build your first data pipelines, you do a lot of work to build your first piece of RL infrastructure, and you build your data sets, you build your filtering, and then you reach a stage where you train your model. And one of the things that we learned after a lot of hard work doing this by hand is that this artisanal approach doesn't really work very well. And you need to spend a lot of time and energy thinking about how to engineer your way forward. And so when I think about differentiation between labs and where we see the relevant investment for ourselves, it's all around investing in this factory approach for us to be able to say, we know how to reduce the iteration speed, increase the iteration speed, reduce the iteration time for our researchers, because we can get them from thesis 1 to thesis 2 as fast as possible. We know how to make the most of the data sets that we already have, because we've maintained full lineage and we understand exactly what went into packing them. So lots of bits and pieces like this. I don't think there are any big secrets in the industry. I think what's interesting is that we're in a moment where I see this as there's an acceleration and then a little bit of a plateauing, and we all kind of converge on similar techniques during this plateauing, and then there'll be another jump, and we all have our ideas about where the next jump will come from. We have ours. We're not super ready to talk about them yet. I think with these things,
you don't want to reveal them?
As soon as there's a little bit of a hint in the right direction, I think but we have a few ideas. None of them may be right. We'll be, watching and waiting and trying a few different things. But I think that would be my answer. I think yes to commoditization. I think there is still a lot to do to become great at training models and to be consistently good. And I think there is a lot of runway for different labs to show their muscle and things like that over
And I think the package around the model is also very, very vitally important. So I'm not sure if folks have heard of Harness Bench. I know artificialanalysis.ai has done a lot of work around this too. But if you hold the model as constant and vary the agent harness that you're using for a specific task, whether it's open code or OpenClaw or Hermes or whatever it is, you can see dramatic swings in model performance based on that agent harness, the tools that it has access to, and how it's kind of hooked into the infrastructure. And then also, things around the ergonomics of model utilization. Like a lot of people really love using Gemini 3.7 Flash. And when you ask them, it's predominantly because of speed. Like you feel like you're sprinting and that you can iterate faster. And so you're able to get a lot more done than if you got an initial result, but you had to wait a while for it. So I think we're just starting to understand kind of the HCI of what does it mean to work with these AI models? How do we build them into systems that are reliable and interesting and useful? And then also, I am a fan of the idea that data is everything for model pre-training and post-training. And so the more that you can get data, whether it's sort of human created or synthetically generated, that aligns with what users are expecting to do, the better kind of quality that we'll get from models over time.
Has agentic AI sort of, you talked about agentic harnesses, but has agentic AI actually changed the way that you design and build these models in a very substantial way? And if so, can you talk about that for the audience?
Well, full stop, yes. I mean, going back to what Paige was saying, I think we used to compare model to model, and now, look at artificial analysis as harnesses, and you actually mix and match harnesses, and you can kind of see that, actually even like Pi, as simple as it is, right? It's very, very lean, very clean, simple harness. The DeepSeek one is also super, super simple. It actually outperforms much more complex harnesses. So I do think the full stack is important. I think if you just compare model to model, sure, you can call it a commodity. It's weird because it's simultaneously commodity, but also strategic and at the same time. Same with actually harnesses, right? We had a Hugging Face and folks, we had a meet up at our offices 2 weeks ago, and I think Ben was there and he was presenting, and he was like, we're counting 1,702 harnesses and they're building a hub now, and it's like, oh my God. So I do think the stack matters a ton. I do want to go back to the bitter lesson pill, kind of like you were alluding to earlier, because when I was reading the DeepSeek paper when it first came out, now over 2 years ago it seems, or whatever that was. I mean, I think people really indexed on the cost of model training, which is it was misleading, I think, or people were misled. I looked at the RL curves. That's the first thing I jumped to in that paper, and I saw how implicitly bitter lesson pilled it was. It was you pour more compute, those curves are going up. But it's also, I mean, back to the point you're making earlier, it is very much an art still and not a science. RL is getting stable RL infra at scale and being able to run on tens of thousands of GPUs is not something that every team on the planet can do. So I do think going back to, is it commodity? Well, if only maybe less than 10 or even less than 8 maybe, or whatever teams on the planet can do it, I actually wouldn't consider it a commodity, even if there is a lot of models out there, so.
Yeah, so you're saying in some ways that there's certain constraints. One constraint is compute. One constraint is skill, and another constraint is data.
Yeah. And compute efficiencies are important. I think while we're probably one of the more well-capitalized neo labs, I would say, that's out there, we still don't have the money that Google or OpenAI has, or the compute. But we're able to find ways to get big compute gains on RL, where we've got 6x wins over weeks, and that accelerates the RL runs that we have going. And so when you get those wins, when you're forced to be constrained, because I came from Meta where we had a lot of compute and people would just sort of I need 5,000, whatever GPUs to do some ablations or do, whatever. I'm like, oh my God, really? I mean, so I think being constrained actually can help you. Obviously we'd love to have more compute, but I think, having constraints actually is good.
100%. And it's if you remember did you read the Kimi K3 technical report?
Yeah.
So it's, if y'all in the audience haven't read it, strong recommend.
Yep.
They go into deep detail about how, and I'm paraphrasing it, so bear with me, but it's basically we didn't have as much compute as we wanted, and also it was old compute, which sucked. So we had to do all of these like really interesting things in order to actually train this awesome model. And that constraint actually led to the artistry being much, much more kind of novel and efficient than it would have been otherwise.
Well, I think some of the original Transformer paper was influenced by just TPU architecture.
Yeah.
Right. So we do have that sort of software or
Yeah.
almost model hardware co-design. Right. Speaking of, like, can you guys talk a little bit about just the compute you're using to do this? Have you guys moved off of NVIDIA in any way? Are you trying to? How do you think about compute constraints as you're doing this? Like, how does that impact things?
I went first last time.
Okay. I mean, our answer is pretty straightforward. We use a lot of NVIDIA GPUs, as much as we can get, as many as we can get, as long as we can get them. I think it's we're super focused on shipping models, and so. But I think my background is definitely hardware heterogeneity. If you look at the blog post I did last year at PyTorch conference, I believe in hardware heterogeneity, full stack, everything I built on PyTorch. I've been working with AMD since 2018, 2017, trying to get their stack into place. We ship billions of dollars of their infrastructure. Obviously, we're here at Modular Qualcomm here. I've been working with Qualcomm for many years since Jeff and I and folks working together. So I believe deeply in that world. Our company is definitely in a very pragmatic regime in terms of like as much compute with as little friction in the software stack as possible in the short term. But I think we will absolutely be supporting lots of hardware. And through our friends like VLM and SU Lang, who support lots of hardware, TPUs, support AMD. So you can't really democratize unless you run on the broad set of hardware.
Yeah. And I mean, I think I have a similar answer. Our current primary cluster is NVIDIA Hoppers, so we're still a little bit vintage in that way. But
actually, they're coming up in price.
Yeah, I mean, but the mileage we've had has been amazing. I mean, we've had the same cluster for coming up on 2 years now, and just from this investment in data and investment in compute efficiency, it's amazing the progress you can make, right? And I think we're excited to move to Blackwells. We're excited about all of the innovation in the industry more broadly. I think it's also interesting, from the lens of some of our customers, where heterogeneous compute, having the ability to confidently run inference on different kinds of hardware, depending on what's available, depending on different cost profiles. I mean, we have some customers who are very happily running smaller models of ours on, single developer workstations and things like this. So I think we're super excited about the range of different possibilities that come from having a wide ecosystem of compute. But we've certainly invested significantly in making sure we can squeeze the most out of the ecosystem we're committed to from training perspective. And likewise, NVIDIA is a longtime investor in Poolside as well. But yeah.
I agree. The DeepMind story, we obviously use TPUs both for training and for inference across the company. They're incredibly powerful. It's been really interesting to see how they've evolved over time and as the models have advanced. But we're also running models for inference on NVIDIA GPUs. The Gemma team has invested pretty significantly in AMD support and NVIDIA support, being able to run Gemma even on tiny devices on CPU only. For the tiniest versions.
Yep.
And so I do agree, this story of heterogeneous compute, especially as we move into these more complex agent workflows, I think we're going to see a big blend of CPU plus GPU inference and being able to flexibly shift between both, which is, I think Modular also is working towards that bright future.
Cool. Yeah. One thing I wanted to ask, changing direction a little bit, is actually about the process. So Varun, you talked a little bit about this. Maybe Victor, you have a perspective on this as well. But just what's the biggest challenge just getting a new version of a model, like a full update, right? So a full major version change. What is the biggest bottleneck or challenge in getting that from start to finish to market?
Happy to kick it off. I think my biggest concern, so I spend a lot of my time right at the beginning of the process, so on our factory infrastructure, and also right at the end of the process as we're working with partners to get the model out there and deliver. The biggest thing, I think there's two things really. I think one is general timeline compression. because for us, having a high cadence of releases is super important because that allows us to measure our own progress. It allows us to stay out there and keep our name out there and all these things. So this has been great, but these processes are really complicated and there's a lot of moving pieces. And so general compression of timelines makes everything harder, right? Whether it's pre-training, whether it's the number of days you can squeeze out for RL, like all of these things are hard. I think something that's been really interesting recently has been trying to really take our time on evaluations. So one of the things that we've observed, and we've worked with a number of the sort of big evaluations providers like Scale and the team, the Harbor Framework, for example, we're seeing a lot of incidences of reward hacking-like behavior and things like this, and we've invested a lot, in developing our own evals, but also patches and fixes for existing evals we see out there and upstreaming them and things like that. But there's still no substitute for like good old sample review, and so we really want to make sure we always leave time to check our work, make sure we're really carefully understanding where progress has been made on different evaluations. With our most recent release, we actually decided to just publish all of the trajectories for all of our like final hero evaluation runs. We figure let's try and set a bit of a standard here for other providers where we want to be super open and transparent about, this is the progress we made on this eval, here are tasks where things still don't work, and this is the kind of work we've done to try to mitigate reward hacking and things like this. But still a major challenge. I think something that any user of models should be aware of is that our evals are super imperfect right now as an industry, and we all have to get a lot better, I think, at trying to understand how do we best represent the leading capabilities of models when we have these lagging evals, which in many cases are subject to problems with reward hacking and issues with sandbox resources and stuff like that. So that's also a bit of a novel challenge.
Yeah. And thank you also for bringing up like timeline compression, especially with matching the cadence of these releases, not only on the Minimax side, but also for all these other frontier labs, all these other open source labs. So a bit about my work, definitely much more on the end of the pipeline. How do we uniquely position ourselves, especially when we honestly don't know what's coming out? What's the next step function improvement or where the Pareto curve is headed to? And I feel as though the way we've approached it, especially here at Minimax, being a company that focuses entirely on our multimodality and our different models that we offer, is finding the bridge between open source as well as these different modalities. As you've seen recently, we did even open source our OpenWeight, our music model 3.0 as well, which was pretty big surprise, especially for some of the creative professionals we have within our ecosystem. And finding these unique ways to position not only Minimax, but also our community within this whole AI ecosystem has been a challenge, but also really rewarding too, for sure.
Yeah. Okay. I agree, like building the community strategy around a model release is so important. And I feel like we're really fortunate on the Gemini side and on the Gemma side to have so many people who can be part of that story for a day zero announcement.
Yep.
Like we've been working really closely with the teams at Unsloth and Olama, and then also the folks at Vercel, LiveKit, et cetera, to make sure that when we do release these models, it's everyone who can kind of share the story and to feel like a hero and be there in the place where people can actually start using it and pick it up and actually kick the tires. As opposed to historically, I think that when the models got released, it was a little bit perplexing for people to understand, like, well, where do I actually go to test it out? I'm already using it as part of my infrastructure here. How would I easily swap it out and see if it actually accelerates my use case? And so I think that's something that I'm most proud of that we've been investing in over the course of the last year and a half, is making sure that when we do talk about model releases, it's not just the Frontier Lab sharing the joy, it's kind of everyone in the community feeling like a hero and feeling like they can be part of the story.
No, I totally agree with that, Paige. Crafting that narrative, especially with our partners, is not only unique, but also incredibly important for us at Minimax as well, when you guys are modular.
Yeah. So last question, because we're running out of time here. What's missing between, I know it's going to be a hard question, but what's missing between where we are today and sort of true autonomy? I think everybody looking at agentic usage today would love to get to a point where...
True autonomy?
Yeah, autonomy in the sense of not like true AGI, but autonomy in the sense of I can ask an agent to do something, wake up the next morning, and it's going to be complete, right? And there's sort of an active learning component to it where that model's actually figuring out what I want, and I'm not having to write a prompt that has 5 million "don't do this" in it. How far away from that are we, and how do we get there?
I mean, it's a good question. I mean, it's hard to say how far away we are. I mean, I still think we're like in somewhat still like we're in a little bit of a high entropy phase in terms of like all the components that are coming out and like the gold rush of harnesses and how do you mix and match these things so that you get some kind of determinism out of the system. And then there's the whole, discussion around like safety and security and observability. And, before I left Meta, we published a paper, we ended up branding it something else, but basically we called it Agent Bus, and like agents talking to agents and being able to durably write to a bus that they could then talk to each other and inspect and see what each other were doing. And I think it created this like environment where we took basically more of like a distributed systems approach where if it's like a fault tolerant agentic multi-agent system, and there's different ways that you can do swarms and these things, but ultimately they're going to fail. They're going to fail, and you're going to have to be able to fail over in a way. So I think we're still at the early days of trying to figure that out and having these like super long horizon tasks, because they will diverge. They will, like, I mean, you look at the agents today and they will just, they will reward hack, back to the point earlier for sure. But they're very much not deterministic. They will burn a lot of tokens and sometimes just go nowhere. And I think that's like still a problem. So I think like, one of the biggest challenges that I think we see that we're trying to solve is definitely the token efficiency. How do you get to a more deterministic solution without just burning millions and millions of tokens? And I think like that's where there's like this misnomer or understanding of like the per million token blended like price. Is that actually my bounded price? No, because it ultimately doesn't matter what that price is. But I do think like the tooling around the models is getting better and better, and the models themselves are getting better and better. I think we're getting closer. I think for constrained use cases, I actually think we're pretty much there for like a lot of coding. But still, when you use coding agent, like it writes a lot of code you don't need. And if you kind of challenge it, oh well, I don't need that. Like, and I just blew that away. And so a lot of people actually will pit agents against agents, or Joaquin Candela, my friend of mine who was at OpenAI, worked with him a long time at Facebook. He pits Codex against Claude, against Cursor, and has them judge each other, and like ultimately gets things down. And then he ultimately merges the pull request. So people have different ways of like approaching things. And but I think we're probably, for certain things like coding, we're pretty close, I think, in my opinion. So.
Yeah. I love the discussion of kind of ML for systems and distributed systems approaches towards building these agent workflows. And I love also that those disciplines have this expectation of failure.
Yeah.
If you have a bunch of processes operating simultaneously, like some percentage of them will flow, it'll fail. And so you have to build checks into your system to make sure that you can spot those instances and figure out how to gracefully recover. And I think it's a great point that we need a similar philosophy for agents and for these model systems.
GPUs fail all the time.
Exactly.
In the first Llama paper, we published the failure rate for all the GPUs for NVIDIA GPUs we were using. And I mean, it was like a significant percentage. Actually, most of the failures in pre-training were because NVIDIA GPUs went down.
And hard disks and even CPUs when you're at like Google scale or even smaller scales, like some percentage of them will fail.
That's right.
And just as kind of natural guarantees from the supplier. So you've got to figure out how to react to those instances.
Yeah, and just quickly, I feel like there's still a lot of untapped potentials on with the models we actually have out now, and what we optimize with the systems. There's a lot of innovation we can do there. Pretty unique case, but I've seen, especially with how these systems and harnesses actually compact context, have a significant impact on the models and their performance, also the memory layer that you use. All these things that we can fine tune at the harness, at the system layer, are just as important for reaching that level of autonomy, just as the model too.
Do you want to say any last
No,
words?
I think the only thing I'd say is it's basically a combination of a system design problem, right?
Yep.
And a task design problem. And I think I see amazing examples of people just setting up the environment such that models can work autonomously. So I think my answer to your question, we were already there. If you look at some of the work that gets done in kernel optimization and things like this, if you create the right setup, then for certain tasks, this is possible. I mean, one of the ways that I like to think about this is you're basically in the business of figuring out what the right experimental loop is for the thing you want to do. Sure. Yeah. And one of the reasons I think biology will come very soon is that it will become a matter of us understanding how do we create the right experimental cycle for the physical world of the wet lab.
Yeah. How do you match in silico with the wet lab and create the interloop? Yeah.
Exactly. Yeah. But if you think about it in that way, these things are not far away, right? Because it's just work to be invested in.
How do you effectively programmatically create a scientific method for working through it?
Yep. Exactly.
Yep.
Makes sense. Cool. Well, we're at the end. Please give it up for the panelists.
Great question.
How should we stand up?
We should stand up and
walk.
No water for me.
No way.
What an exciting future ahead. A big thank you to our panel for a look at what's happening at the frontier right now, and just as importantly, what remains unsolved. Before we move underneath the models again, here's Maria Saraton introducing Milfolio, a way to pull insights from data without the data ever leaving your Mac.
Let's have a look.
Have you ever wanted to get insights from your data, your private data, but wanted to make sure that it doesn't leave your drive? With foundational models and their harnesses, I'm worried that part of my data will leak to the provider and then to the wider internet. By exploring, still a work in progress, is to use a two-tier approach. The foundational model receives helpers, schemas, and some tags or categories about your data and generates some Mojo code. This Mojo code is processed in the backend of the Milfolio app, which is also written in Mojo. There it goes to the privacy system, the GPU engine, the vault, and it applies the text classifications received from the foundational model to the data. The local model is the only model seeing your data. Let's take a look at the Milfolio application running locally. You can see all your data under Vault, in this case the demo financial transactions. Here are the simple and AI tags existing in the system. Under Board, you can save useful questions you have asked earlier. Let's go to chat and look at the available local models. We will ask a question about impulse buys, a tag that doesn't exist yet in the system. You can see here the information shared with a foundational model, and the foundational model will generate the first version of the code. You can see the suggested tag for the local model in the generated code. Milfolio will start to run the new tag over your Vault transactions in batch mode. It will take 4 to 5 minutes to apply the tag, depending on how many transactions you have. The tag will be saved for this and for future transactions. At this time, we only get about 30 tokens per second, so it's important to manage your compute. An updated version of the code is generated now with a precompiled tag. The compilation and execution will be much faster now. The code will generate some structured data, which will be rendered as a dashboard by the app. You can navigate back to the Vault, filter by a given merchant. Here are some more details about the architecture of the app. The GPU engine is about 17,000 lines of Mojo 1.0 RC3. It is custom written for this application with Claude, and it contains a couple of models. Note that one of the models is too big for 16 gigabytes of memory, and it also contains the embedding model. The scheduler is very specific for local inference. It handles different types of activities. Ingesting is the lowest priority, and user queries are the highest. The user can additionally pause the processing or change the level of effort. The laptop is basically unusable on a high level of effort. The privacy system contains the following component. The harness assembles the prompt, compiles the module code in the enclave, and orchestrates the work. The enclave is based on the macOS seatbelt. It doesn't allow network access and only well-defined X folders. We also have an egress guard. Go to demo.milfurio.app for a quick preview. A very small subset of the capabilities are there. For example, there is no access to a foundational model. Please install the app on your Mac and ingest some data from your bank. This is the most time-consuming part. Thank you very much for your time.
All right, ModCon, let's go a layer deeper, because there's a whole different side to everything we've seen so far. The models are getting bigger, the chips are getting hungrier, and increasingly what determines where capability gets built isn't just money or silicon, it's power. As demand for compute accelerates, access to power is becoming one of the defining questions for this industry. So for this next conversation, we're going beneath the cloud itself. Where will AI compute actually live? Who will decide where it gets built? And can workloads truly move across infrastructure without being rebuilt from scratch? Well, if Bring Your Own Cloud caught your attention this morning, this is where we put the idea to test.
Please welcome Jay Jackson, SVP at Oracle Cloud, Jeff Tatarchuk, co-founder of TensorWave, and our very own moderating the conversation is head of go-to-market at Modular, Adam Nanji.
Now the future of data centers.
Thank you. Hey, everybody. I know it's almost end of the day, so we'll try to get through this one and get some good perspective. I want to introduce a couple amazing partners for Modular, Jay Jackson, SVP of Oracle Cloud, and Jeff Tatarchuk, Chief Growth Officer of TensorWave. We're going to chat a little bit about data centers. We're going to chat a little bit about power, capacity, and talk a little bit about the future of data centers. So really excited to do that talk. Gentlemen, first question. It seems to us, we keep hearing in the market that power is the currency at the moment. Even if you have bare metal, you have capacity, there's things flying around the years it takes to get power to a data center. Would love both of your perspectives on, is power the real currency? And tell us how you view, from liquid cooling to energy in the ground to solar, how are these things getting powered?
Yeah, energy is definitely the current bottleneck. When this thing took off in 2022 and 2023, the GPU was the bottleneck. And we're clearly seeing today, the people who are making GPUs can make them, but there aren't places for them to plug them in. And so that's what our focus is on at TensorWave is site selection, finding access to as much power that we can get access to as quickly as possible, just because the demand is currently just unsatiable. And there still are a lot of roadblocks to being able to get access to the power, whether there's not enough power on the grid or there's not enough supplies to power behind the meter, or being able to get access to a lot of the other components to deploy the data centers, just to get it up and going so that you have a powered shell. The amount of inbounds that I get on LinkedIn every single day saying, hey, we have a site, because they see a power line somewhere going across their land in the middle of Texas thinking that they have access to power. My inbox is just blowing up every single day. But if that were just the case of what we needed, that'd be great, but it's not. There's a lot more components that are needed in order for us to build these data centers, and it's just not there. The capacity and energy available just isn't there to match the demand. And we're doing a lot to help match the most strategic opportunities with the demand that's there, while also doing capacity planning over a long period of time. So I think initially people were very nearsighted when it came to their capacity plans. They didn't know we'd be running out of power, or at least capacity, as soon as we were. But now we're seeing a lot more customers and people who need access to compute planning for the longer horizon as a result of what's happening right now.
And Jay, from Oracle's perspective, in terms of the way you guys look at things from a global perspective on power and data centers, love your viewpoint on how you guys think about not only bringing up current, but future planning and bringing on more data centers online on a global basis.
Yeah, well, thank you for having us. It depends on the day, frankly. If you really zoom in, it looks like there are 7 different components or things that are actually your barrier to scale. But the second you zoom out, power has become our constraint. We previously kept deploying in 3 or 4 primary regions in North America, and then the second we wanted to go to the next scale, we could deploy in somewhere like Malaysia or Indonesia or Thailand or Japan, and you'd have power 6 months sooner. Or you'd have a team that could bring a data center online 3 months ahead of when you could do it in North America. And so we took the plunge of going over to some of these countries and now have done gigawatt scale in Malaysia, have done hundreds of megawatts in Indonesia, similar in Thailand. And so it's been a bottleneck that, again, when you zoom out, that has been our constraint to doing more capacity.
Both of you are at the tip of the spear in terms of bare metal and tenants and data centers and power. I think I'm very curious to understand, we've had a monolithic player for a long time dominating the space. I think this conference is compute unlocked. And we keep Chris and Cristiano and the whole team has been talking about heterogeneous compute. I'm curious from your guys' perspective, GPUs, custom silicon, NPUs, the return of CPUs. How do you view a multi-tenanted heterogeneous data centers across the board? Curious in your
Yeah, well, for those of you that don't know, TensorWave is an AMD exclusive neo cloud, and we did that intentionally. Our previous company, we had one of the largest FPGA clouds, and so we were working with Xilinx and Altera chips at the time, and our thesis was being able to just squeeze performance out of a chip, and if you could do that in an efficient and effective way, it doesn't matter what's under the hood. And so when Xilinx got acquired by AMD, our previous company became AMD's internal FPGA cloud, and then when they announced their GPU offering, it made sense for us because we saw the bottlenecks that were taking place and that there was one dominant player and that the market wouldn't be sustainable if there was just one player in the market. And so that was the moment we decided to go all in to making, to going to market with AMD's GPUs, their Instinct GPUs, starting with MI210 and then launching with the MI300s, knowing that there will need to be heterogeneous compute across the board so that we can bring efficiency across chips. Our whole thing was that it doesn't need to matter what's under the hood. I think, right now we think about, you mentioned data centers getting access to power, getting access to megawatts. It's not even about squeezing out megawatts anymore. It's about squeezing out intelligence in the most effective way possible. And so I think the best way to do that moving forward is going to be heterogeneous. And I think a lot of people are kind of currently stuck under the current dominant player in the market that has done a great job at building an ecosystem and creating a space for developers to do what they're doing today, but it's just not going to be sustainable. One of the things that we've done is we launched this thing called Beyond CUDA, showcasing all the things happening outside of the NVIDIA ecosystem. And so we celebrate the work that Jensen has done over the last 15, 20 years to build this ecosystem and software layer up, but we knew that it couldn't be sustainable if it was just dependent upon one. And so it just became about how many can work together to accomplish a greater task. So yes, heterogeneous is important.
Jay, I think is there, to what Jeff said, I think there's a crack in the monopoly in the sense of there are so many other optionalities now. Are you seeing that across your data center footprint in terms of multi-vendors and multi-tenants?
Yeah, for sure. I mean, we tried to do this ourselves with our Sun acquisition from 2010 to 2018. We tried to build our own data center GPU. And there was a small business unit working on this, and we decided this is way too hard. We are giving up on doing our own data center GPU. We probably should have continued, all things considered. But it's hard to bet against NVIDIA, frankly. We've been deploying each generation of NVIDIA compute back to P100s. And every time we think we've ordered enough, we ordered 3 times we should have ordered 3 or 4 times the amount that we did. But as we look at our ecosystem and our customers and what the demand is, we need partners who want to reduce the overall cost of compute and the cost to serve models. If I go talk to my internal teams at Oracle about what type of accelerator they're looking for accelerators where they can go an order of magnitude cheaper on cost. And so following the current trajectory, I don't have a path to do that. And so we've announced partnerships with AMD, like y'all. We have announced partnerships with a couple small startups creating chips. We've, in the more recent times, we also figured out one of the legs of the stool for whether or not one of these new accelerators was going to work is how quickly could they go to scale. And that didn't just mean how many accelerators could they roll off the line, like how many wafers could they get. It was actually, could this fit into a hyperscale data center so that we could go deploy 100 megawatts of capacity? Instead of just, we could go put 10 racks anywhere and pretend like this is OCI and give somebody a dev environment. But it actually wasn't that helpful for my customers or me to go deploy just 10 racks of something. If we want to do this, it should have a plan to be a crawl, walk, run, where you eventually have enough scale that this is an investment of hundreds or billions of dollars for us. It costs us $25 million to NPI a new product, which isn't that much money when you then think about the scale we should do when we go introduce one of these new technologies?
I think a lot of the times coming from modular and a lot of the startups, specifically in Silicon Valley and around the world, sometimes don't appreciate the amount of CapEx and time it actually takes to put a data center online. Back in the cloud days, even at the point of laying cables under the ocean to actually have latency to connect 50 data centers plus. I have to ask this question because we get it all the time, and it's insatiable, the demand for capacity from bare metal to top of the line chips. How do each of you, from both the startup side, frontier models, and even some of your largest enterprise customers, how do you manage the insatiable demand?
Poorly, frankly, like with not a lot of sleep. I mentioned every time we've tried to go buy a generation of compute, we'll plan like 6 months, or it was 6 months, now it's like 12 or 24 months in advance, and we always undershoot. And we're not trying to be conservative. We've just gotten it wrong over and over of how much demand we were actually going to be able to serve, or of customers that wanted to come to OCI versus like the global TAM for AI infrastructure. This bin packing problem is really, really hard. Like when modular calls, like we've been working with you guys for a while, and so I'll go do Tim a favor whenever he calls me. But I can only do so many favors, and I run out of capacity really quickly, right? And I'm sure you have some of the same. And so now when you're doing like build to suit often for customers, it's not like customers can go take what's in my regular plan because somebody else bought those 6 or 9 months ago. And so a lot of our compute, frankly, is sold on 5-year reservations with a bunch of it prepaid. I don't know if it's always going to be that way, but that's what it's taken to fund this build out and to keep going into new regions and to do new scale over and over.
And Jeff, do you think, a lot of times when we meet frontier models, they want the latest chipsets at a mega clusters, right? Mega, thousands upon chips. But a lot of the times we're not entirely sure if A, they required to utilize those chips, right? B, can they actually service those workloads on like a 355 versus a 455, let's say? How do you plan for growth when you have a frontier model that's raised, $1 billion+ and says, hey, I need 10,000 455s, and you say when and they say yesterday, not understanding that, there's a very big lineup. How do you plan for something like that?
Yeah, I think to Jay's point, it's not an easy one-shot answer. I think 2.5 years ago, there was plenty of chips, but not as much demand. Like we were having to sell the AMD GPUs really hard. And then when a lot of the frontier model labs, Meta, Microsoft, Anthropic, and OpenAI got behind AMD, we saw it switch from tailwinds or headwinds to tailwinds significantly. And we just saw a huge increase in the demand side of things. And so it went from when we first started having to pre-sell, we thought, hey, we can go out there, say, here's the specs of the GPUs. You guys want them? You should buy it. And then we'll figure out the path to deploying and then serving it to you. That didn't work. So we ended up partnering with AMD to do an 8,000 GPU cluster of MI325s. And it was kind of the Field of Dreams model where it's build it and they will come. And they did. We literally sold that cluster out by the time it was built, once we announced that we were building it. And then when the agentic workflows took off and models got bigger and the amount of people using AI increased, we saw the demand for capacity continuing to grow significantly beyond what we could even keep up with. And so we have all the hyperscalers that are eating up as much data center capacity as possible to deploy their own compute. And then everybody else, all the other 150+ neo clouds that are coming in behind to eat up the rest of the capacity. And then we're all kind of circling around some of the same large customers. You have the top 5 big guys, then you have the other 100, big neo labs that need access to, 1,000 or more GPUs. I mean, frankly, a long story short, to answer your question, how do we decide capacity? It's based upon if it's financeable. We have to be able to finance the deal, and we're only able to finance the deal. I mean, in the best case, if we have an investment grade customer with a take or pay contract for a long period of time, 5 or 6 years with a prepayment, that makes it a lot easier for us to be able to prioritize who gets what. Then it trickles down to all those that can do the prepay and those that can actually finance the deals. But one of the things that I see the hyperscalers, I see the frontier labs that are eating up most of the compute on long-term contracts. And then we have the other labs that are used to just doing 1-year terms, 2-year terms. And I'm like, there isn't going to be a lot of capacity for those labs that are only eating up a smaller amount. And so I do think those that are able to pay for the compute over a longer period of time are the ones that are going to get the capacity. And so we have VCs calling me all the time saying, hey, we're about to write a $100 million check or a $300 million check to this lab, and it's going to be for compute. Do you guys even have a place for them to spend it? And so it is, though, like you have, people will call, Modular will call, hey, we need, this many nodes. Can you help us out? And I say, I want to. I wish if we had it now, I would give it to you. But
I think I've called both of you every week for the past 16 weeks, just so we're clear on compute.
And it's crazy. And so, how do we manage it? I mean, it has to, we have to be able to stay in business as a company.
But what happens in a scenario where you go out, you purchase a chipset at that current point, that chipset is the current sort of top of market chip, and you sign a multi-year deal, as some of these top frontier models and neoclouds are doing. And throughout the course of that deal, those chips effectively, I don't want to say the word obsolete, but a new, maybe multiple series of chips comes. What happens for both of you in this scenario where?
I mean, we saw what happened. CoreWeave just announced, they were able to re-up and resell their A100s until 2019 at a similar rate that they signed up those A100s for. And we're seeing the same with our early chips that we sold with the MI300s and 325s. The price is going up. And as long as people can get tokens and flops out of something, they're willing to pay for it right now. That's how strong the demand is.
Yeah, like you can fit the latest Qwen models on an MI300 or an A180 gig GPU. Like as long as you can fit current gen of models, we'll continue to use all of this older capacity. Yeah. There's a point where it doesn't make sense for me to keep those computers in service. We haven't hit that on any. I still have P100s that I was looking at this last night that have 24 customers running on them. I don't have very many, but there's still customers on compute from 2018. The stuff breaks. It's not that great, but you have customers still using this stuff.
The last 2 or 3 years has been the years of training. We've seen all these models come up. To your point, compute skyrocketed to train these models. I would argue, and even Modular, we're looking at from an inference, this is the year of inference. I think we've seen a few big players come into the market, ourselves included. How does now, from an inference perspective, in a post-training world, how do both of you look at not just data centers and capacity, but how has inference sort of reshaped the way both of you look at compute in your businesses? Maybe we'll start with you, Jay.
Yeah, I mean, with foresight, we would have designed our current data centers differently, for sure. I mean, we tried to stuff, I'm sure a lot of my peers have said the same thing. You tried to stuff as many computers as you could into a certain power profile and use the whole thing, right? Like you had customers who wanted to buy every ounce of power in a data center. And now, backing off of that, we could have put several different accelerators in there, changed our mix of what compute looked like in the data center, and had a much more efficient build for a bunch of our customers. We didn't do that though. And so there's a decision that we make on a bunch of this capacity of, do we rip, replace, and then rebuild what's in this site? I mean, we build all of our positions to be fungible for anything that's air cooled, and then same for liquid cooling capacity. So as long as we can fit different accelerators, different compute in there, we are re-architecting to serve discrete inference workloads well, but we might get it wrong again. I think this is one of the challenges is it works really well for this current split of pre-filled decode, but I don't know if that is going to be our architecture for a year and a half from now. And so we continue to take a bet that you're going to want more throughput, more latency, and that was a lucky bet we made all the way in 2021 when we built the first training infrastructure. It's we built high throughput, low latency networks, and I think we're going to make that bet again, even if it means it's a little more expensive. So I don't know, we're trying to take guesses, but
on the neocloud side and some of the other hyperscalers that both of you work with, and obviously you have deep relationships across the board. As an ex-AWS and Microsoft guy, one of the things we always struggled with was we have an amazing cloud business, we have an amazing connectivity to enterprise, but we were missing an inference capability, almost like an inference control plane. And outside of bare metal and the contribution margin on cloud and cloud itself, we've been seeing in the industry, there's always this demand for if you have the right inference control plane and can provide the best TPM numbers, you will win business. Do you guys see that in terms of that inference capabilities then driving more bare metal and more GPUs? I mean, for us, that's definitely the story, but I'd love to get, Jeff, your perspective if you see that.
Yeah, absolutely. I think, I mentioned before, it was about kind of squeezing out intelligence per watt, and we could only deploy so many chips within, a certain data center per megawatt. But now it becomes about the optimizations that you can make within the data center. And I think the inference layer is the layer where if you can bring up a 2x optimization within the inference stack, you don't have to deploy more GPUs, you get access to more compute because of the optimizations that were made. And so we're seeing it across the board with a lot of companies that are optimizing the inference stack. And I think there has to be optimizations across the board within the whole stack in order for us to squeeze out all of the juice we can out of the power to turn that into intelligence. And so the inference layer, people want latency, they want quality and efficiency. And the more we can optimize that, the better we'll be across the board. And so, yeah, I think customers definitely are looking for that and want it.
Yeah, and I think one of the things we learned from partnering with you guys is I'm not going to be able to do the same type of optimization work that Modular has been able to do. I won't be ready to go release the next model and the next gen model and the model after that with all of these performance improvements. We're focused on delivery, execution, keeping all of this compute healthy. Yes, we have a software team trying to do some of this, but it's not been our core business. And so this is why we've leaned into these type of partnerships so that when customers want to come consume tokens or when they want to consume something more than just bare metal infrastructure, we have an offering for them. And we see this all the time. If you go talk to any bank in New York, you will have people asking to consume intelligence through tokens. Same thing if you go talk to healthcare companies. They don't want a bunch of GPUs sitting in my data center. They want to consume a platform. They want to have flexibility on which models they consume. They actually really don't want to know where the compute is as long as it's in a certified, compliant environment. They just want to be able to consume intelligence. And so that's why we lean into a partnership like this in order to actually go serve this technology, because we won't build it ourselves.
It's really interesting too. A lot of our customers, Modular's customers, especially on the frontier model provider side, have come and said, around this, of course, TCO is a huge component for them, but the perf has to be there, right? The performance from a current NVIDIA chip to a Qualcomm chip to a AMD chip has to be there. And I think for us, a lot of the model providers have told us that not many people, in fact, nobody can get that type of performance, let's call it upper 90 percentile from NVIDIA's chip minus us. And so we're actually seeing a shift where startups in particular, late stage model providers, see the material cost benefit to them going on another chip with $2 per hour on a GPU price is highly material on a 10,000 chip workload. And to your point, Jay, you have to have optionality. I think now, especially in the inference world, you have to be able to have optionality, and you're talking about hundreds of millions of dollars potentially left on the table. $64,000 question for both of you. You guys are in this space, you've been in it for a long time. Where do you see data centers going? The next 5 years, outside of everything you've seen in the last 5 years, where do you see this going from? Is there enough land? Is there enough power? Are there enough, tenants? Love your future perspective on where you see this thing going.
I know people are going to say, are they going to be in space or in the ocean, right? And I'm sure Jay would back me up on this. They're hard enough to manage and maintain on land, but to be able to do that up in space or in the ocean, these GPUs and servers and racks are finicky. But to your point, going from server scale to rack scale, and I could see it's going to go to essentially cluster scale, where we're going to have, we're deploying supercomputer systems at scale to the tune of hundreds of thousands to soon enough millions of GPUs over time, and starting, and we could see, things are shifting from that to this day. And so, yeah, seeing it more at a systems level, seeing more optimizations that are being made. I think right now it's just like, hey, let's plug in what we have, make it work, figure it out. But now we're at a place where we've hit the bottleneck, we've reached the constraints, and this is where there's going to be a lot more room for optimization and innovation across the entire stack. And so I'm excited to see what's going to happen in the next 5 years. I also am concerned about kind of where we're at. I don't know here if you're based in the Bay Area, we're kind of in this echo chamber of technology and enthusiasm around where things are going. But when we're building these data centers out in the middle of America, there's a lot of fear around what's coming, with this world. And so I do think in order for us to get to the next 5 years, like there needs to be a lot of education around infrastructure being built and the benefit for community. And if there are risks, what are we doing as a society to mitigate those risks? I think, 5 years is great, but I think there's a lot of uncertainty in society today that if we don't spend the time to educate the world beyond just what TikTok and Instagram is doing to put fear in people, we're going to be in trouble. We're not going to be able to keep up with the rate and speed to get to the 5-year point to optimize things. I know we're optimistic, we're excited, we want to see the innovations and technology happen, but in order for us to get there, we still have a lot of work to do.
There's a tremendous amount of, to your point about being in Silicon Valley, there's a tremendous amount of venture capital in the ecosystem. We've all been in this space for a couple decades. It continues to just be fueled and fueled and fueled. The goalposts are changing every quarter. I would even argue that sometimes you'll see a lot of startups raise capital just to go back and pay compute bills with hyperscalers, and for both of you as well. Where do you see the point of inflection coming around? Do these startups have tangible business offerings to be able to go and scale? Because a lot of the time, the VC dollars go back to you guys, back to the hyperscalers, back to compute, and the cycle keeps going and keeps going. And where do you see the inflection point is there enough juice, if you will, to have these businesses have that trajectory? And when does this thing stop, or does it keep going? Because we live in this, I would say, arguably a little bit of bubble. You said, Midwest America. I'd say even the rest of the world sometimes doesn't see what's happening here. I'm curious of both of your perspectives being in the Bay Area.
Yeah, I agree with everything you shared about what the next 5 years will look like. I also want to call back to one of the points you shared where, hey, you make cluster decisions based on what's financeable. Like, we don't choose to sell 5-year contracts just because it's a risk mitigation strategy for us. Like, I'd love to sell 1-year contracts or give you capacity on demand. Yeah, it's just been the business model we've had to come to. And so I think the question for our side is, what are the next financial instruments that we have to create and manufacture in order to do more capacity? Like, the business models that exist today won't achieve the scale that our customers want to go build to. And so we're having to become incredibly creative to figure out what capacity for 2030 looks like and 2031 looks like. Though I don't know. I think the ChatGPT had its Apple or iPhone moment where when you touch this technology, you know you're going to use this forever.
Gone are the days of 6-month and 1-year
for now.
deals.
Well, I think when AI took off and the only compute you can get access to was at Azure and AWS, they were the monopoly, and so they could charge the $6 to $8 an hour for an A100 or an H100 and do these really long-term contracts, which frankly sent a lot of these first early AI companies into bankruptcy, and they couldn't get out of it. And so I think that sent fear into the VCs, so that when they're raising money for their next companies, we hear it all the time. Our VC, our board said we can't sign up for more than a year until we hit product market fit. Well, come back to us when you have product market fit, and we can then get you access to compute. And so the VC world has then kind of retracted and imposed, say, hey, don't sign up for any more than 6 month to 1-year contracts. But now they're kind of, beating themselves up because now they can't get access to compute because now the demand has reached a place again for those 4, 5, and 6-year terms. And so, yeah, it's an interesting kind of shift that's taken place. But it's driven by where the money, like who's going to pay for it and when are they going to get that money back, and do these startups have what it takes to actually get that money back? I don't know.
But we'll ride a wave again, right? Like, you've seen it in the past where you have, and we're in this extremely constricted cycle today on demand, and then it will swing back in the other direction. Like, I'll have available compute at some point. I don't know when, but it'll swing back.
Are you guys sold out?
We'll take it, buddy. Amazing. I want to thank Jay Jackson, SVP of Oracle Cloud, and Jeff Tatcha, Chief Growth Officer of TensorWave, for joining us. You've been partners for Modular for a very long time, and we appreciate you guys joining us here for ModCon 2026.
Honored to work with you.
Thanks, Adam.
Thank you. Yeah.
Jay, Jeff, thank you. And Jeff, Adam, thank you. So Courtney, we've talked a lot about models, chips, benchmarks, clouds.
And eventually all roads lead to a power outlet.
That's pretty much. And that's an important shift. Scaling AI isn't just a compute problem anymore. It's an infrastructure problem. And increasingly, now a physical one. Before we move into our final stretch, here's George Meredith with Professor, an instrumentation-based profiling library. We'll see you soon.
Have you ever needed to optimize your code, but only knew the total runtime of your program? Coarse measurements like these are good final metrics, but they do not tell you where your program spends its resources and where you should focus next when you try to optimize it. To identify such bottlenecks, we can use sampling profilers like Perf on Linux and Instruments on macOS. These are processes that periodically interrupt your program, look at which part of your code is currently executing, and aggregate the results. An alternative is to use an instrumentation-based zone profiling library that allows you to define profiling zones in your code. These are named regions of your code for which you want to collect performance statistics. Professor provides exactly this functionality in pure Mojo. Let's look at a simple dummy example to showcase how to use the zone profiler. In this code, do work represents some arbitrary workload, while do more work performs some additional work and internally calls the do work function. Finally, the main function calls do more work 100 times in a loop and performs some extra workload. Our goal here is to measure how much time our program spends in these two functions. When we add our instrumentation profiling code, the file looks like this. First, we need to define the profiler and the instrument that samples the performance metric. The library comes with built-in instruments like wall clock that measures wall clock time and variant TSC, but also allows you to define your own instruments by implementing the corresponding trait. There are two ways to define profiling zones in your code, and both use the zone method that accepts the name of the zone and returns a linear handle to it. Since the handle is linear, the compiler forces us to consume it in order to close the zone. Failing to do so will result in compilation errors, catching bugs early. One way to specify the zone is to bind the linear handle to a local variable and then explicitly close it, while the second, more flexible and thus recommended way is to use its context manager. Then focusing on the main function, first we need to start the profiler so that the instrument starts counting. Then we have the original main code, and finally we need to stop the profiler and produce the report. The report will look similar to this one. First we have the name of the zone as well as its source location. Then we report the hit count, which indicates how many times each zone was entered and exited. After that, we report inclusive and exclusive times. Inclusive is the time that is spent in each zone, including the time that is spent in children's zones, while exclusive is the same time when we ignore children's zones. To illustrate what these times represent, let's look at the do more work zone. Inclusive would be the time that is spent in the whole do more work function, while exclusive would be the same time discounting the time that is spent in the do work function. Then we have the best and average performances, and finally, we have the percentage of total runtime that is spent in each zone, including or excluding the children's zones, respectively. Based on these results, we can answer the question, where did all the time go? In our case, we see that our program spends most of its time inside the do work function, and we should try to optimize it next. The library comes with some additional features that intend to assist developers with profiling their code. We just saw that using the zone profiler with a wall clock instrument told us where our program spends most of its time. However, Professor also provides programmatic access to performance events in order to identify the reason behind these bottlenecks. Finally, repetition testing is a benchmarking method that explores the asymptotically best performance of a function. For more details on the features and the roadmap of the library, please visit the GitHub repository. Thank you very much for your time and happy profiling.
We're now in the final stretch, and after spending the afternoon looking underneath AI at the chips, benchmarks, infrastructure, and power behind it, we're going to come back up the stack and look at what all of that enables. Next up is Morgan Suo, Head of US Business Development at Minimax, to share what open-weight Omni-Context generation enables for AI video.
Please put your hands together for Morgan Suo.
Hello, everyone. Thanks for staying here in the late afternoon. I will show you something cool today to save the time because I think not too many people, but I think it's still worth the time. Maybe before I do any introduction, I will play something good for you first. Okay, 16 by 9 and 15 seconds is not an After Effects work. Actually, it was generated by Minimax A3. And here's the first frame and last frame, and also the prompt we put in the model. Then we generate the video you saw last time. And you can see with this first with the logo and also with how we want to animate the whole thing. So we go back and we can see it again. The continuous line, all the clean text, and also the animations, the text here. So anything you want to put in the prompt, the model can help you to put that. So hello everyone, I'm Morgan. I'm from Minimax, and today I'd like to show you what we want to show in this multimodalities and the frontier in what we think of this AI. Okay, here's some quick context on who is talking today. Minimax is 4 years old, and is an AI foundation model company, and is founded in 2022. At that time, from the very beginning, the zero, we didn't imagine now we have the people, we have the users, the number, and access, even most of the countries have citizens. I'll show you the number later. And what we have in the different modalities and what we think of it is if we put any modalities in consideration like text, image, audio, video, but we think of it as the same context, not a separate business line, how we develop it, how we put that into one same context. So from today's talk, the most relevant part is we do not treat these modalities purely as isolated business lines, and we want to create a research environment that we can put all the study on how intelligence, perception, generation can share the same common foundation. So the foundation actually, the foundation actually draws two ways. The first is the API platforms, and the second is the AI application. So through the API platform, the enterprises and also the developers can touch our APIs, touch our models across the language, the speech, image, video, and music, and integrate them into their own products. And across all the AI application, actually the user, individuals, the work team can use these AI models into their actual daily workflow. And across all these modalities, all these applications, nowadays for the AI application, we have over 300 million individual users across over 200 countries. And also for the API platform, we have over 1 million enterprises and developers across over 10 countries and regions. So how we interact with that many of the users and how they give us the feedback. And now we can see if we took their feedback, took their comments into our development, into our research, what would happen? So for Minimax, our foundation, the whole work, we spans 3 major areas. The first is the large language model, and it's called M3. And the second is the audio model with music and speech capability. And the third is the video model, which I will show a lot today. It's called H3. But if you think of these separate models, you will think, oh, I have Cloud, I have 11 Labs, and I have View, I have Cdance, so in different modalities. And what your Minimax think of this? Especially for the video model, what we are thinking is how we put different modalities into one single context. Like you said before, when we want to generate any videos, we put different video model behind that. Like you put text to video, image to video, reference to video, and also like other motion graphics. So you do a lot of these tools and tasks. But now we put all these modalities into one single context. So we generate with that. So today, I think Minimax H3 can help us to answer how do we preserve this intelligence and integrate information across different modalities and also represent the real space and time, and then at the very last, scale to long real-world inputs. So this is the problem I will focus next, and I will let Minimax H3 to answer it. So what is Minimax H3? It's an open-weight multimodal video generation model. And now you can see about the envelope. It has 4 to 15 seconds output and also 24 frames per second. And you have the 768p as the base. And also you can use our regenerate module to have the 2K version. And also you have different aspect ratio, and you have FL to VA and reference to video and audio. But actually, this envelope is not that interesting, right? So after of this, what's the magic of it? I think I'll put something, a demo later to answer this. So what this single text will batch for you? So this is the input video. So you can check on the left is the real PC. You work with it every day. And on the right is an animated cat. So we will let these two things in different words to interact together. So this is the reference video. Okay, and the prompt, actually the instruction itself is very narrow. So we don't deliberately to describe what type of effects we want, but we only put like enhance and apply visual effects to this video, while preserving its composition, the camera angle, and the cat position, and the timing. So everything keeps this look, but only change this. Not change the scene, but keeps the look. So we can see the results. Watch the edges, watch the blue, and also watch the debris on the table. So this is everything that we didn't put in the prompt. We didn't tell the model to generate, but the model just analyzed everything as the input and to tell us what should follow physically. Okay, then the first thing I mentioned, this model is open weight. So what type of thing we opened? First is these two task-specific checkpoints. First is FL to VA. FL is first and last frame. So with text and first and last frame to video and audio as the output. And second is the reference to video and audio. So take all the references like image, video, audio, and the text as together and to generate the final video and audio. And second thing is the complete local stack. So actually, you see the number is not that big. It's only 33 billion parameter DIT infra. And also second is the Qwen3 VL encoder. and visual VAE and audio VAE. And third is the visual weights. We released it in BF16. So it's a full stack that you can use it to generate exactly as we have served the service online. And four is we support it across almost all the open source community and infra. Confi UI, SGLang, VRM Omni, diffusers, MLX, and 1GP. MLX actually I will show you. Actually is about if you want to run it even on your Mac. So MLX is Apple created for you want to run some model locally on your Mac. Okay, so here it is. You want to run this model, so what type of machines you can have? I think in three camps. The first one is the machine in your bag, is your PC. And second is the machine under your desk, is some workstation. And third is the machine in the data center, so you can run it scalingly. So you can check this number. So if you want to run it in a consumer GPU, like everyone is very familiar with, for example, the RTX 4090, RTX 5090, and you can run it. I can show you the number and also show you the performance when we release it and the people in the community try it. And the second about the consumer, like I said, it's only you can run it on a Mac. And third is about the data center, like 4 B300s, and you can run a BF16 full stack open with video model. And now after we release it, this model is kind of fills the gaps between the weights and the final products. So what type of things we have collaborated with all the community and the ecosystem. You can check from the create, customize, the serve, and also the extend. Every layer, people are working on it, and Reddit, different communities are talking about it, how to optimize it, how to have a better optimization of this model. So it is only after 40 hours we release the weights of the A3, you can check the community is very insane about this model. So about the different data center, workstation, the consumer laptops, and also about your Apple laptop. So I can start from the Apple laptop. This one, I think the text is not that big, but I can take one line. For example, with the M5 chip, and it's a Pro 64 GB memory. So this is some very common computer you will buy from an Apple store. But you can run H3, this model, on it. And if you want to generate a 10 seconds with the resolution of 448p, so you can wait 30 minutes, just have a cup of coffee, and you will get this model, get this video as the output. And another sample is if you have a RTX 5090, one of my colleagues just went to go like line to buy the RTX 5090 in GTC this year, and I know that maybe some of you have that yourself. So if you have one of them and you want to generate a 5 seconds and with the 1280p, and you can have this video as the output in less than 3 minutes. And also for the data center, as I mentioned, you can check the second line. So this is the official VRM recipe. So if with 4 B300 chips, and you can generate this 8.7 seconds video in 87 seconds. So not only that you can access this model from our official API, from our partners, you can also do it yourself to deploy it. So with that, you can do the prototype in your laptop. You can produce it in your workstation, and then you can still scale it in a data center. Okay. Next, I'd like to introduce the whole system architecture of H3. So you can check this graph here. So we have 3 different modules. And also you can check that in the community, in Hugging Face, where we open with and where we can serve the online service to that. And very focused, we can put first is the base generation part, the H3 base. Actually, this is the part we open with now, and you can download it and you can deploy it yourself. Then together with this module, we have 2 very important modules. The first one is the context IR. So with that, it can help you to understand the prompt, the media, any audio, image, video you put as the input, and also it can help you to create a context intermediate representation. And then it will put that into the H3 base to generate a video. And the last module, what is that? It's the H3 Regenerate 2K module. So what's the difference between this Regenerate and a upscaler like Topaz? It's not only an upscale from a lower resolution to a higher resolution. Actually, in this module, we put all the context we extract from the first step, and together with the output we got from the second step. And then we put that into the third module, and it will help you to generate a brand new video, but with all the details, all the context in it. So it's not just upscale and no context of what type of things I need to create, but the model actually it knows, oh, we need to keep the very smallest text on the product. We need to keep the consistency of the people. And I know that about the cat, we need to analyze this is the real PC and this is the drill. So when the drill just put on the PC, what type of things should happen? So with this, we will have the final result. Let's dig it in details. So what type of things we are using in behind of H3? So you can see there's four layers. The first thing is the visual condition. So in the visual condition, we put the encoder for the text, for the pixels, for the audios, and we put all the things we extract from the encoder and together with these things, the noisy targets, then into one sequence in the second. So we pack them, all these contacts into one sequence. And then we took this context into the third one, the Omni transformer. So with this, I think we should, what's the takeaway here is first, the 50 shared layers, and second is a single stream, and third is the joint video and audio denoising. What is the joint video and audio denoising? Actually, for other models, they will put this audio and video to create it separately, to denoise separately. So then they will stitch them together. That the result will be that in some time there will be some mismatch between the audio and video in the final output. But for H3, we put this video and audio to denoise together. So each of this part will know what should happen with the audio, what should happen with the video, and then we will have the final result perfectly. So here's our performance and in the leaderboard, but I think this is not the most important, but still I need to mention for Minimax H3, now ranks the first in artificial analysis video editing leaderboard, and also ranks the first in Arena, also in video editing, and also we are tied first place in Arena for AI image to video. Okay, so after this whole argument, everyone wants to see something even cooler than the cat sample I showed, right? So now is the demo time. I want to show you first about how we can do with the commercial grade generation. So for H3, like I mentioned, it's a single context model. So you put all the text, all the image, the things together and to generate the final result. So when it comes to commercial use cases, what type of things should be the most important? The first thing is the text, and also about the brand's assets, about the UI, about everything that showed on the product on the screen. We need to keep it very consistent to what we want. And then we can spread this to different industries like film, advertising, gaming, and brand and retail use cases. So here's what I want to show you, the first one. This is a commercial, and I think everyone will be very familiar with this. It's a Peking duck. It's a Peking duck commercial. And we want it to have a full parody of an Apple product launch film. So it's very pure black background, and it's studio-grade lighting, and ultra slow rotating close-up, and also minimal oversized text, and also ethereal electric score. So let's check what we have. Thank you. Yes, your next duck is not a duck, right? Sure. So actually, I created this myself, and I only use this prompt and put that in the model. So one shot, I got that. But I used AI to give me some support. So it tells me you can reserve this RMB 198. So it shows like it's the original where this Peking duck come from. So. Okay, the next sample is about the visual concepts and the motion design. So this is some Korean K-pop style. So we want this model to take these two images as the reference. So first is that three girls. So you need to memorize the faces of them. And second, we want to put this magazine style into consideration. So it's the late 1990s looking. And then we generate this music video with all the subtitles, and also you can check the lip sync with all the singers.
One look, split noise, move fast, read nothing. Bass hits, I don't break, cut back, hit harder. Static talks, I'm light flash, red, black, white flash. No echo, we detonate, hard cut, no mercy. I don't fade, I don't fade, I don't follow, no return, I'm the signal.
So for anything like you want, because it's very easy, yeah, thank you to that. 2 images and some prompts, you can get that. And if you want to have more precise output, you can put a reference video there to change it if you want. Okay. Okay, the next sample is about the product and e-commerce marketing. So this is also 3 reference images. 2 models and these different angles of these 2 girls, and then about the eyewears. Actually, this is a commercial of this eyewear, and we want it to be very clean and in this very high-end commercial style. Okay, so for the advertisers, you can check the eyewears. Actually, it keeps very well to the consistency to these 2 glasses. I think the advertisers will focus on this to show that, and also the final, brand name. So if you want to put any text in the very end, you can put your text in that. And also, you want to keep your branding styles, you can put it as the end frame, so you can keep the consistency to your brand. And next, I would like to show you about more cool things about the different multimodal in different languages, how we can clone the voices, how we can put, because we can support 12 references in total and 3 videos at most. So what if we put 3 videos together to generate this 1 video? So this is the case that we have 3 reference videos, and we want to extract very small things from each of this video and to generate the final result. So first, this is the main subject of our output. And second, we want to use this as a reference for the vocal and also the physical delivery. And third, we want to refer this camera move from this Hitchcock style. So let's check this output. I'm just a fool to fall. Okay. And next thing is about how we rank the first in the video editing leaderboard, right? So I want to show you something that is very easy that you want to show, and but you have this original videos and you want to change the backgrounds, change the characters, so you can have different commercials in different scenarios, but without reshooting it. So this is the 3 references, 2 reference images and a reference videos. So the prompt is we want to replace the child at the back right with the golden retriever in the image 1, and also replace the khaki jacket in the far left of this video to this denim jacket. So just we can focus on these 2 keys. And this is the reference video we have. And this is the output. So you can mask anything that in this video and just change a pixel of it. And the next thing is, what if we put an audio into it? And what type of thing we can have?
All the world's a stage, and all the men and women merely players.
So this is the reference audio. We want to use this very sexy voice from this audio. And this is a soundless video, only with music, but we want this character to speak. And the line is, follow the wind, live free, leave worries behind, enjoy the moment. So let's check.
Follow the wind, live free, leave worries behind, enjoy the moment.
Okay. Hopefully you all enjoy the moment now. Okay, here's the final video, but still it's very cool. But I think should be a little difficult for some of you, but because it's in Chinese. But I want to show how we can proceed with different things. So this is a reference video, and we have the bottle of the drink there, and also we have the Family Mart as the convenience store, and we want to change at the final because the girl will take off a bunch of snacks, and we want to change it to a bunch of cooks. So let's check the
这个是我最近发现的一个特别好喝的饮料。
It's a drink
然后这
in
家
blue.
店呢，是我经常来的一家店。然后今天买了一些小零食。
Okay, so this is a bunch of snacks, and also from the Family Mart, we want to change it to another name called Hu Hui. So let's check the output. So we changed that to the Coca-Cola, right?
这个是我最近发现的一个特别好喝的饮料。然后这家店呢，是我经常来的一家店。然后今天买了一些可乐。
Yes, yes. You check that. Everything you want to change in the video, and you can put that in the prompt, and the A3 will help you to achieve that. Okay, so here's what I want to show you with Minimax A3, but I think it's not the end of this speech, but it's the starting point for you to explore it and to know what it can do for you in your own laptop, in your workstation, and also in your data center. So if you want to know more, you can contact us, and also you can search Minimax online, and you will find us like we are already a public company, and we are on our way to do the AGI and want to reach, to achieve that intelligence with everyone as our slogan. So thank you all for today. Thank you for joining us. Thanks for your applause today. Thank you. Thank you, guys.
Minimax H3, what a powerful Omni model. Thank you, Morgan Swell, for walking us through all this. That really brings the full day full circle. From what models can do to the infrastructure underneath them, everything we heard today comes back to making the whole stack work together. As we bring ModCon to close, let's look at what came together today. We opened the day with a unified AI compute layer, and then saw that idea play out across the stack. Modular Cloud running at scale and now generally available, Mojo 1.0 and what's next for the language, and Max running across hardware now with Qualcomm NPU support.
And down the hall, a robot ran its entire demo without notes, which is more than I can say for myself.
Clearly must have had a bigger context window than we did. But seriously, a day like today only happens because a huge number of people and companies show up to build together. So thank you to everyone who joined us today from across the hardware ecosystem. Qualcomm, AMD, D-Matrix, AWS, Oracle, TensorWave, H-Tech, and so many others. A multi-silicon future can only happen when an ecosystem comes together. And today, we saw that happen.
A big thank you as well to the teams building on the platform and to the investors, analysts, model builders, founders, and developers who joined us today. And to everyone who took the stage, shared what you're working on, challenged assumptions, and took on the hard questions with us, another huge thank you.
And a huge thank you to our very own Josh and Danny, who kept the conference theater running all afternoon, and to the entire production crew, who have been here since 8 a.m. yesterday, making sure everything you saw today feels seamless.
A few things before we send you upstairs. Everything that you saw today is available now. You can find the docs at docs.modular.com or get started with pip install modular. The reception begins at 5:30 on the 36th floor. There will be food, drinks, as well as many of today's speakers. So if a session left you with a question, now's the time to go ask it.
There are only a couple of elevators to the 36th floor, so feel free to wait and grab a drink in the foyer or check out the demo booths if you haven't already.
And if you took a photo with Mojo or Max for today's challenge, your plushie will be waiting for you upstairs.
We started this morning with a simple idea. As AI becomes more heterogeneous, the stack has to work as one. And today is the evidence that the world has finally arrived.
And a lot of the people in this room are helping to build it. Thank you for spending the day with us. I'm Courtney.
I'm Deep.
And this was ModCon 2026. We'll see you upstairs.
Thank you.